lined up for you today. Not only that, we also have the much-awaited talk by Chancellor HBNI later in the evening. Before we proceed, I have a couple of announcements. The transport for BRC visit scheduled tomorrow afternoon will leave from Training School Hostel at 2:30 p.m. So please make it convenient to board them. As per security procedure, please make sure that you do not carry mobile, pen drive, or any electronic item during the BRC visit. Also, please cross-check your name in whether it is included in the list at the help desk. The second announcement is regarding the ACTRAC visit scheduled for Saturday. The transport for this will leave at 9 a.m. from Training School Hostel on Saturday. Please check whether your name is included in the list at the help desk. If not, you can add your name now also. The last announcement is that the pen drives with all the presentation loaded are available at the help desk. The outstation participants may collect it from the help desk today. Others may please collect it tomorrow morning. So without further delay, let us start the first session of today and the fifth session overall. To chair the session, please join me in welcoming Professor Majumdar, Director of Harish Chandra Research Institute. I kindly request you to come to the stage, sir. This way. The first speaker will be joining us online.
Hello.
Hi, Vedanga.
Good morning.
Good morning. Why can't I hear you? Vedanga, will you say something to make sure that all of us can hear you?
Yeah, can you hear me?
Yeah, things are working fine.
Okay.
So I think we are almost at 9:30. What is the time now? Yeah, so it's time to get started. First session today, we start with Vedanga describing physics activities at NISER to us. Half an hour's time and 5 minutes for questions. Vedanga, it's all yours.
Thank you very much, Professor Majumdar. So thank you for very good morning to all of you. And thank you for HBNI for giving this opportunity to talk about NISER School of Physics and few topics of recent publications. But I must start with apologizing, not being there, physically present, last minute change due to some unavoidable reasons. So National Institute of Science, Education and Research is one of the younger sister institutes in the DAE family with a unique undergraduates program. It was announced on 28th August 2006. The academic program started on 10th September 2007, close to 14 to 15 years back. And on 7th February 2016, the Prime Minister dedicated the current campus to the nation. What we do at NISER is very nicely embodied in the logo and the motto. The motto being knowledge imparts immortality, and the logo symbolizes some important aspects in basic sciences, biology, chemistry, mathematics, and physics. You can see the benzene, the DNA, the black fractal structure forming part of our logo. Now for the academic schools, we have School of Biological Sciences. Dr. Harapriya Mahapatra presented yesterday. We have School of Chemical Sciences. Dr. Srinivasan will talk about it. School of Computer Sciences, School of Earth and Planetary Sciences, School of Humanities and Social Sciences, School of Mathematical Sciences, which Dr. Brindaban Sahu will talk about, and I will talk about School of Physical Sciences. There are two centers, Center for Interdisciplinary Sciences, where faculties from biology, chemistry, physics, and earth and planetary sciences come together. Then there is a Center for Medical and Radiation Physics, which caters to the societal aspect. And our detailed project report also envisage a School of Engineering Sciences oriented towards DAE mandates, accelerators, nuclear engineering, and chemical engineering. Now, the programs, all schools follow these major three themes. In science education, we have our flagship 5-year integrated master's program after +2, integrated MSc PhD program after BSc, and PhD program after MSc. NISER also faculties engage in research, both in theory and experiment, in all frontier areas of basic sciences. Science outreach is also one of the most important activities carried out at NISER. All the degrees are awarded by Homi Bhabha National Institute, HBNI. Now here is a glimpse of NISER members, and in just one slide what we have done. The faculty, the scientific staff, the administration staff, the students. We have graduated 555 master students, 122 PhD students, and generated extramural funding, non-DAE, quite a bit. If we quantify the achievements in terms of publications, which are important components in basic science, we are at the moment having high quality 475 papers a year, and they are being well cited. The citations are, as you can see, the numbers are given below. Physics forms a dominant component of it. We are also the largest school among the others. Here is a school-wise breakup, but I'll not go into that. We try our best to link our research programs to various sister DAE institutes. Physics, biology, chemistry have a lot of synergy with other institutes, as is shown here. The School of Earth and Planetary Sciences is also trying to form active collaboration with sister institutes. Now a brief note on the Center for Medical and Radiation Physics. It is to cater to the country's need of having well-trained medical physicists. Cancer cases are growing, and radiation therapy is one of the most important techniques to cure cancer. So we would be needing a lot of machines, and people with the skill set as shown in this orange box are required to run, operate, and help. So we have a master's course in medical physics. The first year is core physics, second year core medical physics, and third year a mandatory 1-year internship as per AERB guidelines. The advertisement is out. We are accepting online applications from 10th of April, and we are collaborating very closely with BARC, AIMS Bhubaneswar, Acharya Hariyar Postgraduate Institute of Cancer in Cuttack, and TMC. They are the partners in this program. We have a Center for Interdisciplinary Sciences. It is mostly having facilities related to imaging. I will not go into detailed specification of these instruments. If you are interested, you could contact us or visit us, and we will give you all the details. It has the transmission electron microscope, time resolved fluorescence microscope, and such facilities. Now coming to School of Physical Sciences, its mandate is aligned along the mandate of NISER, the 3 areas of science education. We do research in theoretical high energy physics, theoretical condensed matter physics, theoretical experimental high energy physics, and experimental condensed matter physics. We have 32 faculties, 2 more are shortly going to join. We have about 200 master students spread over 4 years, and we have PhD students close to 100 and integrated PhD 34. This is the physics family, and our house is this building which is in the center. We also have a departmental library. What I want to mention is it's 24 hours open and run by students. In this 5-floor building, we have a very nice open space for discussions and deliberations and just sitting and relaxing, the lounge. Here is quickly the faculty profile. We have faculties in string theory, in QCD, in theoretical nuclear physics. We have faculty in experimental high energy nuclear physics, particle physics, astrophysics, and cosmology. We have faculty in theoretical condensed matter physics, statistical mechanics, mesoscopic systems, strong correlations and topology studies, multi-scale material models, ultra-cold atoms. And in experiment, magnetism, superconductivity, devices, soft matter, nonlinear dynamics, nonlinear optics, atomic physics, and terahertz spectroscopy. You can see we cover almost all areas of frontier physics. The remaining we are actively pursuing to hire. One of the main goals is to expose the undergraduate students to all frontier areas of science as we train them to take research as a career. Now, a brief word about science education. We have a very solid core course in our master's program, covering all fundamental foundational topics: classical mechanics, mathematical methods, electromagnetism, quantum mechanics, nuclear physics, electronics. We have advanced courses 27. These are given as electives on general relativity, quantum information, experimental techniques. The final year is a master's thesis. We have a rigorous student feedback system, both on the teacher and the course. The feedback to teacher is counted for career progression. Apart from giving major in physics, we also give minor in physics to out-of-school students from chemistry, biology, and mathematics. What we are really proud about is our laboratory courses. We have very state-of-the-art 14 laboratory courses with 65 basic experiments distributed over 6 semesters, and 15 open-ended advanced experiments for 7th and 8th semester. One of the mandate of NISER DPR is to inculcate experimental capabilities in the students, and that's how we design them. You can see some of the photos here, including the interference pattern on the top left-hand side. We have a very nice computational physics lab to cater to the advanced computational course, physics course, which is now quite integral for every field. Now, with this background, our students have brought laurels. Here are some selected achievements. We usually top in the NET. We received the Sama Prasad Mukherjee Fellowship, and our students, when they graduate and take up PhD positions outside, and then when they do the teaching assistantship, they excel. Here is one example of Siddharth Satpathy being awarded the Best Graduate Student Teaching Award in Carnegie Mellon University. This is a snapshot from its website. Our UG program leads to publications by students. The one on the left-hand side has come from the advanced open-ended laboratory course. And then from the summer programs and from the master's thesis, it usually leads to publications. Here are just 2 examples. And hence they are very well placed all across India and abroad. Now coming to the research facilities in physics, again, I will not go through the details of specification of the instrument. This is just to give you a flavor. All details are in the website, including the contact person's email address, and you are most welcome to visit us. We have low temperature systems, sputtering units, thin film deposition systems, diffractometers, FESEM. We have the CVD, reactive ion etching, the photoluminescence measurements. We have the particle properties measurement system, high performance computing, the nonlinear optics labs, and the atomic physics labs. All these research facilities with generous funding from DAE had led to quality publications, which in the current stage, the department comes out to be around 275 papers, which are being nicely cited with time. The faculties have also got recognitions from within country and outside. Here is just a snapshot of it. The students have also brought us recognition. The PhD students, best outstanding doctoral student thesis awards. The first PhD student from NISER has got the INSA Young Scientist Award last year and is a faculty at IISER Berhampur. Here is just a snapshot of the placement of the students. They have got prestigious fellowships like Humboldt and CERN Fellow. And this is just some sort of selected list of where our PhD students are going. You saw where our master's students have gone. Now coming to science outreach, the flagship is the telescope sessions. We have an 11-inch and an 8-inch telescope, and we have a very nice Jutni sky. We try to figure out what is there in this universe, take photographs of the moon, the Saturn, including the International Space Station, which passed by NISER. Then we have students coming in for evening sessions. We have about, I think, 25 to 36-inch telescopes. Students from neighboring school, we bring them and join their excitement of picking at the clean sky and finding out how the universe is and where is our position. The students all and the faculties engage in open day and dark matter day. In the open day, we design novel experiments to explain key physics concepts. One on the top right is showing how non-Newtonian fluids work. It is really exciting time when you see all these college and school students coming and understanding concepts of physics. Students come up with magazines. Of course, the photos which we take, telescopes form integral part of it. We also organize workshops to handle data of national facilities like GMRT. We have joined the International Particle Physics Outreach Group so that school and college students have hands-on experience of LHC data through masterclass program. Joining hands with Indian Physics Association, we tried to have discussion with PhD students on career opportunities, scientific writing, and public speaking. We have a vibrant research program. COVID last 2 years sort of decreased it, but we will again follow up. These are some of the colleagues who visited, and there were many more. So I think on behalf of Director NISER, Professor Panda, and all faculties, we invite you to this beautiful campus and place on record really the support, generous support from DAE helping build up these facilities. With this, the remaining 15 minutes, I'll focus on two topics, which is related to experimental high-energy nuclear physics. And these are based on two PRLs which came out last year. The first topic deals with phase diagram of strong interactions. This is based on this publication. What you see on the left-hand side is the phase diagram of water. Pressure is plotted as a function of temperature, and we all know there are three distinct phases of water: solid, liquid, and vapor. A more closer look tells us there are 15 kinds of different phase structure. This is one of the most widely studied and precisely known phase diagrams in science. Underlying interaction is electromagnetism. We ask the question, what is the phase diagram of matter which undertakes strong interactions? These are matters which we all are made up of, the quarks and gluons, the fundamental constituents of any visible matter that you see. Long back in 1975, 2021 Nobel laureate told, if you plot the density, baryon density, as a function of temperature, you should see two phases. The first phase, is where these fundamental constituents, quarks and gluons, are confined inside particles like protons, neutrons, or pions called hadrons. In phase 2, they are free. So this is the phase diagram he conjectured. Things have moved on, and what you see on the left-hand side is the current understanding of the phase diagram of QCD. QCD stands for quantum chromodynamics. Chromo means color. So dynamics of color charge carrying particles, the quarks and gluons. This phase diagram in the y-axis is temperature, x-axis is baryonic chemical potential. This is related to the baryon density, and you can see it's very rich. Now, how do we access this experimentally? If you collide heavy ions, heavy nuclei at very high energies, then you can change the temperature and the baryonic chemical potential, the x and y axis of the phase diagram. You can see on the right hand side that the temperature increases with collision energy of heavy ions and baryonic chemical potential decreases. So changing the colliding energy gives access to this phase diagram. What we are interested is in this white point which you see on the left hand side plot, the critical point. Why? If we discover this critical point on the phase diagram, then the phase diagram becomes a reality. On the right hand side is first order phase transition, just like water to ice. On the left hand side is the crossover. On top of it is the free state of quarks and gluons. Below it is confined state of quark and gluons, the hadrons, protons, neutrons, pions. So this one point would lead to the phase diagram becoming reality, and that's the excitement. Now, we have contributed quite a bit in getting a program in place to have this phase diagram studied. It includes asking the accelerator to operate at different colliding energies, although it was not meant for it, the relativistic heavy ion collider. We had to present the case to the community, which I did in 2009 at Quark Matter conference. And then we were asked to establish an observable so the detectors function and the accelerator can deliver. We were given a test beam data at 9.2 center of mass, GeV center of mass energy, 5 hours of data, 3,000 good events we collected and demonstrated all these aspects. You can see in the last line of the abstract we wrote, the results demonstrate the capability of the detector, although optimized at working at a different 200 GeV, a factor of 10 lower it can still operate, and is suitable for critical point search and making the phase diagram of QCD. This program was approved. This is the collaboration you see, and you can see in the middle the spokespersons, the deputy spokesperson. I was then the physics coordinator and then went on to be the deputy spokesperson. The first thing we did is to set the observable. We measured event by event number of protons minus number of antiprotons plotted in the x-axis. Y-axis on the right-hand side plot is number of events. The moments of this distribution, by moments, the first moment is mean, second moment is variance, third moment is skewness, fourth is kurtosis. We measure the moments of these distributions, and theory tells us these are related to correlation lengths of the system. If we hit the critical point, the correlation lengths become large. Ideally, for a static system, long-lived, it could be infinite, but we have finite size and time effects, so it takes large values. Why do we go to higher order moments? Because the correlation lengths power to which it depends is also higher, so it's more sensitive. Product of the moments, as you can see on the left hand side, skewness times standard deviation or kurtosis times variance are related to ratios of susceptibilities which can be computed in QCD. So here is a direct connection between what experiment can measure and theory can calculate, and that will be breakthrough. That's what we did with the TIFR theory group. On the left hand side is a plot. On the left hand side of that plot is the experimental measures from the moments of multiplicity distribution. On the right hand side scale of this plot is what QCD calculation gives. The red points are data, the black points are theory. With certain caveats, you can see that there is good agreement. Established and observable. We also went on to tell what is the transition temperature. It's of the order of 170 MeV that time, and which is 10 to the power 12 Kelvin. What is the experimental signature given by theory for critical point? a non-monotonic variation of fourth order correlations as a function of collision energy. And that's what we are looking at, and we did the measurements. The measurements took 10 years, and the latest set was published in 2021 PRL, but we started this from 2010. The papers, the 3 PRLs have got 1,000 plus citations. On the left-hand side, you see the fourth order correlations showing a non-monotonic variation as a function of collision energy. How do you establish non-monotonic variation? You take derivatives and so it changes sign. The below plot shows that the derivatives did change sign. But it is with only 3.1 sigma. It's not 5 sigma. So statistical errors are large, and hence we could not conclude confirmedly that there is possibly a critical point. Here is the data in a different form. This is what we would have expected, but you can see the error bars are large, and this measurement led to the phase 2 of the program, and we have collected the data now. The green band says how the uncertainties would look when we finish analyzing this data, huge data set which we have collected last year, and we look forward to what nature gives. There is already excitement. Frank Wilczek, the Nobel laureate who worked on QCD, tells experimenters at Brookhaven have reported hints of such behavior. They are now analyzing a much bigger data set to nail it down or not. If all goes well, they will have demonstrated that deep ideas invented to understand problems in physical chemistry, thermal engineering continue to be useful far beyond their down-to-earth origins. So in summary, you see in textbook the phase diagram of water. We are working towards making the phase diagram of strong interactions a reality. If we manage to do that, perhaps it will one day find place in textbooks. The right-hand side is a snapshot from the NCERT book. Now the last 5 to 6 minutes on the second topic, fractional charge search, this is the PRL which we published with a PhD student. And let me first give you what are the exciting discoveries which are lined up and where we are. The Higgs boson, existence confirmed, 4th of July 2012. Gravitational waves, existence confirmed, September 2015. We still have not figured out the constituents of the dark matter, antimatter, proton decay, magnetic monopole. One of the topic is also fractionally charged particles. Why it's so interesting? Well, electron charge was known by Robert Millikan and Harvey Fletcher, who said that they electrons carry a charge of 1.6 10 to the power 19 coulombs. All of the charged particles that we see are integral multiples of the charge carried by electrons, except for the quark and gluons, which I just now talked, which are not seen in nature. They are confined inside hadrons like protons, neutrons, or pions. Their existence are only confirmed through jets, the dijets or the trijets. So the basic question is, whatever we see in nature, why it has integral multiples of charge carried by electrons? What is the natural law for this simplicity? There is nothing preventing fractional charge particles which carry a fraction of the charge carried by electrons. So hence the search, if we find it, it would tell us about, it has consequences of understanding confinement and many other aspects. So how do people search? There are many experiments which try to look for it. The phase space is mass of the particle and the fraction of charge of electron it carries in the x-axis. You can see the aberration experiment. Central is what we looked at and in the PRL. So the detectors, the experiment was an underground based experiment, 713 meter. The detectors were semiconductor germanium and silicon crystals of 7.6 diameter, put in towers, put inside a cryogenic system. The principle is very interesting. When a particle comes and hits this semiconductor detector, the nuclei recoil. As a result of this lattice vibration, you generate heat. Now, if you are having a sensor such as a superconducting tungsten transition age sensor, which is operated at its critical temperature. This heat will change, being a change in resistance. Then you have an electrothermal feedback, which returns this transition age sensors to its nominal operating resistance. And the deposited energy is as a result of this Joule heating, and that is what is detected. These are operated in cryogenic conditions, and we try to use this to detect this fractional charge particle with cosmic origins. There could be different origins. We tried to figure out the intensity. We need the numerator, the number, and the denominators are acceptance, detector efficiency, and lifetime. We soon realized that usually in our field, in nuclear physics or high energy physics, we obtain the efficiencies also from a rigorous simulations, GEANT-based simulations. And we found that these particles are not described in GEANT. Although the energy loss of charged particles are well understood using Bethe block formulation. So the first challenge was to implement this in the GEANT framework, which we did, and now it's publicly available for anybody to use. Once we have that, we were able to put upper limits on the intensity on the y-axis of the fractional charge carriers, and on the x-axis is the fraction of the electron charge the particle carries. If you concentrate on the left plot, the black line, everything above is ruled out. A particular fractional charge particle with that intensity is ruled out, doesn't exist. So this was a very, very detailed, most stringent limit till date on lightly ionizing or fractionally charged particles. We realize we need more sensitive detectors. That's what we are working on. There is unique possibility of setting up such experiments in India. We are exploring them. In fact, we are collaborating with NPD and TPD to set up experiments also in reactors to look for axions and neutrino-based experiment. Quantization of electric charge is still one of the most fundamental of nature's puzzle. So I think my time is just up, and let me thank you for your attention and giving me this opportunity. Again, very sorry I could not be there offline.
Yeah. Thank you, Vedanga. Remarkable talk. Sort of 59 slides in 30 minutes. Let's see if there are questions, either online or from the physical audience.
Okay. First of all, I want to thank you for the excellent presentation, which could be easily appreciated even by non-specialists like me. And you gave a real flavor of the excellent research and facilities at NISER and physical sciences. We wish you all the best. I have one general observation and one comment. One is that I was very happy to see the mention of quantum information science in your presentation. And I believe now that I'm interacting with several CIs across the DAE, and also even discussions in our own planning and monitoring board, that the quantum information technology is going to be a topic of very great impact and relevance for the country, and that the government is also putting a lot of emphasis. It is nice to find that this is finding a mention in programs of BARC, NISER, HRI, IMSC, many others. I feel that consequent to this meeting, there's been a discussion in a few days that we should have forthcoming meetings on specific topics between experts. There could be a meeting on quantum information science among the specialists and all the CIs. Can help in paving the way forward for making a very national contribution. This is first observation, and your reaction I will listen. Second is regarding more of my own curiosity. You also mentioned about the terahertz spectroscopy, a topic in which I have been always fascinated. Do you know what exactly is going on at NISER on terahertz spectroscopy? Have you set up a system or developed a system of your own? Or is it that using terahertz spectroscopy, you are conducting research on certain compounds? So these are 2 points.
Thank you. Very nice points. And we are at NISER also excited about both these aspects. The quantum information, on the experimental side, Professor Ashok Mahapatra is the person who is leading that effort. He is also collaborating with other national forums. So I will tell him to be in contact with you. And on the theoretical side, a very experienced person is going to join us in May and has done extensive work on quantum information. On terahertz spectroscopy, we have got an excellent experimentalist, Dr. Sovam Pal, who joined few months back, and he's setting up himself a terahertz spectroscopy facility here. And I will again request him to be in touch with you. He can share with you the details, how he's setting up. The laser system is already in place, and they are working on to see that they could see this terahertz effect.
Okay, so thank you very much for the clarifications. I will conclude by saying that the two topics mentioned in your presentation, terahertz spectroscopy and also the transition age sensor which you mentioned, transition age sensor. Both of these are having some national strategic applications with regard to nuclear materials. So I would be very happy to discuss with you at some time. I think the colleagues from IGCAR have joined online. There is work going on there also on transition age sensor for a similar reason. So we will get back and discuss in time. Thank you.
Thank you very much.
Any other questions from the physical audience?
Yes.
Yeah, there is an online question after this.
Thank you, sir, for that very interesting talk. I just wanted to ask regarding the topic on fractionally charged particles. So I briefly worked on something which is called mini charged particles, which have charges which are 1,000th of the electron charge. So I'm curious about how it's related to these FCPs, the mini charged particles and the fractionally charged. And also another point, I believe Dirac showed that if you have magnetic monopoles, Dirac monopoles, then electric charge must be quantized. So how do we, and we haven't found any magnetic monopoles yet. So what is the relation there?
Yeah, so thanks. You are interested in this. I would refer you to a review article by Martin Pearl in annual reviews of nuclear physics. Okay, and if you drop me an email, I can also share with you. This has the whole gamut of fractional charge particles, which are a hot topic in condensed matter physics, and we can discuss that there. And as you yourself said, these fractional charge particles are linked to many, many different kinds of physics topics: confinement, Dirac's theory, monopole. So it's an interesting topic to look for.
Okay. Anyone else from the physical audience here? Otherwise, we move to an online question.
Hello, can you hear me?
Yeah.
Please go ahead.
Yeah, this is K. Mahata from BRC. Again, my question is also related to the fractional charge only. We know that quarks are having a fractional charge, but they are confined. So when in your experiment you are looking for some candidate, can you say what are the candidates you are looking for?
This could have cosmic origin. It could have also be origin from accelerators, common interactions.
Something other than quarks, or?
Yeah, other than quarks, which are confined inside hadrons. We are not looking for those quarks.
Okay, so there means like some new type of particles, you mean, they are unknown.
Possible. And again, I would refer you to this review article by Martin Pearl, and that has much more details of this exciting field.
Okay, thank you.
Any other online questions? No? Any other physical questions? Okay, so let's thank Vedant for a lovely talk. Thank you. 2 minutes beyond our
Very good morning to all of you, those who are present in the auditorium as well as online. So I shall present some glimpses of basic and applied research which are carried out in the radiochemistry and isotope program of BARC. The research carried out in radioisotope and radiochemistry program of BARC is really very vast. You can understand from the fact that here the positrons, which is the tiny subatomic particles, are used to study the characteristics of the liquids in the nano confinement. And at the same time, another group of scientists working in this group are trying to utilize or trying to develop some agents based on positron which can be used for the detection of different types of the diseases in human body, particularly for cancer. In this group, the radioisotopes are used for troubleshooting of various industrial problems, and at the same time, research is going on. Use the energy which is coming out from the radiation for industrial, pollution mitigation as well as material processing. So this group, there are 8 facilities, actually 7 division and 1 independent sections, and we have received one mail from Professor Mohanty. We should talk about 15 minutes about the facilities and research program, 15 minutes talk about 1 or 2 current or broader topics, and 5 minutes for discussion. So following that advice, so I have chosen a few topics in consultation with the seniors, and the topics which I am going to cover: nuclear chemistry, positron annihilation spectroscopy, actinide chemistry, secondary ionization mass spectrometry, radiation technology for material processing, radio pressure applications in industry, and radiopharmaceutical chemistry with slightly more details, which is the subject of my specialization. So research in actinide chemistries are usually carried out to understand the mechanism of nuclear reactions and nuclear fissions, and also for radiochemical separation and decay studies of heavy actinides. This nuclear chemistry research is based mainly on our reactor Dhruva, as well as heavy ion accelerator facilities of India, which are available at BRC TIFR Neutron facility. A similar facility is available at the New Delhi, and also by using the variable energy cyclotron at VECC Kolkata. So one of the very recent studies that my colleagues of nuclear radiochemistry division has carried out is studying the fission fragment pattern of reaction, that is 144 samarium bombarded with 32 sulfur, and it is expected that it should be undergo asymmetric fission because it forms 176 osmium, but they have noticed there is some asymmetric component in it, and the heavy fragment of the neutron number is around 56, the light fragment proton number is around 34 to 36. So they have tried to calculate it theoretically, and they have shown that it is quite consistent with that. In another nuclear reaction, which is they have bombarded with 93 niobium with 12C, and they have seen that the nitrogen formation is whatever is expected, 15 nitrogen formation is more, which they can explain theoretically based on the shell model. The work is also going on study for developing heavy actinide selective agents by homology imprinting. So here, colleagues have developed or synthesized some ligands which they have polymerized and subsequently used it for complexation with cerium-4 because its behavior is very similar to that of the berkelium-4, and they have utilized this ligand for studying the short-lived berkelium-4. Efforts are also on for development of methodologies for non-destructive assay of mixed uranium-plutonium samples based on the gamma ray spectrometry, calorimetry, and neutron multiplicity counting. And based on the studies, they have come out on a contour diagram. You see, in the left-hand side, it is pure 235 uranium. On the right-hand side, it is 238 uranium. So any mixture you take, and from this diagram you can tell. So in this region, you cannot determine any one of these, 235 uranium and 238 uranium. Here you can determine both. In this region, you can determine only 235 uranium and so on. Coming to the next topic, positron annihilation spectroscopy. This positron annihilation spectroscopy is utilized for a variety of studies like dependent defects in thin films or microsphere, defect engineering in oxides or catalysis, defects and radiation-induced damages in alloys, photon-induced positron annihilation for fatigue and aging studies, and at the same time for free volume and physiochemical properties determination for polymer nanocomposites, liquid and nano confinements, and also for studying the characteristics of porous materials like metal organic framework. I'll be briefly mentioning about one or two of these. As I mentioned, this positron annihilation spectroscopy has been utilized for studying the pore architecture of metal organic frameworks, and the orthopositronium ions are used, and it can be found out from the lifetime of the positron if there is interconnectivity. And these pore architecture property relationships are possible because there is no artifact in pore estimation. Similarly, this has been utilized for finding out the defect or accelerated aging, where the depth-dependent defect distribution was determined using monoenergetic beams, and atomic level defect identification was also carried out at different depths. Another interesting studies which are carried out by the colleagues of the radiochemistry division is that we have studied the behavior of the liquid and the nano confinement. As you can see, this is an ethanol water mixture, which is expected to be miscible. They have seen that at a certain point, the positron lifetime increases, which can only be explained if there is some phase separation in the nano confinement. Coming to the research on actinide chemistry and separation. So actinide chemistry research, they study the complexation, or they study the cation-cation interaction. They develop different types of the exotic ligands for the separation of the actinides from the lanthanides, as well as the different actinides. Also, the behavior of the actinides in the environment, and these are done usually by using a series of experiments using different types of facilities like UV visible, fluorescence, XAPS, single crystal XRD, calorimetry, electrochemistry, computational chemistry, etc. So my colleagues who are working in the actinide chemistry section have studied the cation-cation interaction of neptunium-5 and uranium-6, and have seen that this interaction is stronger in room temperature ionic liquid compared to the aqueous medium. And from there, we're able to derive useful information to understand the complicated distribution behavior of neptunium in the nuclear fuel cycle. They have also tried to develop different glycomide functionalized ligands, and they have shown that if it can be used in a preformed geometry, the extraction behavior is much superior compared to that when they are used separately, or that is a single ligand is used. And they have tried to understand this behavior and also try to explain this behavior using UV visible absorption, luminescence, XAPS, solution calorimetry, and computational studies. They have developed some nitrogen donor ligand, that is actually this triazolyl pyridine, which they have utilized for the separation of the actinide and lanthanides, and they have shown that this ligand can specifically extract americium-3 in presence of the europium-3, and they have explained this behavior by DFT calculation, considering the structure determined from various spectroscopic and XRD techniques. Detailed studies has been carried out to understand actinide sorption and speciation into the clear materials using the clays from different places of India as well as from abroad, and they have come to the conclusion that minor iron phase is predominantly responsible for enhanced neptunium sorption in the natural sediments. Researchers also carried out to use the hollow fiber liquid membrane for separation of the actinides, and they are successful in recovery of plutonium from the laboratory waste solution. And also this ligand what they have synthesized is very specific for cerium, and they are able to separate 100 millicurie of cerium-137 from the high-level liquid waste. They are also working on the solid phase extraction that is extraction chromatography. And what they have done is that they have developed different types of the resins which are impregnated or grafted with different types of the ligands, which are specific for actinides. And these room temperature ionic liquid resins, which are excellent for different environmental samples. And they have utilized it for the separation of different types of the lanthanides and actinides. Coming to another facility of our group, that is secondary ion mass spectrometry. This is an excellent system for studying the surface properties, for studying the depth profiling, as well as determining the isotopic compositions. And one of the most important thing is that we can determine the hydrogen, which is otherwise very difficult by other surface analyzers. So here is the, you can say, one animation. So you see that the primary ion, which is generated from the cesium source, or maybe duoplasmatone source, and that falls on the surface of the material which is being analyzed. So from a very small portion, the primary ion generates the secondary ions, which are usually maybe neutral, maybe metal ions, or maybe cluster ions. And then these secondary ions are separated in the magnetic sectors, and you can get the mass spectra or the imaging from which you can do a lot of different types of the studies. I'll just briefly mention some of the studies. Like you can study the irradiation effects on solids. Like they have studied the deuterium depth profile in ion irradiated recrystallized tungsten samples. It can be used for quantitative depth profiling of alloys for determining the composition at the different depths. It can be used for the corrosion studies. As you can see here, the study has been carried out to understand the surface of the steel when it is in virgin state and when this is treated with hydrochloric acid, sulfuric acid, and nitric acid. It can be studied for studying the hydride formation on zirconium oxides, which are very important for our reactor-based programs. Coming to the radiation technologies for material processing. So we can understand that the energy which are coming out from the high energy radiations, that is maybe the gamma radiation or the electron beam, they can deeply penetrate into the material and initiate the chemical reactions. And this can be utilized judiciously to exploit different types of, to bring different types of the changes in any materials at room temperatures. And this radiation technology is used to polymerize monomer even at the sub-zero temperature, cross-link or modify the polymers, generate oxidizing and reducing species in aqueous medium, kill pathogens in sewage slugs, and also induce coloration in hardest matrices like diamond. So I will just briefly explain some of these applications. So one of the very important application of this cross-link polymer is that it can be utilized for controlled drug delivery matrices. As you can see here, a monomer is taken with water and that has been dipped in a freezing mixture, that is dry ice and methanol minus 78 degree, but dropped inside the hexane, which does not freeze at minus 78 degrees Celsius. So what will happen is that these monomers will be there in the dry, in the ice, and then they have irradiated it, cross-link the polymer. So once the cross-linking is done, it has been brought to the room temperature. So the ice melted, and it has created two different types of the pores in this material. So one is the bigger pore from where ice has been melted, and other one is the cross-linked, the pores between the cross-linking. So this is utilized for the drug delivery. I'll explain briefly what we have done. So normally when you take a drug, it reaches a therapeutic window, and then slowly its concentration in the blood comes down and comes out of the therapeutic window. Again, you take another drug, so that again it goes to the therapeutic window. So what they have done is that they, after preparing this polymer, they have loaded the drug in it. And once they allow it to swell, what happens is that as these pores are big and not costly, the drug comes out very fast from here and it reaches the therapeutic window. And then subsequently, it comes out from these cross-linked pores and maintain it in the therapeutic window. So by maneuvering the amount of the drug and this pore size, you can have a very controlled drug delivery mechanism. When the radiation falls on polymer, or when it is irradiated in the electron beam, it undergoes several types of things, like it may undergo grafting, cross-linking, or degradation, depending on the amount of the radiation you are giving as well as on the nature of the polymer. So this is utilized for developing conducting polymers. So what is usually done is a polymer is taken, which is non-conductive, and it is filled with some filler, which is conductive. So you get a polymer composite, and then you irradiate it so that you get the conducting polymers. And this has been utilized for making different types of the sensors, as yesterday Dr. Hassan was also telling. So one application is that about of the Radiation Technology Development Division developed one sensor for acetone vapor. So this acetone vapor, it is very specific to the acetone, and it can be detected within a time frame of 28 nanoseconds. And it is very specific for acetone. Its response to other methanol, ethanol, or any other thing is less than 10% of that. So according to the colleagues of the Radiation Technology Development Division, they can develop, or they're trying to develop different types of the polymer, which will be very specific to a particular type of the chemical. Another very important application is that of grafting. So, you know, in villages, it's the farmers very routinely they put these shions, that is good food-bearing trees, the good stalks, so that we get the best of both the ends. Similarly here, the functional grafted polymer are grafted on the base polymer, which are actually cheaper, much rugged, and this they have utilized for the two-way environmental pollution mitigation. Nowadays, we use a lot of non-stick cookwares, which are actually based on Teflons, and the Teflons is almost never degraded in the environment. So what is done, this Teflon has been taken, and some hydrophilic moieties has been grafted here. And this grafted Teflon has been used for taking out the effluents, the particularly where there are industrial dyes. So it absorbs the dyes, and so that they are able to use one of the pollutant, which is otherwise have no use, to remove another pollutant from the environment. Another important application of the radiation processing is the sewage hydrogenation, because these radiations are excellent for killing the DNS, cell membranes, enzymes, etc., both by the direct and indirect effect. And this converts the sludge into the class A biosolid, as you can see here. This is one of the running plants at the Ahmedabad Municipal Corporation, which has been started in collaboration with BARC and inaugurated in February 2019. It uses 300 kilocuri of the cobalt source and daily processes around 100 ton of sewage and convert it into the biogold, which is used as a manure. Another important application is the electron beam, is the processing of the diamonds. So in diamond industry, diamonds are parts and very small pieces are generated, which have almost no value. So you can irradiate this, the electron beam, and depending upon the impurity trapped here, the diamond get their color, and these color diamonds have a comparatively higher value. As you can see here, this is almost no color, and after some color is generated after the electron beam irradiation. Briefly, I'll touch upon the radio tracer application before I go to the last topic. Radio tracers are the open sources of radioisotopes, and it mimics an inactive compound without perturbing the system. So, if you inject this radio tracer in a very bulky system, and if you follow its pathway, you can have a lot of information based on tracking its pathway as well as determining its quantity. And it is an extremely sensitive process. You can study up to 10⁻⁻18 molar, and it has a lot of applications, some of which I have listed here, like leak detection in industrial system, blockage detection in buried pipelines, detection of underground pipeline leakages, flow rate measurements in pipelines, canals, and mountainous rivers, sediment transport investigation in ports, effluent dispersion in water bodies, fixing time and homogeneity measurements, measurements of pollution and wear rates, etc. I'll just briefly mention two of the applications. So one is a leak detection in heat exchangers. So these are the heat exchangers, and it is very difficult to find out where is the leakage, but it can very easily be done by using the radio tracer. You can find out where this radio tracer is coming out, and this point you can And downtime usually normally 15 to 20 days if it is not detected by this radiotracer method, and it saves a lot of revenues for that plant. Another important application is the detection of the leakages in the underground buried pipelines. So very long pipelines are available in our country for the supply of oils, water, etc. And it is very difficult to find out otherwise if there is a leakage. So you can inject some suitable radio tracer and detect it from above the ground, from where you can find out from where is the leakage. Now coming to the last topic of my presentation, which I'll be discussing in slightly more details, is the radiopharmaceuticals. So radiopharmaceuticals, as the very name suggests, is the radioactive pharmaceuticals that are a special class of radioisotope level formulations which are suitable for administration in patients for either diagnosis or therapy. So it can be of two types. One is diagnostic radiopharmaceuticals, another one is therapeutic radiopharmaceuticals. So diagnostic radiopharmaceuticals are the radio level molecules which are designed to provide images of intended specific organ or disease site, while the therapeutic radiopharmaceuticals are the molecules which are designed to deliver therapeutic doses of ionizing radiation to specific disease sites with an intention to cure the disease. So we are all very familiar with the X-rays. So in X-rays, what happens is that there is an X-ray source. X-ray comes out from the source, passes through the patient's body, and it is detected. And we get this kind of the X-ray films from where the physicians can find out information about the malfunction of the human body. But in case of the radiopharmaceutical, there is no source. The radioactive preparation is directly injected in the patient's body. So patient is allowed to rest for some time so that it gets proper distribution. And now the patient himself or herself is the source. So the radiation coming out from the patient's body is detected by the detector, from where we can have a lot of meaningful informations. As yesterday, Dr. Hema has shown the structure of the radiopharmaceutical, it has a carrier moiety, which is usually a peptide, maybe antibody, hormones, or biomolecules, which takes this preparation to the target of interest. And the target may be the tumor, receptors, antigens, maybe cells, maybe some biochemical process. And this carrier is attached with a radionuclide. This radionuclide, if it is diagnostic in nature, that is when it decays by the gamma emission or by the positron emission, it is called diagnostic radiopharmaceutical. It is therapeutic in nature, that is, it depends by particular emitters, alpha or beta, you can call it as a therapeutic radiopharmaceuticals. So one question will definitely come to your mind that we have so many excellent detection techniques, imaging techniques like ultrasound sonography, computed tomography, magnetic resonance imaging or MRI. So why we need to inject radioactive preparation in patient's body, image or get an image? The reason is all the methods what I have told except the nuclear medicine imaging process only give you the anatomical imaging. It does not give functional imaging, because they are only taking a picture from the outside. They are not taking in the physiological function or the biochemical process of the human body. So that is the reason nuclear medicine imaging procedure, which is a very complementary method, with all the other contemporary imaging techniques like X-ray, USG, CT, or MRI. And this is any body function you take, yes, diagnostic radiopharmaceuticals are available to detect the disease. It is not only for cancer, it's for cardiology, neurology, even in psychiatry, it is available. Radiopharmaceuticals are available, but I'm not going to the details of that. So it is a bit complicated process to the radiopharmaceutical from bench to bed, and it's a very lengthy process also. First, you have to understand the biochemical process or the pathology of the disease, what you want to target. And you have to find out the carrier moiety, which is specific towards that carrier moiety, towards the disease. Now you select the radionuclide based on your application, if it is diagnostic, therapeutic, or etc. You have to synthesize this carrier molecule or maybe modify the carrier molecule, and then you have to do the radio labeling, that is attach this radionuclide to the carrier moiety, do the quality control procedure. You have to do the in vitro evaluation, that is in the cancer cells, as yesterday Dr. Prasanna was telling, then animal experimentation, and finally you have to ask for regulatory approval. And once you get the regulatory approval, you can go for clinical utilization. So I will briefly mention about one or two applications of these radiopharmaceuticals where we have made meaningful contributions. So one is peptide receptor radionuclide therapy. So many cancers have expressed different types of the receptors. And some of the peptides are very specific to the receptors. So if you can radio label a peptide, you can have a so-called magic bullet. That is, when you will inject in the human body, it will specifically go to the tumor. Now, one of the very important agent which has come out in the last 15 to 20 years is 177 lutetium level dotatate. So this is the TET moiety, that is an peptide containing 8 amino acids, and we have coupled it with a bifunctional chelator to facilitate radio labeling called DOTA. 15 years back, when we started working with this, the situation in our country is that our people have to go to Europe, maybe the Germany or maybe Switzerland, to get this treatment. And one injection was costing 4 lakh rupees. That time I'm telling around 2005 or 2006. And usually patients need to take 3 to 4 injections. So total cost was 20 lakh, which was almost affordable to our countrymen. So what we have done is we have done extensive studies using the medium and low specific activity 177 lutetium, which you can produce using our Dhruva reactor, standardize its methodology, and it is not only the research and development, it is deployment also. We have visited at least 15 different hospitals, major hospitals of India, and started this procedure. And today, this is utilized actually for the different types of the neuroendocrine cancer treatment. And today, it is very heartening to note that it has started supplying this agent, and at least 60 nuclear medicine centers of our country is using this agent, and the cost has come down to around 50 to 60,000 rupees per dose. So which was in 2006, 4 lakh rupees. Now it is available in only 50,000 rupees in India. So we have definitely have the facility of synthesizing this peptide by using the solid phase peptide synthesis. As yesterday, Dr. Hema was also telling about the synthesis of 2 other peptides, PSMA11 and PSMA617, by the colleagues of Bioorganic Division of BARC. So we synthesize different types of the peptides, and now we have started a program for modification of the peptides to extend its half-life as well as to improve the pharmacokinetic behavior of these peptides, which can be done by a variety of methods. So anybody having expertise and willing to collaborate with us is very welcome to develop the new peptides for human application, and we'll be happy to radio label it and study it, or the clinical study we have given here. Another very important thing what we have studied is to study the peptide nucleic acids, which are almost like, this is a DNA structure. So if you remove the sugar phosphate base of this DNA and change it with N-amino ethyl glycine, you get the peptide nucleic acids. So what are their advantages? Advantage is that they looks like DNA or RNA, so they can easily target different cancers, but our body does not recognize them, our body enzyme does not recognize them, so they don't undergo hydrolysis. They are very rare to the enzymatic hydrolysis. So we are in the process of synthesizing different types of the PNAs or different types of receptors which are overexpressed in human body, and we'll try to radio label this and translate it to the clinical stage. Coming to another application is antibody. So all of you are aware about the antibody, that it is an immunoglobulin large Y-shaped molecule, which is used by the immune system to identify and neutralize foreign objects such as bacteria or viruses in the body. So we are extensively working for developing radio-labeled antibodies, and very recently, before that, just let me explain this. So what happens is that antibody, we have labeled with the radioisotope, and as these antigens are overexpressed in the cancer cell, so due to this antigen antibody very specific nature of the reaction, it goes to the cancer cells carrying the radionuclide with it. So as I mentioned, the last 5 years or so, we are extensively working on the radio-labeled antibodies, and one of the radio-labeled antibody that is called lutetium-labeled trastuzumab, its use has been approved by the DAE RPC, Radiopharmaceutical Committee, which is the authority in a country allow injection or administration of the radiopharmaceutical in the human body, administered in human patient. As you can see, the initial clinical studies in collaboration with Tata Memorial Hospital in a breast cancer patient, which is getting accumulated in the breast lesions. So we will be starting the full-fledged clinical trial of this, and my colleagues are also working with another antibody called lutetium-labeled pertuzumab for the same applications. But my intention is not to think that we are starting the clinical studies, but what we are doing next. We are trying to develop the antibody-drug conjugates. Radio-level antibody-drug conjugates. Antibody-drug conjugate is a very exciting field of research. all of us know that the chemotherapy is the first line of treatment for the cancer patients. But the problem with the chemotherapy is that these are not specific. On the other hand, antibodies are very specific because they have a very specific mechanism of getting attached to the cancer cells. So all over the world, even multinational companies are trying to develop suitable antibody drug conjugates, which takes the best of both the world, that is best of chemotherapy and antibodies. And till date, US FDA has approved 12 antibody drug conjugates. And this field has recently get a lot of momentum in 2020 and 2021. Four antibody drug conjugates, which are commonly known as ADC, have been approved by US FDA for different types of the application. So we want to go one step further. We are trying to attach a radioligand, radioisotope with these antibody drug conjugates. And in the next 10 years or so, we'll try to take this radioligand drug conjugate in the for clinical studies. The last thing which I'm going to share with you is the radionuclide therapy of liver cancers. So presently, two agents are available, which are mostly used. One is called SARS spheres, which is 90 yttrium level resin microsphere, and the other one is Therasphere, that is 90 yttrium level glass microsphere. And this procedure is called transarterial radioembolization. As you can see, the patient is injected with the preparation through the a catheter. And it actually blocks the liver. It cuts down the blood supply of the liver, that is called embolization, and at the same time, it gives the radiation as there are radioactive particles. But the problem of this agent is that this Therasphere is used in India, but it is imported, and cost of one injection is around 7 lakh rupees. That is in our Tata Memorial Hospital, and if you go to the private hospital, it is around 10 to 12 lakh rupees, so it is almost non-affordable. Very recently, in collaboration with our materials group of BARC, we have developed glass microspheres, which is having yttrium in it, and our chairman very fondly calls it spheres. And we started the clinical trial in collaboration with the Tata Memorial Hospital. Its use has already been approved by the DIRPC, and we have done 8 patients. So we are actually in the process of developing other materials with a similar type of the behavior. So we'll be very happy if someone has the expertise and wants to collaborate with us who can develop this biocompatible material which can undergo the irradiation in the reactor and which contains the yttrium or holmium. Presently, we are trying to work with the holmium, which is another isotope which can be utilized for the liver cancer. We're very happy to collaborate with this. So I am in my last slide where I just want to show you how this applied research can help in sustainable development. So these are the list of 9 products. So last 5 years, we have brought 23 products which have been now in patient domain and regularly supplied to the patient through our sister concern, Board of Radiation Isotope Technologies. So here I have just chosen 9 of them, and you can see the effect of our research. This is the input price, and this is the price from which we supply it to the patient. So this is a direct application, how this applied research can be utilized for the societal benefits. So with this, I'll complete my presentation, but before that, I need to acknowledge several people. I sincerely acknowledge Professor S. Kannan, Director, Radiochemistry and Isotope Group, who has kindly helped me to sort out some of these topics which I have presented today from the vast ocean of the things which my colleagues are doing in Radiochemistry and Isotope Group. Professor Y.K. Bharadwaj, Head Radiation Technology Development Division. Professor H.A. Pont, Isotope and Radiation Applications Division. Professor P.K. Mohapatra, Head Radiochemistry Division. My dear colleagues, Dr. Jason PG and his team from Fuel Chemistry Division, Dr. Kathi Sudarshan, Dr. Rahul Tripathi, Dr. Ronasis Bhattacharya from Radiochemistry Division for giving the slides and most importantly, giving their valuable time to make me understand the subject, because it's very difficult to understand or really don't work. And all my colleagues of the Radiochemistry and Isotope Group, with due apologies because very important work I could not present due to the limited time. And I sincerely acknowledge Honorable Vice Chancellor of HBI, Professor Basudev Rao, Professor A.K. Tadi, Director, Chemistry Group, Professor P.D. Nayak, Dean HBNI, and Professor D.K. Maiti, Associate Dean HBNI, not only for organizing this symposium, but also to call us, to make us understand what we should present in this meeting. And finally, thank you all for your kind attention.
Thank you.
Hope, sir, I have not taken extra time.
Thank you very much. We are slightly out of time. I don't see any raised hands. Are there any raised hands? Nothing on that. So maybe from the audience, if anyone, please.
Yeah. First of all, thank you very much for very nice and informative talk.
Thank you, sir.
So I have one question that you, in the first slide, you had told that there was some samarium is irradiated with sulfur. So do you know what is the charge state of the sulfur beam? And the energy of the sulfur beam?
Sir, as I'm not very familiar with the subject, but I think it's quite high. I think Dr. Kathi can answer that question.
Pardon? 140 MeV, what was the charge state of sulfur? Okay, okay.
I don't remember exactly, but it was charge state. I don't really remember.
Okay, thank you.
But it was about 140 MeV of the beam energy.
Okay, thank you.
Anyone else? No? Someone there? Ah.
Tapas, thanks for the nice presentation. The Bhavasphere you have told, no? What is the specialty of these silica spheres? Because we also prepare some, say, nanoporous silica spheres, which is something like 5 to 10 micron.
Yeah.
So what is the size and what is the specialty? Is it porous or something? Can we collaborate on this direction? Yeah.
Yeah, it is around 20 to 30 micron size. And it has a very specific composition, which I can share with you.
Okay.
But it should be homogeneous and it should be circular. It should be spherical. Otherwise, it will injure the arteries. And the composition is very specific with some yttrium doped in it. But now we are working on agents where holmium will be doped because it's much easy to produce holmium in the reactor. Its cross section is much higher compared to that yttrium. But that work is at the preliminary stage.
But is 20 micron is very essential or it can be less than that?
No, it should be somewhere between 20 to 30 micron.
Okay, thank you.
Yeah, that is the Bhabha sphere that is being prepared. Now the spheres are prepared in an inactive lab.
Yeah.
Well, you label it with a radioactive nuclide. So how the nuclide is doped into the Bhabha sphere? Is it like sorbed into it once they are synthesized, or how does the process go?
Okay, Vinita, thanks for the question. Actually, it is not. Actually, the yttrium in inactive state is already there in the glass matrix. So when the glass matrix or glass microsphere is prepared in the inactive lab, yttrium is doped into it. And this glass microsphere is directly irradiated in the reactor.
All right. Okay.
So it becomes radioactive.
Okay. So that's post-synthesis irradiation.
It is post-synthesis irradiation. The ready-made particles we get from the materials group, and we directly irradiate it in the reactor and do the processing to make it suitable for human administration.
Oh, thank you so much.
Thank you, Vinita.
Anyone else? So let's thank him once again.
Thank you, sir.
Thank you. Thank you. Final talk of the session, Dr. Paul from RRCAT.
Hi, good morning, everybody. First of all, thank you, HBNI, for organizing such a nice event here to present our work as well as the opportunities that we can see. So I'll be discussing about the research opportunities in engineering sciences at RRCAT. So the presentation plan is, I'll be discussing about the major activities, then coming to the
Indus accelerator complex, and specifically I'll be talking about engineering beamline, because yesterday also BRC beamlines are discussed, and some of the beamlines will also be discussed by Dr. Majumdar, who is going to present the work tomorrow. I'll be touching upon the RF and microwave engineering that RRCAT is doing and what are the research opportunities. Power converters for electromagnets, MEMS, piezoelectric actuators, electron linac that RRCAT has and how the things are going on. Then coming down to the laser activities, and at the end I'll be focusing on laser additive manufacturing, which is my area of expertise, and I'll be trying to give us brief output and give a small dive so that we understand a lot of things about it. So if we talk of RRCAT has got two big programs, we all know that. One is particle accelerators, another is on laser program. When we talk about particle accelerators, we have Indus 1 with 450 MeV, Indus 2 with 2.5 GeV, we have electron linacs. Electron accelerator program is now coming up, and industrial and medical applications we are dealing with using particle accelerators. On the laser sides, a lot of development in the lasers, YAG lasers, fiber lasers, ND class lasers. CO2 laser work is also going on. Copper vapor lasers, semiconductor lasers, free electron lasers, industrial and biomedical application of these lasers. In this part also, the biomedical applications will be covered by Dr. Majumdar. So I'll be focusing on the industrial application of the lasers. So if you talk of all these programs, we can find out that there are many areas where there is opportunity for the research, specifically in RF and microwave, cryogenics, optics, power supplies, instrumentations and control, ultra high vacuum, and advanced manufacturing. So I'll be touching upon some of these topics in my presentation. So I'll start with Indus accelerator complex and engineering application beamline. You know that this is a very familiar PowerPoint. Normally, it is presented whenever we talk of Indus accelerator complex. So both Indus 1 and Indus 2 are working around the clock since February 2010. I'll not be, talking the deep detail of all this. So if you see the view of Indus 1 and Indus 2 storage ring, so again, Indus 1 is 19 meters, and then 172 meter is the Indus 2 tunnel perimeter. And again, it's a very challenging thing to have and put it on the place and also operating this round the clock, specifically when working with the systems, and a lot of challenges with indigenous system developed in-house. Indus beamline have got 7 beamline from high resolution VUV spectroscopy beamline, angle integrated photoelectron spectroscopy beamline, photophysics, angle resolved electroscopy, soft X-ray reflective beamline, infrared spectroscopy beamline, photoabsorption spectroscopy. Indus 2 have got 17, and out of this, I'll be focusing on beamline of for engineering applications, BL2, that is normally called in the RRCAT nomenclature. So this particular work, I acknowledge Dr. Sanjay Rai. He has done, I also written his email ID, so that if for any of the future correspondence, if you want to have some clarification, you can also directly write to him. So this is again X-ray diffraction in energy dispersive and angle dispersive mode. We do it here. The idea of engineering beamline is because the size of the samples can be large. For example, 500 millimeter diameter, and weight can be as high as 20 kgs. So it is a typical engineering application, you can use it. In angle dispersive mode, we can use power in the range of 5 to 25 keV, and energy dispersive it is 5 to 40 keV. And these things are basically used for residual stress measurement, microstructure degradation during service investigations, and also for the damage assessment, specifically, which is developed by Fatigue and Creek. So what can we do is, using these particular techniques, we can try to achieve best performance in the component. We can also try to work on the estimation of the safe life of the component, because now whenever we talk of, and also people talk of probabilistic design. So we can think on this and also try to understand the failure analysis if something fails, and we can investigate further using this engineering beamline. This is one of the recent application carried out at RRCAT by studying the roll-bonded zircaloy SS joint in the pressure tubes of PHWR. This is done in collaboration with the Reactor Engineering Division of BRC. So this is the piece, and they mounted on the things as it is without without any special preparations. And you see very nice residual stresses they could get And you see here, we have brownish mark here. And this zone is investigated how things are changing with the location and residual stress. This could be done without damaging the specimen. So that thing is done at BL02 at RRCAT. I come to the another topic, which is RF and microwave engineering. Acknowledgement to Dr. Akhilesh Jain. Email is already mentioned here. So here, a lot of equipments are available in our RF division, and we are specifically, they are vector network analysis, directional sensors, spectrum analyzers, digital oscilloscopes, power meters, radiation monitor. Also, they have very good software strength using microwave office, high frequency structure simulators, PCPI SCAT softwares, very nice test stands for the high power level at 325 megahertz and 500 megahertz and 650 megahertz. Low power to high power level protection components, and many things they are trying, and many things they are having, like RF power dividers and combiners, directional couplers, and digital question. Using these facility, whatever we have at RRCAT, and especially in RFSD, we can think of taking of research, especially if you want to have some circuit model for radial combiners, or you want to use estimate the performance of RF power drivers, direction couplers, by incorporating the electric resonators backed by the dielectric loading theories. And the research studies of the mechanism of the compensate phase and amplitude imbalance automatically in the solid state RF amplifiers are the potential area where people are trying to go ahead and working on these things. Not only the RF and microwave, also many other contemporary technologies, for example, thermal design of heat exchangers for solid state RF devices. So these are the areas where people are working, and there are opportunity for possible collaborations and taking this thing if it is of your interest. If I go to the power converters of the electromagnets in particle accelerators, again, acknowledgement to Dr. Mangesh Porge. Email is ID there. You can contact for the more details. Power converters for the electromagnet has got very nice strategies, and then we have DC to slow varying power converters, fast and power converters, pulse power converters, 1, 2, and 4 quadrant power converters, and special purpose power converters are developed at RRCAT. And the features of this particular power converters are they have very unique requirement for the accelerator programs. Tight performance specification, when talk about the precisions, very tight precisions are there. They have a precision sensing control. Reliability is tested because, again, you have to run the machine round the clock without less of the maintenance. You cannot afford to it, otherwise things may be different for it. GI has to be good, interaction and layout has to be maintenance-free operations. So many things they have tried and worked on, and especially focus on the varied power architectures and try to handle the stored energy. So almost 400 power converters built by the people, and they are working in the range of rating in the range of around 10 watts to 720 kilowatt, with the current rating 500 milliamperes to 800 amperes. So, and in the pulse mode, both can be possible. They can have high sinusoidal and the trapezoidal shape with the maximum current of 11 kiloamperes. They are also fast ramp. So this is the facility that we have as a power converter support. And what we're thinking further to take the step ahead to go for the study about the power converter reliabilities and how the topologies of fast ramp power converters with intermediate energy storage and grid power control can be managed, and how these things really can help in upcoming accelerator programs. Also talking of digital controllers for power controllers. So these are the areas where our team from the power converter side trying to get into and bringing a change in the things. Let me come to the MEMS side and piezo actuators. Dr. Rahul Shukla is working in this area. His email ID is also mentioned over here. Basically, in MEMS and piezo actuators part, the facility they have is especially double-sided mask aligners, spin coaters, hot plates, electromagnetic setups, multisonic cleaning systems, optical microscope, supercritical CO2 dryer developed indigenously, positive and negative photoresist. So using these things, they are trying to develop some MEMS components, and a lot of studies and investigation are being done. The piezoactuator sites, they are working on the using software for the simulation, COMSOL multiphysics, piezoelectric materials, epoxies, fixtures, optical tables, confocal sensors, power amplifiers, signal generators, oscilloscopes, and many equipments they are using to really develop piezoactuators and fabrications for these things. The area they are looking for is, for example, you can want to work on the micromirror arrays for the adaptive optics. This is one of the area that they're trying to work on. MEMS accelerometers, MEMS inclinometers, MEMS gimbals, piezo MEMS, and piezoelectric actuators for focusing and aberration correction of the X-ray mirrors. That is again a program, and then students are working on this, and they're also helping to make the things in a big way. Hybrid X-ray mirrors, piezoelectric materials and devices, and the most important, which has started recently, is smart materials and structures, so that thing can be managed in a better way. So especially these things are actually due on the spot. I'll come to the next topic, which is electron linac. You know that we
RRCAT has set up an agricultural radiation.
some problem. Yeah. So we have electron beam radiation facility at RRCAT. This is now being exploited by pharmaceutical industries and other industries for the commercial purpose. And now this is on the chargeable basis under incubation services. So whatever the basic things is learned in last 2 decades, now really translating, and many things we are trying to do, especially gem radiation, like yeah. So this is now available commercially. Things are done in a commercial basis, and we have a pretty long list of the vendors. People are coming to take the things and get these things processed. So which is again a new dimension to the things that is being done at RRCAT. Let me come to the other part of the activity, which is the laser activity. If we talk of the lasers, you know that there is a predomination of the various activities, and if we talk of lasers, definitely in India, RRCAT is the thing that we always think on those. So we have high-power green lasers developed indigenously, YAG lasers developed, femto, second fiber lasers, DPS multicolor laser systems, and a lot of research are being done on these things, which can have various applications. Especially if we talk of the fiber lasers, wide dot fiber lasers, we have developed this, or this is being used for various applications, especially 1 kilowatt average and 20 kilowatt peak power fiber coupled YAG lasers, which is the workhorse for all our ECCM activities that we do for the nuclear power plant, and these things are done routinely. Now people are also going to the semiconductor laser diode arrays, and now this is being packaged and some activities done in a reasonably good way. And from basic science to now its application. And advantage of these things are like when you talk of the penetration of the technologies. So once you have some understanding and expertise, definitely these can be extended. And one of the such example is when some of the people from Surat contacted us to help us in repairing the things. So since the people here have expertise on this, and they worked on, and now we are working on the repair of the laser diode arrays for the systems. And the impact of these things will be like earlier, whatever they were importing from there was costing around 1.5 lakhs. And after this, incubation, when technology goes to that, the cost of the machine will come down to 20,000. So that sort of advantage we'll get. And at the end of that, all these things will transfer to the people of India. If we talk about the material processing, we are doing a lot of material processing, especially laser cutting, laser welding, laser surface treatment, laser cladding and alloying, and laser additive manufacturing. And one of the beautiful example of the application of the understanding about the laser things is like we carried out underwater laser cutting for the pressure tube stubs of L8 coolant channels in 540 megawatt TAPS 4 reactor and laser cut PDP stubs. So this is the things which has been a beautiful example. And fitting cutting of coolant channels in TAPS 4 is another example. It is done using lasers. And if we talk of the laser welding applications, fuel pin welding, especially in PFBR, is done, and you see very nice and clean weld. And if you talk about the precision and reproducibility and the challenge, what laser welding can meet, when you talk of the welding of radiotherapy sources in encapsulated with the talk of the welding of 0.8 millimeter thick substrate with a size of 4.75 millimeter. So in such a small size and chips, you can work and things can be done using the lasers. So I'll come to the area where I work on as the laser additive manufacturing. So I'll go to a bit deep about this. So if we talk of laser additive manufacturing or laser 3D printing, normally people call upon what it is. In this, what we do is we start with a 3D model, and this model can come up from object imaging, or it can be an output of designer work using 3D CAD software, or it can be an output of a mathematical data analysis. So if you have a 3D model available, you can slice it along the vertical axis, and then you take the bottom-up approach for the deposition, and layer by layer, you start making the component. So we did the slicing of this, we use the job manipulations, and we deposit layer by layer from bottom-top approach. And at the end of this, you have whole component made in very things you can see, and I'll be telling you about how this is really changing the scenario. So this is the model, and this component is built, and this is this particular image that I'm showing we built in our machine over there. So now issue is, when I talk of this, how does it help to the industry? And we talk of the product development, specifically when we talk of the low volume manufacturing, specifically when we talk of DAE applications, we may not need, components in thousands and, lakhs, and we may be talking in a few tens or maybe a couple of them. So how does it change the whole scenario that I would like to tell so that you'll appreciate the concept of this? See, any work, it starts with the synthesis of data. We go for the analysis, then we go for the preparation of the documentation and drawing. And when this is done, we plan it, how to make it, we procure the raw material, we go for the tool procurement, we go for the CNC programming, manufacturing, we do the quality check, and then say pack it, dispatch to the user, and then use it. It's a very conventional method of making any component. But the moment you think of involving additive manufacturing, especially laser additive manufacturing, some of the steps goes out of it. For example, when I do the analysis, I have a 3D model available. Then I'm not looking for any documentation, any drawing, because that 3D model has all the information I want. So that step is saved. And since everything is going to build on the machine, we need not to plan, if you talk of mechanical systems, we need not to plan whether this has to go to, fabrication shop or to lathe or to, milling machine, where it has to go. So that sort of decision we need not to take. So no need of planning. Everything will be planned on the machine, on the additive manufacturing systems. When I cross the raw material procurement, my intention is that we are going to save a lot of time and the spare. See, normally what happens is we are not able to procure the material unless design is finalized. Because suppose you plan to buy, you think that the size of the component can be 120 millimeter by 120 millimeter by 120 millimeter. But if the designer comes with the size and he says this is optimum design, and the size is 122 millimeter in one dimension, probably you cannot use that particular raw material. So that sort of challenges are there. So, and if you buy a larger size, then again it's issues. But here, the moment you know about what is the material I'm going to use, either I'm going to use titanium or steel or any other material, I can buy in shapeless material like you can have powder and wire format. So right away we start the activity, we can start the procurement, and then that will save the whole procurement time and the cycle. So that's sort of advantage we have the raw material. Not only that, we can always negotiate with the vendor to have an economic order quantity, which is another part that we can think on. In additive manufacturing, we have lasers as a tool. So there is no need to procure any special tools for that. So as you see, there is a lot of saving and the time as well as, and time is money. So that way we can compress and come up with a faster product development using additive manufacturing technology. So the advantage it can bring us, for example, we always say that material design freedom. So when I talk of the material design freedom, you can have feature-based design manufacturing. You can think of depositing strong material as a base here, and then if you want to have some conductive material like copper on the top, you can do this. And this can be done in one go while making the component itself, which is a really big advantage as far as the making a component is concerned. Second thing is, if you talk of making this component, you see very complex shape. But what happens is the moment you slice it, it becomes very simple. You see, the base will have some circles, and then if you cut slice on the different area, then you'll find very simple 2D geometries available for the making it. And it really makes things very much different and easier for the people to work on. In this particular application, when you use laser array manufacturing, we are not having any cutting forces. We are not mounting on the job. The parts fixture also becomes very simple, and it really helps. You need not to have extra material to do a lot of things, especially the friction part. Another advantage when we talk of is the mass customizations. Whenever we talk of making any components, we always talk of the economies of the scale. We talk of the, handcrafted, specifically you want some particular feature, in particular, some of the components and some of the components you don't want. So that sort of thing is possible. One of the nice example of this is you can have, dental implants, thousands of them or maybe hundreds of them made in one batch, which is possible using this technology, which is not possible conventionally otherwise. Another beautiful example of this, you can have some sensors embedded in the component itself, which is not possible to assess but if you make the component by conventional method. So this is the beautiful advantage of that. And you can always have the advantage of logistic freedom. You can send your model across the world or any other places share with the collaborators, take their input and dot it. So that is the advantage of the logistic freedoms. You can place all these components and you can have a very beautiful nesting of the parts. So then optimization can be done in terms of the material saving. So a lot of reduction will be there. So this is the areas where this is bringing a big change. At the top of the limitation of these technologies as on today is the high production cost. As the technology is getting mature, more players are coming, premium is getting down, so things are changing. Another challenge and matter of research is to understand how to tackle the mechanical anisotropy, because when you make it, you will have different things. And specifically when we talk of our nuclear industries, how to qualify, because when we talk of this, we always talk of section 3 and section 8 or section 9. So how to bring them in and board in, and these are the challenges which need to work, and we have to really take this. Build volumes are really today small, and how to make it scale up is again limitation. And many of these processes require post-processing, which we need to rate the things and make the things another. Being a layered manufacturing technology, it has a disadvantage of stress stepping. So if you have very fine layer, probably you can have less stress, but the fabrication time will be very high. But if you increase it, so again, you have to optimize and come with some really good thickness so that things can be done in better way. If you talk of our lab, we are working from the system design to system development to material processing, to material testing, qualification and validation and modeling. So whole domain we are trying to cover. An idea to bring innovative element technologies and their applications so that really we can have a dent in manufacturing industries. That is the whole idea. Our efforts, if you see, we have built laser directed energy deposition systems indigenously. And one of the machine now is ready to dispatch to BARC. So it will be coming here. Another machine we also built for powder bed fusion machine. We are using extensively to making different components, and this machine will also be coming to BRC to CDM in a year or a half year time. So these things, again, I'll tell you the advantage of this. First is when we took up and we started this program, it was very easy for RRCAT to get a commercial machine, being not in the list. Band list, but what we did wanted many of the materials that probably DAE wants to work on for their recipe may not be available to us, that may not be available. So we have to really develop a recipe for this. And today these machines are not only able to address those material problems, but also giving it very cost effective, because when I talk of importing a DD machine, it is in some 7.5 crores. And if you talk of our Indian machine, if you go to the industries, we may come up somewhere in 3 or 3.5 crore. That is the reasonable good for Indian industries if they come to the market. So if you talk of powder bed fusion machine, the typical cost of the machine that people are selling it is in the range of 5 crore. And if you come up with, probably we may land up somewhere around 2 crore or so if we start and push this into the commercialization to the Indian industry. We tried to make many components, and I'll show you some of the examples where really we made a change. For example, these are the columni bushes that we developed for IGCAR. Earlier, what they were doing is they wanted bushes like this. And for making this bushes, they used to make a conventional substrate like this, and they used to deposit columni using GKW or GMAW process, and after that used to machine in and out. And this particular component is used for CRDM, a controlled rod drive mechanism of the FBR. And idea here is that this particular thing is required to avoid galling, and it has to have purely columni. There should not be any dilution. That is a challenge. So when you deposit over stainless steel, you have to do excessive machining, and columni is being a hard material, the hardness in the range of 750 to 810 VHM. It's really difficult to match, and people used to work and then they used to spend really 45 days to make such bushes because of excessive machining and lot of distortion, control other stuff. When we started using laser additive manufacturing, we made helical upward motion and built like this without any base. And after that, this is reduced to 72 hours. So that sort of change in the time and saving this. Some other things we did and try to work for the mesh type spaces for electro-engineering division at BRC. We wanted these mesh type spaces. And these you see very complex shape, and 0.1 millimeter is the dimension accuracy, and the wall thickness we are talking about 0.5 millimeter. So conventionally they are using a VIII process for making this, and being circular, rectangle and triangular shape over there. Lot of time used to spend, and they used to spend 5 days to make 3 or 4 mesh type spaces. When we started and mainly with water bed fusion machines, we reduced to 3 hours. So that sort of change. And when you talk of making 60 or 70 mesh type spaces, lot of difference in the time comes. And when we are qualifying and talking of this, before we make these components, we also do the process optimization, qualification of the material, so that all other things problem can be resolved. And when this is through, we can go for development of these components. Another beautiful example with involving dissimilar material is for ITER project. See what they want for DNB, they wanted a molybdenum layer on the top, and the thickness of the layer they are looking for is a 0.2 plus, 0.2 millimeter plus. And moly and copper, specifically they are using a copper alloy, copper chromium zirconium alloy. So in this, it is not possible to deposit this conventionally. And moreover, they have a constraint of, distortion of the plate also. So we started working on this, and we used some buffer layer, which is possible because you are using layer by layer. So you take the copper substrate, go for one layer deposition, then follow another one. And finally we could do, and with the nickel interlayer, we could deposit. And this qualified the process now. We are going for a fabrication of the larger component, which is being done in the range of 250 by 250 by 250. That is one of the things that we are doing for the ITER project. So if we focus and consider all these things that I talked so far, we'll have basically 4 basic areas of the research in this. One is, if you talk about the system development, you can think of a more smarter closed loop system so that things can be better. There's opportunity for the process development for the different materials, because every material will have a different recipe. You have to really have a taming strategy so that things can be done in a better way. And definitely material developments, because whatever the material today we are using is which is available commercially and developed for some other applications. For example, these are developed for plasma spray or some other techniques. We are adopting them directly and using this. But probably the composition may need to be tweaked here and there for better performance. So there is a scope of material development, and definitely design for additive manufacturing is really new and coming up, booming up the area. So I'll tell you some of the examples where we can really make changes. Idea is we can use the advanced tools of using solid mechanics, heat transfer, mass transfer, material engineering, and we can think of a really very smart component using generative designs and topology optimizer. For example, this is the bracket, and you want to make a really optimum bracket using this. You can come up, do the analysis, and shape can be like this, and which is extraordinarily different. And you can think of working on the material issues. You can try to have many materials, for example, titanium stainless steel joint. We are working on we had some limited success. We are working to make it more reliable and repeatable. So this is really thing that we can work on. And beside this, we can also work on having a microstructural design. When I talk of the anisotropy, at one point, this is a disadvantage for us because we are not able to use the material as a thumb. But if you have directionality in the microstructures leading to direction properties, you can always design the component so that you can derive the advantage of the directionality of the material property, which is possible here. You can think of going for a lattice structures. Conventionally, this cannot be made, and the dimension is in the range of 300. One compact heat exchangers we built, and again, I'll tell you the cost thing that comes. Conventionally, they are making using acid etching methods such as lattice structures, and they are costing in the range of few lakhs. One of the application for high temperature application, we tried to investigate, and we found that the rate they are asking from UK is around 65 lakhs for one heat exchangers. But if you make this, and we made one proto also at our lab, the money spent, if you took all the costs, especially deputation costs, whatever we include for the employee who worked on, the cost came out to be 7 lakhs. So you can think of how things are changing in terms of cost as well as the availability. And one more thing is when you talk to the foreign vendors, they also put a limitation on the design, and they say, no, these are a standard module. You have to select among these. But here we can think of our creativity, push them, and we want in specific case, which is possible. Another example is conformal parts. You see here, conventionally, if you want to have a die and you want to have cooling, the cooling channels like this. If our analysis say it's done, then it's done. And it's then used for biospide design. So all these things are a part of this, and we are working on it. So let me summarize the presentations. Yes, we have developed various technologies and facilities which can be used for research in engineering sciences. Continuous efforts are unfolding new areas of the research with a special emphasis on product development and subsequent transfer of these to application areas of the niche. And RRCAT is open to all Deshpande scholars and the family for extending the research facilities along with expertise earned through experience. With this, I conclude. Thank you very much for patient learning.
Thank you. Questions? Lots of hands.
Thank you for your nice talk. So I have one or two questions regarding that. You have already told about your Indus site synchrotron. So what is the machine availability?
What is that?
Machine availability to the user, considering all the planned and unplanned maintenance. So what is the machine availability to the user?
Sir, it is told to us it is more than 90% machine availability, and you see the already maintenance, and probably Nakazar will be able to address appropriately.
Plus one is available for more than 7,000 hours.
Okay. Okay.
Around 5,500.
Okay.
Okay. That is for similar machine.
Okay. So next is that regarding laser welding, you are also doing EB welding for this niobium cavity, etc. So is there any specific reasons that you are EB welding for niobium cavities? Technical reasons?
Niobium cavity?
You are doing niobium cavity EB for Formula, etc.
Yes.
So there you are doing EB welding.
Yes.
So is there any specific technical reasons for that, not doing laser welding?
No, sir. Now laser welding is also developed, and both things we are doing. But this EB welding is as per their as the process qualification what Formula wanted. So and again, since electron beam welding is more mature in the Western world, and they have a recipe available, so things are developed there. But as far as RRCAT is concerned, we already developed the laser welding part, and it is available, and some of the things are already tried out in our lab.
Okay. Thank you.
Hello. Yeah. So, do you have any slide on the status of your engagement with the LIGO project?
Sir, Dr. Shobhan Majumdar will be telling.
Oh,
yeah. Because we divided. So Dr. Shobhan Majumdar will be telling about the LIGO.
Perfect.
Anyone? Something. Shall we take the online question in that case? Oh, so what do I do? Someone from IGCAR? Is this the one? Shall I read this out? Yeah. Okay. So there is a comment question from IGCAR saying, nice talk for MEMS, micromirror and accelerometer fabrication. Are you using synchrotron X-rays or some other lithography technique?
We are using conventional lithography technique.
Conventional lithography?
Yes, yes.
Okay, I hope he got to hear it.
Yeah.
Anything else locally? So Dilip, what is the plan now? I mean, we have about 10 minutes to the next talk probably. No, this is done. Okay, no, is there a break or people, there'll be a break? Okay, take.
Thank you very much.
Thank you, Professor Mazumdar and all speakers. Before the break, let me quickly make the earlier announcements once again for the benefit of delegates who have joined late. The transport for tomorrow's BRC visit is arranged from Training School Hostel at 2:30 p.m. Mobile phones, pen drives, and other electronic devices are not allowed during this visit. The transport for Saturday's ACT-TRAC visit is arranged from Training School Hostel at 9 a.m. Please ensure that your name is included in the list at the help desk. The outstation delegates may collect the pen drives, which contain all the talks at the help desk today. The others may collect it tomorrow. And finally, if you've missed any of the previous lectures, these are available on YouTube link. Let us now break for tea. We are expected to begin the next session at 11:40 a.m. Thank you.
Unmuting myself. You can hear me? Hello? Yes, you are. Oh, from the WebEx, right? Wait, let me just see. Try speaking. I can't hear you, Anurag, from the WebEx. See any more? Unmute, wait, speak. Let me see. Wait. Shall I come out and again join back in? Giving access, that might work better. Me. Please try speaking. yet. What is wrong? I everything is.
Are we audible now, ma'am?
Yes, absolutely yes.
Okay, sir. Ma'am, just share your presentation.
Okay, I'm disconnecting the phone now.
Okay.
Can you see?
Yes, ma'am, it is visible. Can you make it full screen?
Yes.
Yeah, perfect.
Yeah?
Yes, ma'am, it is visible.
Okay. Yeah. So I'm changing my slides also and they are visible, right?
Yes, yes, it is visible.
Okay. So I am audible as well as visible.
Yes, ma'am.
Okay. So we are done with this now.
Yes, 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 perfect.
Thank you very much.
Welcome.
And I will be ready at yeah, like in the lunchtime itself. So we can just get this going in the lunch itself.
Sure, ma'am, sure.
Okay. Thank you very much, Anurag.
Thank you.
Okay. So I stop sharing now?
Yes, ma'am, you can stop.
Okay. Thank you.
The atomic energy program was started in the country in 1948, and the Department of Atomic Energy, DAE, was established in 1954 by the visionary Indian nuclear scientist Dr. Homi Jahangir Bhabha, who envisioned it as the hub for the development of nuclear science and technology and their applications. The objectives for DAE were multifold, namely to create know-how for harnessing atomic energy for power generation, using radiation technology for societal applications in agriculture, healthcare, and industry, while carrying out basic research in a variety of domains of mathematics, science, engineering, and medicine. Right from its inception, DAE has placed great emphasis on the in-house development of human resources for carrying out its research and development activities. To meet this objective, the BARC Training School was established in 1957. Subsequently, to further strengthen the framework for human resource development at DAE establishments and push the frontiers of nuclear science and engineering through academic programs, the Homi Bhabha National Institute, HBNI, was established in 2005. It was recognized as a deemed to be university by UGC and given the status of a grant-in-aid institution of DAE in 2014. HBNI was accredited with an A grade by National Assessment and Accreditation Council in 2015. HBNI conducts postgraduate and doctoral programs in various disciplines across its 11 campuses, comprising the 4 research and development units of DAE, Bhabha Atomic Research Center, BARC, Mumbai, Indira Gandhi Center for Atomic Research, IGCAR, Kalpakkam, Raja Ramanna Center for Advanced Technology, RRCAT, Indore, and Variable Energy Cyclotron Center, VECC, Kolkata, and the 7 grant-in-aid institutions of DAE, namely Harish Chandra Research Institute, HRI, Prayagraj, Institute of Mathematical Sciences, IMSC, Chennai, Institute of Physics, IOP, Bhubaneswar, the Institute for Plasma Research, IPR, Gandhinagar, National Institute of Science, Education and Research, NISER, Bhubaneswar, Saha Institute of Nuclear Physics, SINP, Kolkata, and Tata Memorial Center, TMC, Mumbai. HBNI is thus a conglomeration of constituent institutions and off-campus center with a thriving academic and research environment. The organizational architecture of HBNI, with a central hub at Mumbai being linked to centers of excellence all around the country, is one of its strengths and has facilitated research and development across diverse disciplines while sharing common objectives. The academic and research activities at the constituent institutions have significantly enhanced the country's indigenous capability in nuclear science and technology and generated capable and dynamic human resources to man and spearhead these programs. HBNI offers options in 32 diverse academic programs across physical sciences, chemical sciences, engineering sciences, mathematical sciences, life sciences, medical and health sciences, as well as humanities. In addition, HBNI also runs several academic programs towards skill development for the country. In the 15 years since its inception, HBNI has awarded over 1,600 PhDs, with around 250 PhDs being awarded in 2019-2020 alone, a notable academic achievement. More than 2,200 publications in high-quality journals during 2019 bears testimony to the faculty and student quality of HBNI. Students are also encouraged to present their work at international conferences by extending financial assistance. Apart from the quality of faculty, mentors, and students, excellence is enabled by world-class research facilities, such as research reactors, accelerators, state-of-the-art equipment, and ultra-modern experimental and computational facilities across all its centers. This has created the ecosystem necessary to push the boundaries of innovation and solve crucial and challenging problems. HBNI has been ranked 14th in the list of top universities in the country by the National Institutional Ranking Framework. In recent times, MOUs have been signed with several eminent national and international institutions. These measures shall also add a range of value-added programs to the curriculum and are expected to lead to further enhancement in the quality, outcomes, and ranking of HBNI in the future. HBNI is also rapidly adapting to the new age teaching methodologies, and capacity is being ramped up towards improved infrastructure facilities in sync with the current trends of online teaching, webinars, and incorporation of augmented and virtual reality in the teaching learning methodologies. This is expected to increase opportunities, raise academic standards, and widen the base across various segments and strata of the academic community. HBNI is today recognized as a world-class university in the sphere of nuclear science and technology. With the zeal and motivation of its faculty and students, and steered by an able administration, HBNI is expected to scale new heights in the years to come. It provides a vibrant platform for bright young minds to explore, endeavor, and succeed in the fulfilling pursuit of scientific and technical advancements across a gamut of domains.
Welcome back, everyone. The chairperson of session 6 is Professor Sumit Som, Director of VECC Kolkata. I humbly request him to take over and conduct the meeting. Please, sir.
Thank you very much. So now, in this session, there are 3 talks. The first one is medical and health aspects is from TMC, Dr. Sudeep Gupta. So, Dr. Gupta, please. So total time is 30 minutes plus 5 minutes.
Beg your pardon?
30 minutes plus 5 minutes discussion. Thank you.
I will stop on the 30th minute. Thank you, Chairperson, sir. Good morning, colleagues. First of all, I would like to thank the Honorable Vice Chancellor for the privilege and opportunity of making this presentation this morning. I am absolutely delighted to be here. Yesterday, my colleague, Dr. Prasanna Venkatraman, delivered a talk on the basic and translational science aspects of Tata Memorial Center. I am a medical oncologist. My areas of specialization are in treating breast and gynecological cancers with chemotherapy and systemic therapies. And I'm also currently the director of ACTREC. So what I will do in the next 30 minutes is to try to give you a flavor of the kind of clinical activities and clinical research that we undertake at Tata Memorial Center. Before I do that, I think it would not be out of place to set the context by discussing a little bit about the epidemiology of cancers in India and the clinical spectrum. But before that, I would like to bring to your attention the remarkable fact that in all of human history, the population, the world's population has actually exponentially increased only in the past about 100 or 120 years. Now, the reason why this is important for diseases like cancer is the fact that this also means that the large majority of older population in the world, and if I may take you back, if you look at this figure, most of that increase in the world's population is confined to the so-called less developed region or the developing parts of the world. And the reason this is important is because this also means that the older population has increased substantially, also largely confined to the developing parts of the world. Many non-communicable diseases, including cancer, are essentially diseases of aging. So as we move forward, as our population ages, we have to deal with the possibility of exponentially increasing number of cases of non-communicable diseases, including cardiovascular, renal, pulmonary, cancer, etc., and so on. So this is a map of the world by incidence of cancer, and incidence of cancer is defined as the number of new cases of cancer per 100,000 population per year, standardized for the population structure is in various parts of the world. And you can see that India and many similar countries have an incidence that is much lower, about 1/3 to 1/4 that of industrialized nations. In terms of the number of deaths due to cancer per 100,000 population, which is mortality, also we have a population-based mortality from cancers that is much lower than that in the industrialized parts of the world. But I will call your attention to the fact that this is the denominator here is per 100,000 population. In absolute numbers, the burden of treating diseases like cancer is substantially higher in India and in many other countries that have large populations. So this is what I was wanting to say. At the current time, in India, we have about 1.3 million new cases of cancer every year. And with the current trends, it is expected that this will become about 2.1 million per year new cases of cancer every year in the next 15 to 20 years. We currently have about 850,000 deaths due to cancer every year, expected to increase to about 1.4 to 1.5 million in the next 15 to 20 years. So this particular, there's a ratio called mortality to incidence ratio, and this became very popular during the COVID pandemic. It is called the case fatality ratio. So at the population level, if you divide the incidence by the mortality, you approximately get the proportion of cases of any disease that die of that disease. So this is Europe, and you can see in most parts of Europe, the incidence of cancer is about anywhere between 320 to 360 cases of cancer per 100,000 population per year, and the mortality is about 1/4 to 1/3 of that. And you look at Asia, in absolute numbers, we have about 100 to 150 cases of cancer per 100,000 population per year. But you look at India, it is 100, but the red bar there, essentially our mortality is 60 per 100,000. So even though we see fewer number of cases per 100,000 population, about 60% of the cases die of their disease, compared to, for example, 1/4 to 1/3 in more advanced countries. There are several inequities that exist within countries like India. Even within a country like India, the incidence of cancer is not uniform. So urban areas have much higher incidence compared to rural areas. And I'm just showing you this figure. This is relatively old, but largely representative, that about 50 per 100,000 is the incidence of cancer in rural parts of India. But if you look at the mortality is the same. So which means that with half the incidence, the mortality remains the same in rural parts of India, which means a much higher proportion of patients who are diagnosed in rural and semi-urban areas die of their disease than those who live in urban areas. And by literacy, you see that the least literate portion of our population have more than double the mortality of the most literate population. So this was a study that was conducted by my colleague, Dr. Rajesh Dikshit, who's the director of the Center for Cancer Epidemiology, published in the Lancet a few years ago. And this points to continuing and pervasive inequities and inequalities in the delivery of healthcare within our country. It is well known, but it is there in stark numbers. So in males, tobacco-related cancers, those of the oral cavity and lung, are the most common cancers in India. In women, breast cancer has now overtaken cervix cancer as the most common cancer in our population. In terms of clinical spectrum, this is just an exemplar, and on the bottom is the US data to show that even with whatever number of cases we have, a higher proportion of our cases are present in the more advanced stages to the healthcare system. So which, of course, it is well known that cancers are more curable if they are detected at an earlier stage. And it is not uncommon to see these kinds of presentations even today, although it is hard to believe. So we have larger tumors, we have more advanced disease at presentation, and we also have our patients on an average are younger compared to the series that are presented from the West. This is the map of the world by radiotherapy machines. And you can see that the parts of the world that treat the most advanced cases, although in fewer numbers, and that require radiotherapy equipment the most, have the least number of machines of anywhere. In terms of the number of personnel, you can see again that the number of doctors, nurses, healthcare personnel are much lower than what is recommended, what is optimum, and what is desirable. But on the good side, you look at the cost of the same drug in the US and in India, and because of a relatively robust generics pharmaceutical industry, our actual cost of drugs is much lower than in most parts of the world, and which is why India is often called the pharmacy of the world. So this is Tata Memorial Center. It used to be only Mumbai, but we are currently located in 7 locations across India: Guwahati, Visakhapatnam, Varanasi, Sangrur, Mohali, Mumbai. So all these have been, is now Tata Memorial Center. And our mission is to provide comprehensive care to one and all, regardless of their ability to pay for it, through excellence in service, research, and education. And this has been the mission of our institution since the time of its inception in 1941. So this is a brief history of our institution. We were commissioned by the Tatas, the House of Tatas in 1941, but we came under the control and are a unit of the Department of Atomic Energy since 1962. ACTREC moved to its new campus from Parel, which is in Navi Mumbai, in 2002. And we have all these other centers that I just mentioned. And I overlooked mentioning Muzaffarpur, which is also functioning as of now. Muzaffarpur is in Bihar. So all of these have progressively happened in the past 7 to 8 years. So there have been many pioneering activities of Tata Memorial Center. And the most recent one is the first patient being treated with an indigenously created chimeric antigen receptor T-cell treatment in 2021. And this is an indigenously constructed CAR in collaboration with IIT Bombay. This treatment costs about 3.5 to 4 crores of rupees per treatment in the West, and we will deliver it. This is being done in patients in clinical trial even as I speak, but this will be delivered to our patients at a cost of about 25 to 30 lakhs per treatment. So this is, these are the number of cases that we register in our hospital. These are new cancer cases every year. Many of them have repeated visits. So in 2018, we registered close to 80,000 new cancer cases every year only in Mumbai. And this makes us the largest hospital, the largest cancer hospital in the world, larger than MD Anderson Cancer Center in the US and Sloan Kettering, at least in numbers. This is a heat map of the patients who visited, who came to us. And you can see that naturally we have a large number of patients from Mumbai and Maharashtra, but we have a very high number from northern and northeast parts of India, again pointing to the fact that healthcare systems are perhaps most deficient in those parts of our country. So in TMC, we have pioneered another way of working in India at least. So I'm a medical oncologist, and medical oncologists specialize in giving chemotherapy, for example. But my primary affiliation now is not as a medical oncologist, it is as a breast cancer physician. So we have what we call the multidisciplinary disease management groups. So all physicians, surgeons, radiation oncologists, radiologists, pathologists, nuclear medicine physicians, microbiologists, everybody who will specialize in one or at the most 2 diseases, and all of them will work together in the same location in the hospital so that the patient doesn't get shuttled from one location to the other and we don't create silos of departments. And of course, this requires a large amount, this needs human resource capacity. We need to have enough number of physicians to go around for each disease management group. We have painstakingly created that capacity in the past many decades. And now we are the only cancer hospital in India who function in this focused disease management group like activity. So we are paperless for the past many years. Our data, patient histories, their records, all investigations are all online. Patients can access them from anywhere in India. They need to have access to the web. But this also creates opportunities, for example, for working with big data. And I am collaborating with colleagues from IIT Madras in crunching all the data from our, for 2 diseases, breast and gynecological cancers, using natural language processing algorithms and hanging the data on common data models or PEGs, where they can then be analyzed to make sense out of that data. And I think this is one opportunity where colleagues from many different institutions of DAE can collaborate with us. We also have an image management system. We don't have an X-ray film in our center. We look at all the films on our computers, X-rays, MRIs, mammograms, etc., and so on. And again, this lends itself to several opportunities for collaboration. I'll just give you a very brief flavor of the kind of clinical research that we do at Tata Memorial Center. Our motto is not to write papers. Our motto is to conduct research that is locally relevant, that will answer questions that are relevant to cancer patients in India, and hopefully which will have an impact not only in my center in Mumbai, but worldwide. And I'm happy to say that we have succeeded at least to some extent in that mission in the past many years. So we have 3 ethics committees. We have a clinical research secretariat. We have the TMC Research Administration Council that oversees all clinical research in our hospital. And we are grateful to the Department of Atomic Energy for creating what we call the DAE Clinical Trial Center about 15 to 20 years ago, that has made us a very sophisticated clinical trial center in India and in the world. So some flavor of our research. This is our founders, Dr. Khanolkar, and I believe my colleague Prasanna projected this slide very briefly yesterday. But Dr. Khanolkar was a founder of the predecessor of ACTREC, the Cancer Research Institute, and he and his colleagues deciphered the association between tobacco and cancers almost contemporaneously with Dahl and Hill. And some of you know that Dahl and Hill are famous for pointing out the association between smoking and lung cancer. This was almost contemporaneous with that. This is in Nature in 1945. More recently, we ran this large randomized controlled trial in 150,000 women in the slums of Mumbai. Many of you know that the way to screen for breast cancer is by mammogram, and the way to screen for cervix cancer is by pap smear, but it is not feasible in India because of logistics and requirement of expertise. So we asked the question, can we screen for breast cancer and for cervix cancer using the techniques of clinical breast examination and visual inspection of the cervix with acetic acid, using a workforce that comprised of women who were 10th standard educated. So this was a randomized control trial, 150,000 women, 75,000 women received this screening, the other 75,000 did not. This was presented at the plenary session of the American Society of Clinical Oncology, the biggest cancer meeting in the world. And we showed, my colleagues showed actually, that you can bring down the cervix cancer mortality by 30% using the simple technique of applying acetic acid on the cervix. For the breast cancer component of this study, published in the British Medical Journal last year, led by Dr. Mitra, you can see just clinical breast examination, no mammogram, brought down the mortality from breast cancer sharply in women over the age of 50 years. And of course, we are happy to say that the result of our study has led the government of India to introduce these 2 techniques of screening throughout India in all primary healthcare centers as part of the national health policy. My colleague, Dr. Dikshit, the director of CCE, led a study to figure out what might predispose individuals to develop gallbladder cancer. Now, gallbladder cancer doesn't occur everywhere in the world. It happens in India, it happens in Chile, it happens in 1 or 2 other countries. So they did a genome-wide association study, and you can see they found 2 SNPs that led to a very high predisposition to breast cancer. This has subsequently been validated by the Chileans, but my colleagues were the first to bring out this association, published in the Lancet Oncology a few years ago. In terms of treatment, my colleague, Dr. Anil De Cruz, the former director of TMH and members of the Head and Neck Cancer Working Group, asked the question, should you remove the neck nodes when you operate on a patient with oral cancer? And this might seem a very simple question to you, but this had never ever been answered throughout the world. This was a plenary presentation, yet another plenary presentation at the ASCO, and published as a single center study in the New England Journal of Medicine a few years ago. And we showed, my colleagues showed that you can have a sharp increase in cure and survival by performing neck node dissection along with performing surgery for oral cancer. Another study by my head and neck colleagues, can you preserve the jawbone mandible when you operate on patients with advanced oral cancer and by using chemotherapy prior to surgery? Now, some of you may say these are all very mundane, simple questions, but believe me, this is the Journal of Clinical Oncology, and people would give their left arm to publish in this journal. So my colleagues showed that actually you can preserve the jawbone if you deliver chemotherapy prior to performing surgery in such patients. My medical oncology colleagues from head and neck showed that a low-cost oral treatment is not only less expensive, but actually more effective. The upper survival curve on your left actually is the oral treatment. So oral treatment is less expensive and more effective than the intravenous treatment for some of these patients with oral cancer. In cervix cancer, should we do radiation? Should we do surgery? I had the privilege of presenting this at the plenary session of the European Society of Medical Oncology, again, the second biggest cancer meeting in the world, and subsequently again published in the JCO. And we showed that performing chemotherapy with radiotherapy leads to a sharp increase, about 7 to 8% increase in cure rates compared with performing surgery. Now, this is one figure here, but this has led to change in practice throughout the world. Europeans have stopped performing surgery. Latin Americans have stopped performing surgery. East Asians in Taiwan and Japan have stopped performing surgery and are giving radiotherapy as a result of our study. We also showed more recently that delivering radiotherapy with a sophisticated technique called intensity modulated radiotherapy compared with conventional radiotherapy actually results in a sharp decrease in side effects to the bowel and bladder. And again, this is a practice defining study because now the government of India can confidently say that there is a health benefit of using the more expensive machines. In prostate cancer, when you radiate the prostate with curative intent, should you radiate the surrounding lymph nodes in the pelvis? Should you give very focused radiation only to the prostate? And my colleague Vedang Murthy and colleagues from the genitourinary group showed that you can actually have a sharp increase in cure rates if you also include the lymph nodes in the pelvis while delivering radiotherapy. Now again, let me just point out another fact. The numbers on the x-axis, 0, 12, 24, 36, 48 are actually months. And that means that I cannot define cure by giving treatment today and looking at the patient tomorrow. I have to follow up these patients for 5 years, 7 years, 8 years, 10 years. And therefore, these studies take a long time. They actually are about 8, 10, or 12 years in the cooking, and then you can produce a single result that I show here. And again, this is a question that has never ever been answered. This has changed practice throughout the world, including in North America. In breast cancer, can we increase the cure rate in in women who are undergoing surgery for breast cancer by recapitulating the second half of the menstrual cycle in them? So many of you know that menstrual cycle, the first half is the follicular phase, estrogen, and the second half is the luteal phase of progesterone. And there have been indications that if women are operated in the second half of the cycle, the cure rates are better. So Dr. Badwe asked this question. He actually asked it when he was in UK, but he carried out the trial when he came back to India. And he recapitulated the second half of the cycle by giving a single injection of progesterone costing about 50 or 55 rupees to half the patients, and the other half did not receive it. That's called a randomized control trial in 1,000 patients. And you see in patients with node-positive disease, a single injection of progesterone costing about 55 rupees increases the cure rate by about 11 or 12% as well as survival. Is it beneficial to remove the primary tumor when the patients with breast cancer already present in stage 4 disease, when the disease has already spread to organs like the liver and lung? No question, no answer to this question thus far. Dr. Badwe led this study, again a randomized control trial, and we showed that it is not useful to perform surgery in such patients. This has stopped surgeons from performing surgery on such patients throughout the world after this publication in the Lancet. So my thoughts as a physician, many treatments may be effective, but they are useless if they are not accessible to patients. This is a drug called trastuzumab. It targets the HER2 receptor. This was called a revolutionary treatment for breast cancer because it markedly improved the cure rates in HER2 positive breast cancer patients. And this is 2005, Dr. Hortobagi writing an editorial in the New England Journal of Medicine. We audited our patient population in 2008, and we found that only 8.5% of our patients actually could receive this treatment because the cost was 1.2 lakhs of rupees per injection given every 3 weeks for 1 year. So what did we do? We did something. And in 2016, we audited our patients again. We showed that close to 60% of our patients were able to receive this drug. And currently it is about 90%. What did we do? We forged social partnerships and philanthropic support. There was the availability of somewhat lower cost biosimilars by Indian companies. But very importantly, we consistently advocated that 1 year of trastuzumab is not required. You can get away with giving it only for 3 or 6 months. Now, many of you know that I cannot speak from the top of my head. This is the era of evidence-based medicine. I have to prove what I say. So there have been 6 randomized trials, all from Europe, that have compared 6 months or 3 months of this drug to 1 year, and none of them has proved non-inferiority. So what did we do? We undertook an individual patient data meta-analysis of all these trials. But for individual patient data, you have to write to all the investigators. They have to share their Excel sheets or their SPSS sheets with us. What we did was we pioneered a statistical technique of extracting individual time to events from published survival curves. We did this for the very first time in the world. We used data and we used WebPlot digitizer to extract individual patient times from each published curve from each of those 6 trials and reconstructed the survival curves of the kind that I showed you earlier. We synthesized all of them and we showed that shorter durations of trastuzumab of about 3 to 6 months are equivalent to 1 year. And you can see in the denominator on the x-axis that this is about 11,000 patients. And we published this in the Journal of the American Medical Association. And we have produced a result that will impact the treatment of this disease in at least 60% of the world. So what did we learn? We learned that robustly designed clinical trials or studies are likely to answer important questions, including cancer. But if we ask the right questions, if we ask the relevant questions, and what are the important elements? Relevant question, potential to define clinical practice worldwide, a nice design, a nice statistical design, meticulous follow-up, very importantly, funding. 95% of the studies that I showed you here have been supported and funded by the Department of Atomic Energy, not by the DBT, not by the DST. They have changed practice, not only in Tata Memorial Center, they have changed practice throughout the world. And very importantly, an appetite for long gestation periods. We cannot have a project system where the result is expected in 3 years, because in 3 years, you cannot say whether a person is cured or not cured of their disease. The future, I will not go into the details. Artificial intelligence is here. It is still not clinically actionable, applicable in most scenarios, but is beginning to be. Perhaps 10 years from now, 15 years from now, we can decipher the genomic makeup of a tumor, not by performing PCR or by sequencing, but by looking at an image of that tumor and applying an AI algorithm. So our center, our group has done some work in AI related to radiology images, but more importantly, and I'm the PI of this study, we have recently received a very large grant from the Department of Biotechnology to create a national imaging biobank for cancer. And you can see our collaborating centers are AIIMS, PGI, and a couple of other hospitals. What we will do, there are 2 kinds of images. Radiology images, they are all available on PACS. There is a standard format called the DICOM format. Hundreds of thousands of those images are in our computers and our servers. But more importantly, the pathology slides, they have never been digitized systematically in every patient. What we will do, what we are doing is to create whole slide images of every single pathology slide throw it into a server, and then this is a biobank. This is a bank that is available to everyone throughout India, including colleagues from DAE, to apply a variety of AI techniques, including ones like CNN, to bring to bear on this huge and important data set. Just creating this biobank is a task. So let me end. Dobzhansky said, I think around 1970, that nothing in biology makes sense except in the light of evolution. And over a period of time, I have come to realize the force of this statement. Where were we in the past? And will that help us gaze at our trajectory as we go into the future? And this is a cartoon that I drew for another talk some time ago. On the y-axis is progress, whichever way you define it. On the x-axis is time. And progress can be linear, it can be exponential, it can begin to plateau. But to be able to gaze meaningfully into the future, we should know which trajectory, or we should at least try to think about which trajectory are we following, but very importantly, also where we are currently on the arrow of time. And only with some sense of history, some sense of our present situation, I think we are able to gaze somewhat meaningfully into the future. So it is often said that the low-hanging fruits in science in other fields have already been plucked. But at Tata Memorial Center, we believe that low-hanging fruits appear magically before each generation. So thank you very much for your attention.
So wonderful talk, Dr. Gupta. So now a few questions, please. Yeah, sir.
Dr. Gupta, first of all, my thanks to you on behalf of everybody here for an excellent presentation, and also for spearheading research that will have great impact and immediate impact on the society. Congratulations. I have only one observation, because this your talk has come just after the talk by Dr. Paul from RRCAT. I am tempted to ask, with regard to breast cancer, where you are the leading expert, implants, will the work at RRCAT on this additive manufacturing be of any relevance in developing low-cost implants, materials which can go into breast cancer treatment?
Thank you, sir, for your very kind comments about Tata Memorial Center. I must say that the kind of research that I presented today is a team sport, and each of the authors on those papers were there because they truly, all of them, produced the results that were produced. So thank you very much for your kind words on behalf of TMC. We are grateful to you for giving us the opportunity. With respect to your comment about breast cancer implants, I think you've hit the nail right on its head. There are a variety of clinical situations in oncology as well as in non-oncology practice, but since Tata Memorial is only an oncology center, we can speak only about cancer. There are a variety of situations where prostheses, implants, and other devices are of immense value. And I also listened to the excellent talk by Dr. Paul, and he mentioned the versatility of manufacturing. You can custom make, you can do all kinds of things. I think that is tailor-made for clinical application. And with your help, sir, I think I did connect with Dr. Paul just before my talk, and also with the director of RRCAT. And I hope that we will be able to make a visit to RRCAT and reciprocal, and hopefully we will progress this further. I must add that we have had fruitful collaborations with the Indian Institutes of Technology, mainly Bombay, but also some in Kanpur, some in Madras, not so much with Delhi. And there is immense talent within the DAE. And we have also collaborated on many projects with the Department of Atomic Energy, including on radiotherapy machines, etc. But I hope to take this forward, at least for implants and for 3D printing.
Maybe you spoke about this. Will you tell us a little bit about immunotherapy? I mean, are you sort of engaged in immunotherapy in the sense of tailoring treatment to the genetic makeup of the patient or the tumor?
So I think that's an excellent question. And some of you would know that the Nobel Prize for Medicine was awarded to two individuals who made monumental contribution to immunotherapy a couple of years ago. So at Tata Memorial Center, we deliver the routine drugs that are manufactured by multinational companies. We have no intellectual contribution there. We just give the drugs, the immune checkpoint inhibitors that have been made by others. But very importantly, I told you that we are the pioneering center in India who delivered the first chimeric antigen receptor treatment last year. And chimeric antigen receptor is essentially T cells of a cancer patient that are engineered to express receptors that will recognize an antigen on the cancer cell and destroy it. And this is ordinarily done by manipulating those T cells using what are called vectors. Now, that vector technology was pioneered at UPenn in the US, but it is the preserve only of a few labs all over the world, which have essentially then sold it to pharma companies. And which is why I mentioned 4 crores of rupees a year, not a year, per treatment. So what we have done is collaborated with an individual called Dr. Rahul Purwar. Some of you might know, he's in IIT Bombay. And he has created an indigenous vector for the CD19 antigen, which is expressed on the B cells and in B cell malignancies. And we have the ability to manipulate that in ACTREC in a lab that is led by my colleague, Dr. Gaurav Narula. And we delivered the first CAR T cell. 6 patients have already received it, even as I speak, both for acute leukemia as well as for lymphoma. And we are going full steam ahead. That's a highly tailored form of immunotherapy. To your last question, it is not necessarily specific to the genetic makeup of that particular individual. It is essentially specific to the kind of cancer that that person has and kind of antigen that that cancer expresses. So yes, that is our original contribution, and that technology is available, like I said, to perhaps 4 or 5 companies all over the world, no more than that.
Any other questions?
Yes, it is not something that you can give to 50,000 patients. It is, of course, if you have to tailor make something for each patient, it takes time. It needs a GMP facility. It needs expertise. It needs expertise in vector technology. It needs expertise in manipulating the cells outside the body. And we have created that expertise. But yes, it is not even required for all patients. It is required for patients who fail the conventional treatments. I think if there's time, there is somebody who raised the hand right at the back.
Last questions, I think. Yeah, please.
Oh.
Yeah, congratulations, sir. Undoubtedly, Tata Memorial remains the actual temple in Bombay, treating everybody for time immemorial. Sir, you spoke about it needs a standing ovation, sir.
No.
So, intensity modulated radiotherapy, sir, you mentioned.
Yes.
That is very important. The beam delivery system should generate the beam. And we have to modulate the intensity too, as well as also scan the whole tumor in 3D volume to deliver it where, and so that the healthy cells are protected. These healthy cells, if they get radiation, possibly they may eventually turn out to be malignant in time. Have you carried out some studies on the multi-ions? Besides the usual proton and carbon, which ions will treat the type of tumors that we have?
So you have touched a nerve here. So along with the blessings of Director of BARC, Dr. Mohanty, we have been in discussions about using oxygen and other ions, not only just proton and carbon, but that technology does not exist anywhere in the world. It is not there with CERN. It is not there with Japanese as we speak. The Japanese use carbon. And so what our thought process is, and my colleague Dr. Laskar is leading it, and you have been in communication with him, is to have a machine that will produce all ions which can be accelerated and used to treat. It's a humongous undertaking. We are not a technology institution, so we need partnerships. And we have been in discussion with BARC and also with a couple of universities in Japan to be able to do this. I am not sure whether we will be able to do it or not, but yes, it is on the wish list. Thank you. Thank you, sir. Thank you, sir.
Time is over. So thank you very much once again. So next talk from BRC on engineering sciences, Dr. A.K. Nayak. Dr. Nayak, please.
Namaskar and very good afternoon to all of you. So my talk is mostly on, I will give you an overview of the research development activities, BARC especially in engineering sciences. So it's a little, I will say that, what do you say, spin-off. It's basically spin-off of the basic sciences. So when these 2 days we have been hearing from atoms, molecules and all, this you will not hear in this talk. It is basically products, technologies, and what probably what you have already done, maybe something beyond that. At the same time, let me tell you that in engineering sciences, the spectrum of activities, especially on technology development, it's really very, very high level. Novel technologies has been developed. It's very difficult to present it here because of I would say that strategic nature and very, very limitations to basic sciences. So all that I'm going to speak here, which have some connections to basic sciences or which has been carried out under the umbrella of HBNI. Okay, let me first thank the groups which have contributed here. My own group, there's a reactor design development group, the chemical engineering group, materials group, and energy, that's nuclear recycle group. So I'm covering basically the summary of R&D activities under HBNI umbrella, which is I'm going to present here. So if you look at BRC as a whole, I think if they carry out a large spectrum of activities, but if we club them, 2 important activities which we do is one is on energy, that is the clean energy production through nuclear fission. And other is definitely to meet the clean drinking water for millions, or with time it becomes billions. So these 2 are basically 2 big spectrum of activities for which historically a lot of technologies being developed. And the nuclear energy conversion, the R&D is right from the front end to back end, covering the whole nuclear fuel cycle, and that leads to the research in development of the research and development in the closed fuel cycle. And the energy conversion is especially through development of many advanced reactors I'll be covering here, as well as on the research reactors, especially for isotope production, for medical and a lot of industry applications. And with time, the automation, especially in robotics to handle the radioactive materials, as well as medical applications, a lot of activities is going on. I'll speak very briefly about those things. So my first, I'll say that why do we require the advanced reactors? The nuclear technology is 6, 7 decades old. And the moment I speak to a basic scientist, there is a lot of things in his mind. Why after so many years you talk about advanced reactors? So the genesis of advanced reactor development happened especially after the accidents at 3 Mile Island, Chernobyl. It started after that. the investors, the nuclear vendors who were building the reactors, they no more wanted the conventional reactors. They wanted very, very highly safe reactors without or with minimum operator actions. And more happened, especially after the Fukushima, that everybody almost who are working on the nuclear technology wanted very, very safe reactors with the minimum or without any operator actions. And that is what is called the passive safety systems came in. You have to design a reactor so that in case of, if you look at the right side, any external events which include, for example, a prolonged or long station blackout for several days, it should survive on its own. The reactor should not melt down or Fukushima type of accident is completely eliminated in design. On the left side, if you see that, especially after the 9/11, there was trust that in case there is malevolent action or some mischievous people enter the control room and they disengage, especially the C&I, the control instrumentation system, the reactor should be safely shut down. These are the history that why the advanced reactors started developing. So when the new reactors started developing with these concepts, especially with passive safety systems, so many things came into picture which started right from the reactor physics aspects for advanced reactor design. The thermal hydraulics, which becomes very critical, especially in the passive systems, those rigorous R&D took place in that. The structural mechanics, especially for the nuclear reactor components, their health evaluation and aging effects. Then a specific type fuel, which we say that accident-tolerant fuel, the R&D started taking off in that. Materials, which is the backbone of the nation, lot of work started, especially on advanced materials development. And this work not only in the front end, back end, and the closed fuel cycle it happened. If you look at the right side, the R&D, especially for the structural mechanics, this started, if you look at this, go right from the atomistic scale modeling, which is multi-scale, multi-physics simulation, and the fatigue behavior of degraded materials, the seismic simulation, including how the soil behaves, whether the reactor structures are safe enough under those conditions they are evaluated. And very recently, I believe, may not be aware, the human reliability, especially being talked about, especially after the 3 Mile Island accident and recently Fukushima, the human reliability is a big question, being questioned everywhere. So research that rigorous research on factoring of human reliability, the ultimate risk of the reactor is also being. Then the probabilistic safety assessment of aging components, the machine learning and data analysis, these are the, I'll say, the high technology areas where the R&D is going on. Especially in BARC, for the advanced nuclear reactor development, many facilities were being built. So you'll be questioning that why to build so many facilities for the advanced nuclear reactor development. So one of the major aspects was, as I spoke sometime before, is the passive safety systems. The passive systems, they operate on natural laws, the buoyancy itself. There are no force circulation in the system. So the physics of fluid is very complex for such systems. It's because the flow is not fully developed, especially when you start the reactor from rest. There is big question that whether there is adequate flow to remove the fission energy, or the flow can be oscillatory. Yesterday there was a presentation also, or what is the thermal margin, the critical heat flux for these reactors. So considering that, several facilities were built which are state of the art in the world. You may not be believing that the largest spectrum of thermal hydraulic facilities which were built for advanced reactors probably is in BARC. Today it is existing. And that happened for a spectrum of natural circulation loops, for high pressure natural circulation loops. The second one, if you see the parallel channel loops, this is something where we could engineer the neutronic feedback, the reactivity feedbacks on the natural circulation behavior. This was, this is probably the third facility in the world having such features. And similarly, to study the heat transfer, fluid mechanics behavior, of many other aspects of the advanced reactors were shown here. And towards that, if you see yesterday, we had a small presentations about the sensors and components which are developed. The most important is the instrumentation. Believe it or not, India is one of the countries probably in the world, I would say that, which work in the high-tech areas, but we import almost all sensors. It's very, very difficult even today. Suppose I say, let's build a thermocouples, which having a, let us say, I'll say that I said it should be something like micron size thermocouple, which probably may not be believing. In 1990, I developed myself in Japan when I was doing PhD, a micron size thermocouple, 25 micron size. Today, it's very difficult to develop here. So towards this, many sensors were developed in BARC itself. One of them was the void fraction sensor in a pipeline. When there is heating, the steam bubbles forms. What is the void fraction in that? So there are many in-house technologies like conductance probe, capacitance probe, impedance probes. Also using the beam lines of Apsara reactor, these void fractions were first time measured in the country. And also, if you look at the two-phase flow meter, it's very, very difficult to measure when the flow is in the two-phase. There is the steam, liquid flowing together. Very in-house, I thought the high technology, two-phase flow meter was developed in-house. Similarly, to find out, suppose there is an accident in the reactor, whether steam is coming out, specific sensors to diagnose loss of coolant accident was developed. And believe it or not, first time probably in the world, passive valves were designed, developed, and fabricated in the system to address the components issues of advanced nuclear reactors. And the next thing I'll say that what I'm showing here is the history here. First time in the country we could measure the critical heat flux in a nuclear reactor fuel bundle, which was electrically simulated, heated, on the full scale, I'll say that full pressure, temperature, and actual full length of the bundle. So this is something we made history. And this is another area which I was talking about, knowing how the flow distributes inside the fuel bundle. Okay. And currently, we may not believe that computational fluid dynamics is still handicapped to find out or to predict what is the individual fuel pin temperature, especially if there is some boiling occurring. And towards that, this is also first time in the country such a facility was built where we can measure the pin to pin, the flow movement, the void distribution, the temperature distribution inside the reactor fuel bundle. And this is the next thing which I want to say, that very large scale, full scale test facilities simulating one-to-one condition of the reactor was built to understand the hydrodynamics, the heat transfer, the safety behavior of the reactor under normal operation as well as under accidental conditions. And for to simulate the nuclear heat, if you see down the line, this is the actual one-to-one fuel rod simulator. Very few countries in the world have these technologies where you can simulate through electrical heating the nuclear heat. And also at Tarapur also we built a full-scale facility of one of our advanced reactors called ASWR here. And then also the right side, if you see, a full-scale containment facility was built, and the primary heat transport system has been directly communicated to the containment facility where we create the loss of coolant accident and study the integral behavior of this reactor under normal operation and accidental conditions. The containment response to accidental conditions could be experimentally simulated. And coming to the severe accident is a much more complex behavior. And the severe accident means the reactor core melts down. It's called corium. Corium means it's a complex mixture of reactor fuel, like the uranium itself, the structural materials, the zirconium. It becomes a complex mixture. And the temperature is very high, of the order of 3000 Kelvin. And if you have to retain this material before it comes out and really aggravates the concrete, the vestment material, it has to be retained in a specific device called the core catcher. First time in the country we developed is a device called core catcher device, which could retain the molten corium and cool it and stabilize it for a prolonged period. That is one thing. Second thing, after especially the Fukushima accident, there was a rigorous requirement that we must bend the containment. And in that case, for example, the moment you go to bend the containment at high pressure, the radionuclides in form of aerosols are going to be released. And for that, we developed from first hand a technology called the filtered venting system, having the capability to scrub the radionuclides was developed. And this is a very, very, that state-of-the-art technology in the country. And towards the development of core catcher, again, I'm saying there's something, the science and technology both are involved here. Because what basically in the literature you may be knowing, how the uranium dioxide or uranium zirconium mixture, especially at certain temperatures until melting, its physics is known, chemistry is known, thermodynamics is known, material properties is known. But the moment other materials mix with them and you want to retain them inside a core catcher, you will not believe even a single thermodynamic data may not be there because it's such high temperature, it's very difficult to measure, it's radioactive in nature. So first time in the, I'll say that in the country, or first time in the world, I'll say, we could melt a very, very surrogate material of the corium using thermite reaction. Okay, we melted Syria, which is a surrogate of plutonium, zirconia, and the stainless steel, and other structural materials, 550 kg. And the left side is a very specific sacrificial material which was developed in-house, and we could demonstrate that it can cool, retain the molten corium inside a core catcher. After the Fukushima accident, there was a very big question, especially on the safety of PSWRs under severe accident conditions. In fact, you will not believe there was a lot of international assessment. The last barrier is the calendar of the PSWR. If it breaches, then the containment fell early and radioactivity can be released to the public, demanding early public evacuation. This was a very big question. And the only way to prove that is to do one-to-one experiments in PSWR conditions by demonstrating that we can retain tons of molten corium in a thin calendar vessel by cooling it outside. So many experiments we performed. Those are very, very, very challenging experiments, melting simulated corium at temperatures close to 3000 Kelvin and half a ton molten material, push it into the calendar vessel, cool it from outside and demonstrated. This was, I'll say that this made a history. When you tested and demonstrated, now the PSWR safety under extreme events, which can lead to core melt, I think that issue is resolved. Next thing, this is something I wanted to sensitize, especially with regard to a presentation from IMSC yesterday, that we do, I'll say that world-class mathematics. We can predict what is the sun's temperature, but it's very difficult to predict in case nuclear reactor accident, how much hydrogen is now occupying at which volume. Why, I have not understood. If we're so good, then we should have applied or developed the mathematics to such an extent that the computational code should be well developed to answer this aspect. This is something I wanted to sensitize our mathematicians. So we have done a lot of CFD simulations, especially for boiling phenomena, to apply it to, I think, specific events, accidents in nuclear reactors. But everywhere, the problem is that most of these computational tools are imported, and we cannot do any value addition even on that. So that is one part. Second part is, when you go to boiling problem, the number of constitutive equations really increases for mass, momentum, and energy. And to solve them from first principles is extremely difficult. And worldwide, all these numerical algorithms, believe it or not, are developed by mathematicians. And then through, I'd say that those who are experts in software, they will write. So this part, something I think if it can be done under SBNA umbrella, it will be good. Okay, so that is one part. Second part, what I want to say here, there is a state-of-art development in CFD, especially with the applications to boiling phenomena, to severe accident phenomena, or even other aspects of nuclear reactors. We have been doing a lot of studies have happened. This is something very interesting, the nanotechnology. Nanotechnology, I will also conclude with that. We started the effects of especially nanomaterials on nuclear reactor safety, assessment, even on performance. Believe it or not, very, very small concentration of specific nanoparticles can enhance the critical heat flux margin by 2 times. Means from the same system, I can extract 2 times power. So this is a very, very novelty, what we could find. Also, for advanced nuclear reactor system, when I was talking about the natural convection and all, the flow instability is completely died down. And the flow also is increased several times. And another very big issue in nuclear industry or even other industry is the water hammer effects. In case of there is water hammer, it's known that many components gets destroyed. So what we found, this wonderful material, if it is injected into the system, the water hammer is completely eliminated. This is another surprising thing. So a lot of R&D on this work has happened. Next, a part of which I want to sensitize here again, especially when you look at the decarbon energy sector, one is we are going for decarbonize. That is one part. But then we have billions of tons of CO2, which is already there that has to be captured or till they are getting released. So rigorous R&D should be taken up today itself to find out how to especially capture the CO2, which is already in the air or which we are still releasing through specific technologies. And there is worldwide only one country and there is only one plant, carbon, which is, I'll say that coal-based plant, which has only one, I'll say that, device for the CO2 capture. And because of that, believe it or not, the cost of electricity is almost double. So it is not feasible. Okay. So we have to find out technology which is commercially viable and easily implementable. And that would require very, very specific solvents. Some we have found out, but again, I'm sensitizing, very, very specific solvents with a high absorption rate, low cost, low volatility, toxicity, and very, very ancient manufacturing. And all that we learned from nanotechnology, even the scrubbing of the iodine, which I was talking about before, this can be engineered. And then probably it's possible in a couple of years from now, we can have an engineering solution, a commercially deployable device for CO2 capture and storage. Then this is something we have started very recently on the small modular reactors, basically to accelerate the nuclear power growth in the country and to have a specific technology which can be utilized or which can be put in the retired coal plants. So for that, the research and development areas are many folds, which probably we have never worked out. For example, one steam generator, which I have shown here, is a compact steam generator, helical coil. The tube side, there is superheated steam, outside boiling. Believe it or not, what is the pressure drop in this? What is the heat transfer coefficient in this? We cannot predict from first principles today also. So this is something I'll say that, like that, there are many problems, but this is one just I want to sensitize you. And what today it drives to go for small modular reactors are many, I think I have listed here. So this is important, and I'll say that immediate area one has to work on. And there are a lot of opportunities for research right from design, the process design, the little, I'll say that mechanical design, the manufacturing science, the safety assessment. The Indian molten salt breeder reactor is definitely the front runner for our third stage program. And third stage is not very far away, maybe in another 4 to 5 decades you should shape it up, provided we finish the groundwork. And the groundwork, there are a lot of R&Ds involved, right from material development and its qualification, because the temperatures are very high. The aggressive material which it is using, highly corrosive material, so that is the material development itself is a big. The second thing is the molten chloride, which is used as a fuel. This itself is a very complex fluid. And nobody will share you any information about its transport behavior, its heat transfer behavior, its fluid mechanics behavior, and how you are going to separate even the actinides from this online. This is another for going for online processing of this. And I will say that a lot of R&D is going on in BARC with regard to material, corrosion behavior, reprocessing and all. But then we all have to tighten our seat belt today itself. If we want to really see by 2070 or 2060, the third stage of the program is really driving the nuclear power in this nation. And towards the physics aspects of a lot of studies have happened here. Really, you have to salute, or we salute to our reactor physicists. And that happens right from the nuclear cross-sectional data measurement, generation, benchmarking, and a lot of computational tools have been developed here in BARC. And that includes the deterministic methods, the Monte Carlo techniques, and indigenous codes like ARC, thermal hydraulics, Excel, and so on. And many of these also have been validated because they have also built state-of-the-art critical facilities where different types of fuel can be tested for the neutronic parameters, including the reactivity parameters, and validated. And towards this, I'll say that the several computer codes have been developed, which already I have spoken. And book also has been written. It is because our VC, Professor Vasudev Rao, he is the big driver for writing books for HBNI, and one of these has been written by our colleagues on physics of nuclear reactors. And 4 books we wrote, especially after doing so much research on advanced reactors. One is on natural circulation, one is theory of energy for the future, one is computational fluid dynamics for nuclear reactor design, safety, and very recently we wrote a book on severe accident on nuclear reactors. These are all dedicated to HBNI. The nuclear materials, as I said, is the backbone of a nation. If a nation has to develop, it has to be, I will say that, very, very strong on materials, metallurgy development. A lot of work, of course, is happening within BARC, right from different types of materials which develop, the processing, characterization, modeling, and also they have built many facilities, which I will be showing you to characterize them. And then this whole application is to several nuclear reactors, right from our PSWRs, 220, 540, 700, IMSBR, the materials is being developed by them, even for the fusion reactors and other heavy water plants. So this is the list of, already have spoken about this, and the activities range right from understanding the phase transformation, degradation and joining of materials, and developing of process materials for different applications, and understanding new phenomena of materials under various conditions, structural behavior, and the methodologies of their extraction, synthesis, characterization, and processing. This is the, I'll say that, broad view of the different facilities with the materials groups having, right from ACM imaging, then X-ray diffraction, hydrogen charging, fatigue, creep and vacuum facility, and so on. So it is open to not only to DA units, also many outsiders also come and do measurements here. And on corrosion studies, there are very dedicated facility called high temperature, high pressure recirculation loop facility, simulating nuclear reactor conditions, and autoclave, the laser Raman, and so many. Then for microstructural and surface investigations, there are TEM, high resolution TEM, energy filtered TEM, scanning electron microscope, and so on. So many facilities also is having. Then for processing of materials, the lead litmus for circulation loop, then melt spun for RSP ribbons, hybrid laser welding facility. Okay, this already I have spoken. Then there is a very new technology which has been developed by Energy called the induction melter. Just state-of-the-art technology itself, used for production of specific glass materials for our back end of the fuel cycle. This technology is ready for the transfer. Now coming to the chemical engineering, they do hardcore research from fundamentals right from the molecular level or molecular scale modeling, experimentation, and also applications for two areas. One is, as I understand, development of specific materials for nuclear industry and other applications. And second thing is just 2 minutes, membrane, very typical membrane they develop for the desalination. So first is the R&D in microreactors and chemical microprocessing. So they develop also very precision pumps for micro scale measurements, very small flow measurements, and micro channels and microfluidic devices, high speed imaging system, DLS particle analysis. These are the facilities they have. And they develop very novel solvents and conductors for various applications. And because of time, I'm not going hard so much with this, but a lot of facilities they have which can be utilized for solvent and solvent extractions and conductors. Hydrogen production, purity, separation is another important area, especially if you look at for a decarbon energy sector, we need to have a lot of hydrogen, especially clean hydrogen, green hydrogen production. Towards that, okay, I think I have been one to complete, so I'll go to my last slide. I'm sorry that I could not give justice to chemical engineering department. Last slide, I'll speak, which is my vision, which something you people can take away if you agree. The first and foremost is the nanotechnology. And nanotechnology is so important because today's energy conversion efficiency is poor. And what we read probably 100 years back is still continuing, especially if you look at nuclear industry. So something else has to happen. And probably fission science has to take a new route through a different technology so that we should have a much larger efficiency. Today's efficiency of the order of 30% from fission, energy, whatever heat is produced, and what is converted to electricity. And this nanomaterials probably will play very important role for enhanced heat transfer, ultra high strength. Can you imagine tomorrow we should not have a building like this made of tons of concrete and steel? Can you imagine we should have a paper thin building having the same strength of concrete, same strength of steel? Can you imagine? Probably this is something can come out through nano composite materials. And of course, what I said about carbon capture and storage is very important. We don't have time, we have to address it. Then high density energy devices. This is something very important because renewables are coming. They have the cycles, energy needs to be stored. Dry cooling technology, world is like what? Sometime back we heard about how many millions are going to suffer because of cancer. But let me tell you, there is another much bigger crisis than energy, is the water crisis. If you evaluate the water availability per person for India is exponentially going down because of the large population. This is something one has to address. Then materials for ultra high temperature, heat pipes, efficient thermo energy devices, hydrogen storage and transport, this needs to be addressed. And one thing I wanted to ask you, to all of us, low dose radiation hormesis. This is something I'm sensitizing to everyone who is sitting here, or all nuclear scientists and engineers, that low dose radiation is found to be very, very beneficial for health. On the other hand, even though there are thousands of studies, books have been published, the dose criteria has been made by some regulators with some numbers, which do not conform to the, I'll say that the hormesis effect. A lot of R&D has to be done, and then that will remove the fear of radiation in the public mind. And last but not least, it is already spoken, the artificial intelligence for advanced diagnosis, minimal operator actions, control and safety of nuclear reactor. Sorry, I exceeded my time. Thank you. Thanks SBNI for giving me the opportunity to speak.
Okay, thank you, Dr. Nayak. Only one quick question. Anybody? Okay. Oh yeah, one.
If there is a question from anybody else, we can go to them. Otherwise, I have just one or two observations. You mentioned very interesting point about how nanomaterials dispersed in the coolant can increase the heat removal capability. It's a very, very interesting topic, and I just want to add to your statement. This was considered even in the case of sodium. People believed, and there is a patent on it, that adding nanomaterials to sodium can reduce its reactivity with water, make it more safe. And there is a patent on it, there are publications on it. But fundamentally, this has been discussed earlier also. One question which is asked by many safety people, that you are to demonstrate that this nanomaterial will not coagulate at some time and completely take back the property originally. Okay, this is my comment. But there are just one more comment is that you mentioned a few topics where I felt there can be good role for mathematics. For example, one you mentioned about probabilistic safety assessment, and you also mentioned about reliability analysis. And there was also another interesting mention about human behavior simulation. So there are, I think, strengths available in other institutes of HBNI where some of these could be addressed. I wanted to know your reaction.
Yeah.
Sorry, 1 minute. I understand it's getting delayed. I think probably you may not be aware, or probably we are aware. I think when Grover Saab was director of SBNI, he took, I think, a mammoth action that solving real life engineering computational problems by mathematicians. And if you look at the mathematicians, they want to live in a basic mathematical world. And this applied mathematics, somehow they have some hesitations, like if you ask a physicist who works on atom and let us say subatomic level, ask them to make a device for welding of two components, probably he'll have hesitation. No, I don't want to penetrate in that. Probably that barrier that ice we have to break. I think Professor Grover Saab must have much more experience than me. So this is something that ice has to break. Sorry again.
Thank you once again. The last topic is on Professor Shishir Deshpande from IPR. He will be speaking about physics aspect at IPR. Professor Pandey, please.
Good morning to all of you, and I thank HBNI, especially Professor Vasudev Rao, for this wonderful opportunity. This is going to be a very different meeting because we will be able to listen to these talks again and again with our students back home. So we have really retained knowledge here. I'll talk about IPRs, somewhat on basic activities and some engineering activities. My colleague Suryakant Gupta had given you a wide overview of plasma's diverse applications to sustainable development. So I'll take the other line, and this is a graph from the website which shows the various areas IPR engages in. And we'll talk about tokamaks, basic research, and fusion today. So these are the activities that we do. Plasma physics of tokamaks. Tokamak is a magnetic bottle which contains plasma. It has gotten into prominence because of its tremendous ability to hold high density, high temperature plasma for a long enough time. From the physics perspective, plasma waves, turbulence, complex systems, nonlinear dynamics, etc., is the broad portfolio going all the way down to directed research in fusion and ITER. And we have a number of experimental facilities that I will show pictures of. So in transport, the important things are, how do the electromagnetic fields, the geometry, the atomic physics, the boundary conditions, anisotropy, the gradients, how do they impact transport of particles? And as you know, in tokamaks or in magnetized plasmas, transport of heat by electrons remain anomalous and ununderstood for a very, very long time. Waves have, never dying interest in any system, and plasmas are no exception. In fact, they enrich these waves because the plasmas produce electromagnetic fields which influence the plasma's dynamics itself. So there are cases where waves can influence waves, create cavitons, for example. Wave breaking is another area. Instabilities and turbulence is another major area here. And not only by experiments, but by high-tech simulations, we approach the problem of turbulence, self-organization, and critical gradients. In tokamaks, long pulse operations are desirable because they have to become reactors one day. Controls must be learned, how to manipulate the plasma in different shapes, for example. Understanding transport and confinement, understanding disruptions, and in certain cases, enabling technologies, we need to introduce heating and current drive for the steady state operation of the tokamaks so that they become fusion reactors. So to accomplish that also, there is a ladder, step-by-step ladder of research that one has to establish. And there are large facilities coming up for those R&D as well. Finally, the tritium breeding is essential because a tokamak reactor's most important attraction is that it can breed its own fuel on the fly. And so R&D for that is necessary. Plasma-facing components like tungsten need to be understood in depth because the fuel, the neutrons, the gamma, everything is bombarding the plasma-facing component. We need to understand irradiation effects and whether the materials will survive in the long term so that we have a truly long pulse reactor. There are some other things as well. So in basic research, experiments, theory and computation, let me just show you that we have this large volume plasma device where we study Whistler-induced turbulence. Dr. Avasthi and his team work on this. They developed it along with the previous team that worked on this. And this is important because, how the Whistler turbulence influences the electron's energy, how it changes the electron energy distribution makes a huge difference. It could be of tremendous consequence to understanding the dynamics of energetic electrons in the Earth's and other planetary atmospheres. The multi-cusp plasma device is an interesting and a very challenging system. Here, the team is trying to create an ultra-quiescent plasma where, except thermodynamic fluctuations, no other fluctuations would remain. And this attempt is ongoing, and they have good results on that. So the important thing is, if we can understand what is the lowest level of fluctuation we can have in this system, we can then understand the fundamentals of how perturbations grow and decay in such systems. So it's like creating an ideal plasma. The helicon plasma experiments are where a few tens of megahertz waves interacts with the plasma. And the exciting thing here is that the polarization of the wave post-launch is changed by the plasma. Something that it was not heating the electrons, for example, is converted into heating the electrons. So there were many surprises in these experiments and the nonlinear behavior of the plasma. I'm showing you those facilities where young students, PhD scholars, faculty members from other places could come and join, work together. Inverse mirror plasma experiment device is another device where people are studying plasmas at high magnetic fields in the center and lower residual magnetic fields at the edge. This is exactly the inverse of a mirror, where we have low magnetic fields in the center of a device and high at the edge. And the turbulence in such systems has different characters. And therefore, it is a rich system for the students to look at the waves, their evolution, and how they break, for example. The applied plasma physics experiments in a device called Apple is another exciting experiment where one can create beams within the plasma in such a way that there may be a possibility of observing what is called a lane effect, where in an otherwise crowded place, people try to form lanes so that they can move fast. So it's like plasma discovering a new state of self-organization where the transport by the plasma particles and heat can be discovered by the plasma to be much larger than what it would have been. So it's like finding out whether plasma has various other tricks in its bag in understanding transport. The SmartXC is a unique experiment where pure electron plasmas are produced. It's a torus, and it has created a range of achievements. And one of the latest is that it is apparently an incredibly long confinement time. There are theoretical works which indicate that long confinement times can result in pure electron plasmas, but we haven't yet understood fully why. So, in short, turbulence, waves, nonlinear dynamics, complex systems, exotic plasmas form a very exciting portfolio for the students in basic sciences. And these actually are connected inter alia to directed research in Fusion 2. The range is amazing because for example, large volume plasma devices, the gyro radius may be order of millimeters, but in some other devices, it will be sub-micron scale. So one is able to span, in fact, a vast scale for the same parameters, and thereby generate an understanding of the fundamental constants and possibly certain conserved quantities, which are sort of pan scale. So let me come to the tokamak physics. We have these basic experiments, basic experimental toroidal assembly, the first device that was made in almost 1982. This is a currentless toroidal device, therefore it differs from the tokamak in the sense that there is no current in this device. But there is still a strange confinement, and there are a number of interesting studies on why open field lines like this, along with the plasma and an electrostatic bias thrown in, can hang on for such a long time. The important things has been discovering turbulence and waves in this device, especially how the waves interact with the plasma. This has been before Aditya and SST1, and this was therefore one of the first, hands wetting exercise on the toroidal systems at IPR. Aditya and the Aditya upgrade are the workhorse. They have worked, there's a whole team which worked with Dr. Ghosh on confinement improvement, instabilities, turbulence, transport, disruptions, shape control of the plasma. And this system has now number of PhD students working on it. So this is a place again to look forward to practice, operations and learn for the future reactors. Similar is SST1, where the difference is we have superconducting magnets and therefore a potential for long pulse operation. So the struggles to get it working to those long pulses is exciting because many systems have to work together and a current has to be driven by waves rather than by a transformer action. And coupling of this RF waves of few gigahertz to a plasma is a challenge because we are talking about large powers of the orders of hundreds and sometimes megawatts. In such cases, removing the heat and the particle in a steady state manner will also be a major thing. So this experiment takes us from basic science to the complexities of thermal and other engineering, vacuum systems. And if we were to use, in full fusion reactor, a deuterium, tritium fuel, various chemical and other separation methodologies to bring back the fuel which has not been burnt back into the reactor. So a fuel cycle also will need to be developed one day. The next, so to say, kid on the block will be the small scale spherical tokamak. This is being built. It is in the state of procurement. The exciting thing about this one is that it is a small aspect ratio tokamak, which is say 1.75 compared to around 3, which is there for Aditya, and almost 5, let's say, for SST. Now, what makes a difference here is that for small aspect ratio tokamaks, there are some very unique properties. For example, there is natural elongation. There is a resistance to disruption. There is a natural diverter for exhaust of particles. There is what is called a homogeneity, which means there is a uniformity of the absolute magnetic field. And this lends it terrific properties in terms of exploitation. You can have large currents driven by the plasma, within the plasma, by plasma itself, because of the friction between trapped particles and the untrapped particles. Now, this direction takes us to compact reactors. This is a new thing which is opening, and a number of institutions are now pursuing this line of attack as well. We are also ourselves designing a set of codes which will explore the parameter space of these reactors. The challenges in these reactors would be high heat flux on the diverter because of the small size, extreme neutron flux, and because again of the small size, no chance of putting any transformer coils on the central zone. So we will have to depend on wave-driven currents. And that's why this whole area of wave-particle interactions, wave-wave interactions becomes so exciting. In the next step towards fusion, we have several facilities for studies on blanket and blanket materials. A blanket is basically a let's say, a layer of steel and lithium ceramic composites surrounding the plasma. The neutrons from the fusion reactions impact the blanket. They interact with the lithium, generate the tritium. And they also are to be shielded. So dedicated special materials were developed in collaboration with the DAE institutions, VIII, IGCAR. And we have an Indian version of the reduced activation ferritic martensitic steel that can be used for making the test blanket modules. Although we have not done the irradiation properties of this, which is the future, the other properties seem to match very well with its other counterparts, for example, the European and the Chinese. The material property database needs to be built using fission reactors, and preparations are afoot for that. The ceramic materials based using lithium is just one route. There is also another route of making liquid blankets, liquid metal blankets, by using PBLI eutectic. And India has a concept which has gone through the conceptual design review accepted by the international community. And that concept is also ready. So should there be a need, a state of readiness prevails in taking the design further. Then, of course, there are some important thermohydraulics, and to carry out, a 80 bar helium through a hot component and ensure that it is cooled. Make sure that the temperature windows are between 300 to 500. Make sure that the temperature window is maintained for the structural materials. Requires a demonstration, and such loop has now been is getting commissioned in IPR as we speak. So this would be another exciting area. In the interdisciplinary work, we have, as I said, need of qualifying materials. And for example, the tungsten material, we have irradiated at different facilities, gone through the analysis of the post-irradiation experiments, including transmission electron microscopy, X-ray, positron spectroscopy in BARC, and shown that what kind of clusters of defects form by which kind of radiation. Of course, these were done with ions, and now the next step which we are taking will be through the fission reactors. Similarly, the problem of the fuel getting trapped in the plasma-facing components is outstanding. The fuel gets trapped because there is a simultaneous bombardment by neutrons, by helium, and by the fuel atoms itself on the plasma-facing material. The subsurface implantation, the inverse diffusion of the fuel make a great difference to how we will operate that reactor in long pulses and whether one will be able to control the density in the plasma, because the wall itself will start releasing the fuel in an uncontrollable fashion. The regulator will worry about fuel being retained, especially tritium being retained in irretrievable deposits. So those will be the outstanding questions which are actually easily intersected in the basic sciences, because you're dealing with transport of hydrogen isotopes in metals. But it is a complex problem because it requires those samples to be at high temperature under simultaneous loading by different irradiating components. In the mega science category, we have a part to be played in the LIGO observatory to be built in India. And in IPR, there is a system being made which is almost the size of the original LIGO, but on a much smaller length, but containing all its essential components. And some of these deliveries which have been done to RRCAT. So there is a joint work. And this system will tell people, how to handle coatings, whether they work, what is the effectiveness of these things, how to handle this system as a whole, because this will require a complex assembly And this pipe that you see is 20 meters is actually going to be eventually 4 kilometers one way and 4 kilometers the other way at right angles. So before all that comes up, this will become a nice training ground for engineers, industries, our people, new people to see what exactly it takes to put things inside this kind of a tube. So I have chosen a few highlights at random. I'll just sort of run through them in terms of the last couple of years. So we have reports of a new mechanism discovered for direct coupling of the laser energy to ions. It's a novel mechanism. It has impact on the direct drive of fusion because the way a solid pellet absorbs energy can be very complex and is subject to a number of instabilities, especially the relativistic instabilities. And if we understand in depth how plasma, electrons, and waves interact, especially extremely dense plasmas, then we might be able to circumvent certain bottlenecks in the efficiency. Then boundary-driven unconventional mechanism for magnetic field generation in beam plasma interactions has been not only proposed, it has been simulated and experimentally demonstrated. The nitrogen seeding of the plasmas has been shown to affect turbulence. This has impact because these experiments were also done abroad, and it seems that injecting the nitrogen gas within a tokamak plasma boundary changes significantly its edge character. And this may have to do with its particular ionization states and the way it interacts with the boundary plasma, the radiation. Then wave breaking in warm plasmas. There is a limit coming up in electron temperature beyond which these waves do not break. And therefore, it means that if these waves don't break, they could continue to take away the energy and the particles in the matter in large, probably relativistic jets to great distances. That may give you a new mechanism of transport of energy and matter. Similarly, there is another result in the cold plasmas, but relativistic case, where certain waves which were thought to be stable are no longer unstable. Even a small amplitude perturbation, longitudinal perturbation seems to destroy that. So those were some interesting discoveries in this area. The laser cluster interactions have been modeled. There are experiments at TIFR on which our team collaborates. There are first experimental observations of pinned solitary waves, which means if an object, a charged object, moves in a plasma at supersonic speed, it would carry along with itself a solitary wave, which is a large amplitude, steady wave. And this could have great impact in cometary debris, in planetary science, where charged dusty particles can move at great speed especially in the area where Earth and Sun boundary exists, could give you an early indicator of warnings, for example, because those waves can be detected. Then there are some steady state toroidal electron plasmas where with a very specific initial condition evolved from maximum entropy mean field solution as an initial condition have been shown to be confined forever. And this is a very interesting result, which will also be tested experimentally as we move along. The electron hole instability as a primordial step towards sustained intermittent turbulence in linearly subcritical plasmas. Here, we are dealing with a system which was linearly damped, but seems that can still undergo turbulence. So systems which are apparently stable could be driven unstable. nonlinear effects in bounded dust vortex flows. These are results applicable to a very wide range, right from the Jupiter red spot to even intercellular activity. We have a high performance computing center. I'll show you a picture of that. And this is getting pressed into answering certain questions like when noise or fluctuations dominate, how does one achieve a directed walk? And it is shown that a ratchet and pawl mechanism is at work due to asymmetric forcing, which can convert an apparently chaotic motion into a directed motion. There are a whole lot of works on the 2D Yukawa systems, which range from turbulence, which range to, let's say, flows, things like generation of the magnetic fields. So a whole lot of high-tech computing is supported by this cluster, which is a petaflop cluster, ranks very high, and a whole lot of users available. And it is open, provided there are exciting enough problems coming from other people and institutions. So we have a large uptime, and we are backing it up with a much larger software controlled database soon, which will be totally user transparent and hardware independent. So a whole range of applications run on this Antya cluster, which is like 10 to the 15 in Sanskrit, right from space and fusion to artificial intelligence and basic sciences. So I'll thank a number of colleagues who have given me these inputs for this section, and let's move to fusion ITER and test. So we know tokamaks. They have been in the hope for a while. But what is important is their credibility. You can see that over a period of time, a very strong database has now led to the credible projection of energy confinement time for a size like ITER, about 3.5 seconds. And this makes a tremendous difference because it brings down the power required to create fusion. That is why we have these large capital Q numbers for ITER. ITER construction, as you know, is shared. It is being made in France, and around roughly 9 to 10% portion is contributed by all except EU, which takes almost 45%. So this tokamak is complex, many components, and India supplies 9 packages to ITER. The ones on the left that you see are we are dealing directly. We have to supply these components. And a good many of the components required for the first plasma have either been supplied or been installed. Some R&D specific components are coming up next. And the red ones are the ones where we need to invest so that we are able to make our own reactor in future. So here are some pictures of this manufacturing phase, installations. And this is the important thing, that the R&D for some packages which I have listed here will continue to happen in the lab, and therefore it is a fertile ground for scientists and engineers from other CI to come and join ITER India lab in Gandhinagar and do some exciting work. So there are different phases, and this will be true for any mega science projects. So basically we will need scientists, engineers who can specifically address the issues and prepare themselves for all these phases, because this is what we will need in future. So I thank the ITER India team for this. And in summary, IPR has several experiments ranging from turbulence, transport, confinement, instabilities. nonlinear dynamics, complex systems. And this is the, I would say, the broadest portfolio we can have for a whole range of interdisciplinary scientific collaboration activities, including national, international, and mega science. A range of theoretical and computational plasma physics and physics exists. We have this Antya high performance computing facility supported by a newsletter called Gananam. We have these two tokamaks where students work, and ITER India, and LIGO related activities are happening at IPR. So in epilogue, the big question is, how does one continue these activities in future? Because we see around us a dwindling population. So a robust succession plan to truly celebrate this International Year of Basic Science is needed. Faculty members who can channel these freewheeling energies towards directed research and induction of new members will be needed. Otherwise, we won't be able to retain that knowledge because it lives in people, not just documents and drawings. So collaborations and synergy, and of course, long-term planning are essential if we have to make a niche for ourselves. So thank you. I have not been able to cover a few areas, but that's because of the lack of time. But I really thank a number of people at IPR. And thank you, HBNI.
So we are already late, so a few quick questions. Please.
What sort of research backup you provide to ITER at ITER India?
We have facilities and we have projects. So some of the projects come also from ITER. And so the computational facility exists. So the guidance, computational facility, library, and computing, these are all possible. And there is a program called BRFST, which is Board of Research for Fusion Science and Technology. So there is a yearly program of interns. So universities and industries can join that program and develop those critical directed technology components also.
Yeah, I have a couple of questions. I mean, you mentioned that the Indian contribution is 9.1% to the total ITER fund.
Yes.
In absolute terms, how much it is approximately?
It will be close. If you take the total, there are two pieces in the Indian contribution. One is the in-kind, other is the cash. The cash is called cash, but basically it is for the management of the ITER facility itself. That is their salaries and their contracts and their procurements. So total would be close to 15,000 crores spread over, say, around starting from 2007 to let's say around 30, could be around 20 years or so.
Okay. And the whatever is in kind is being built in India or mostly, or it's kind of purchased from abroad?
No, today there is a huge contribution only from India. There are only certain cryogenic components, but there what has happened is that an order outside there was an order inside. So our people also made up to that level. In certain areas. There are certain things which, are impossible, like, you can't build those magnetic bearings and the truly high-tech stuff. But I think those really come into directed research. If there was, levitation bearings and at ultra cold temperatures, one could design that would be so nice.
Okay. And most of the people who are engaged in India ITER part,
yes,
are from IPR?
There were 50 people from IPR And there were about 120 which we could take as project staff, but long-term project staff from India.
Okay.
And then there is a whole lot of industries in India, like, L&T, Avsarla, Inox.
Okay. And my last question, I'm just curious, out of this 50 plus 120, say 200, 150, 200 people, what percentage is physicists?
The number of physicists is small. I would say it's about 25% to 30%. Others are engineers.
Okay, but it is only, mostly you need engineers. It's the requirement of physicists is more at this.
No, it is more, because the problem is that in this complex system, you need someone who will connect the ITER specification to engineering specification. Okay. Like if you want to change something, then someone needs to know what is the impact of that. So, if we go by the engineering mind, it's about precision, getting things done. And in the physics, what happens is that there is always this, if you, for example, if the nuclear loads are not 20 kilowatts,
I understand that, yeah.
Those are.
Dr. Bhattacharya.
Yeah, sure.
We
Yeah.
can talk during lunch time.
Yes,
So
okay.
I have one small point that
Yes.
you told, other than cryogenics also, there are some RF, high power RF
Yes.
tubes are also, you are procuring.
Yes, we had to procure the, let's call, what is called dichrome or tetrode tubes.
Yeah, dichrome. And another point is that 15,000 crore is escalated from 3,000 to 15,000, right?
No, the 15,000 crore is actually the original cost, but that original cost did not have certain elements. It was a partial cost. This 2,500 crores that you are referring to, the original was with certain exclusions, because at that time the agreement was just signed and no one had the idea of the cost. But remember that the costing at that time belongs to the 2001 baseline. So.
Okay, thank you. Thank you once again, Professor Deshpande.
On behalf of HBNI, I express my sincere thanks to the session chair, Professor Som, and all speakers. We will now break for lunch and meet back at 2:30 p.m. for the remaining two sessions. Thank you. Institute of Physics, to chair this session. I hand over the rest to you, sir.
Good afternoon. One online and two offline. So first speaker is Oishee Chakrabarti from SINP. So I invite her actually to present her talk.
Good afternoon, colleagues. It has been a wonderful experience listening to all of you from the entire HBNI fraternity. Today, I will take you through the activities of the Biophysical Sciences group at the Shah Institute of Nuclear Physics. During the course of the talk, I hope I make it clear to you that we do directed basic research with a potential of translation. So what comprises our group? We are a group of scientists who specialize in cell biology, mechanobiology, synthetic biology, mass spectrometry, structural biology, with emphasis on NMR, EPR, X-ray crystallography, nanomaterials, and high-end spectroscopy. We have a group of 16 principal investigators, under whom there are about 46 PhD students and 6 research associates and postdoctoral fellows. So what are our goals? We utilize multi-dimensional cross-platform approach to understand some of the basic biological mechanisms that are completely deregulated during diseases. And what diseases are we talking about? We try to understand cancer, neurodegenerative diseases, and also infectious diseases. So during the course of my talk, I will try to impress upon you that cancer and neurodegeneration are basically two sides of the same coin. Cancer means uncontrolled proliferation, whereas neurodegeneration means uncontrolled degeneration and death. So let's start at the very beginning of life. A sperm and an ovum fuse to form a gamete. The gamete then divides into multiple cells, which are absolutely identical in nature in the zygote. From this identical group of cells, differentiate in specialized organs like the brain, the lungs, the liver, blood, etc., to make a complete human being. So proliferation followed by differentiation. And during the last days of life, there is excessive degeneration and definitely death. But death of cells is also integral to our development, because without cell death, we would have interdigitated limbs and like the duck or platypus, which we don't. Where we would have webbed feet and hands like the duck or platypus, but we don't. We have separate fingers and toes. So these are our goals. To address these goals, what facilities do we use? We have a mass spectrometry facility where we have a MALDI TOF MS, an ESI QTOF MS, and a GC-MS. We have high-end microscopes where we can do super resolution and high resolution imaging. And we have state-of-the-art microscopy facilities. So first, let me take you through the mass spectrometry facility. the GCMS, the gas chromatography mass spectrometry facility. So in-house, what do we do with this? We utilize urine and blood samples from patients and try to see the changes in metabolites that have occurred during the progression of liver cancer. How a normal liver, through the various stages of genesis of liver cancer, the metabolic profile changes. So these metabolites are generated in normal human being as well as a cancerous individual. The levels of these do not vary humongously, but the subtle changes are where our expertise lies, to identify these subtle qualitative changes as well as sometimes quantitative changes, as well as at times new qualitatively new metabolites are generated within a diseased individual. So this facility, the GCMS facility, which analyzes metabolites as well as lipids, is very heavily used by multiple institutes across the country, be it the Tata Memorial Hospital, ACTREC, BARC, VECC, hospitals in and around Kolkata, as well as the entire India, like even IMS, BHU. So do we do only cancer samples? No. We also analyze how malnutrition from either animal models or in children may be affecting their prognosis of cancer. Also, even plant samples like arsenic stress induced metabolic changes during root development or saline stress in soybeans is being analyzed at our facility. So there are many mass spectrometry facilities across the country, but the metabolomics specialist of our institute is sought at by various other institutes just because of the intellectual infrastructure that we have. This facility has also been used in the recent times to analyze how metabolic changes have occurred during COVID-19 infections. So in short, we are a facility which caters to a wide range of colleagues across institutes, across universities, across hospitals throughout the country. I must point out that the GCMS facility that we have at present uses samples in the soluble phase. We are now thinking of, rather, we are in the process of acquiring a new module where we can do inline gas phase gas chromatography, because that is quite in demand in-house by our colleagues inside the Saha Institute of Nuclear Physics, as well as by our neighbors in VECC. Now coming to the microscopy facility. The microscopy facility, as you can see, as you have heard throughout, that high resolution confocal microscopes are present practically in the institute of the country. However, many of our neighbors seek our expertise in analysis and imaging at the high resolution as well as super resolution. By super resolution, what I mean is that when in the high resolution platform, the imaging is limited by the diffraction limit of light of 200 nanometers, we can break that barrier and go down till about 80 nanometer resolution in the super resolution platform. Next come the spectroscopy facilities. The spectroscopy facilities, like the ones where like the Raman spectrophotometer, the single molecule FRET, fluorescence correlation spectroscopy, as well as circular dichroism, are utilized by multiple members of the institute as well as by many neighbors across the eastern zone of the country. The Raman spectrophotometer is actually built in-house. So far, I have taken you through the physical infrastructure that we have. Now coming to the intellectual infrastructure of the Shah Institute of Nuclear Physics. We are a unique research group. Here, we have been able to bioengineer bacteria and utilize the artificial neural network algorithms to actually generate intelligent bacteria, which can, where you can actually give a certain type of input, the bacteria can process it, pass it on to its neighbor, and give an output which is completely different from the input that was given. Very similar to a neural synapse. So thereby, we have devised a back-to-neural synapse. This has been covered by the Nature India and as an evidence for the first artificial neural networks with genetically engineered cells. This has also been actually covered by the IIT Madras magazine called Shastra. Similar bioengineered bacteria have been used in solving mazes. So this is one of the significant steps towards biocomputation. Our work has been acclaimed by the MIT Technology Review and multiple technology review journals to suggest that we have made a huge leap in our own way towards biocomputation. Wikipedia suggests that this is one of the, and Wikipedia also suggests so. Not just that, the bioengineered bacteria have been now used in a way that they are the inputs and the output comes in the annihilation of cancer cells. So this is one of the most unique facilities in the country, among the only few in the world where bioengineered bacteria have been used to actually obliterate and kill cancer cells. So now, following the cue on cancer, cancer cells undergo drastic architectural changes when they progress, like when they metastasize. So a normal cell naturally has a certain architecture, but when it metastasizes, it breaks through multiple boundaries, multiple membranes, for which it has to twist and turn in many ways. To understand the changes, architectural changes, we use mechanobiology approaches to understand how these changes, what these changes are. Not just that, we use machine learning and artificial intelligence to actually identify cancer cells from normal cells. I must say that this platform is now in the initial stages of patenting. Architectural changes happen not just on the cells, architectural changes happen in the connection of cells also. So coming back to our high resolution imaging, if you look in these two panels, they look very similar. The top panels, the numbered panels, the cells look very similar. But we utilize these cells, the images of these cells, to actually develop with the help of computational biology, we develop models to actually see what is happening inside these cells. And now in the lower panel, you can find that though they look similar in the images, they are actually very different. The normal cell and the disease cell actually look very different. So here, with help from computational biology, we analyze cells imaged on high resolution platforms. We also analyze images on super resolution platforms to see what connections between organelles inside cells are going wrong in a diseased situation. Not just architectural changes inside cells. The architectural changes happen at boundaries also. A cancer cell has to break through the basement membrane. A cancer cell also has to undergo changes in its own shape and architecture. So how are these changes brought about? So we all know that the information lies in our genes and chromosomes. And what are these? These are actually from the DNA. But think about it. A chromosome, which is about 2 to 3 meters in total length, is compacted, twisted and turned and stuffed into a space which is less than 10 microns. So naturally, it has it turned in multiple ways. And on these twists and turns, many different decorations or embellishments can be made. These are called epigenetic changes. So the epigenetic profile of a normal cell versus a cancer cell is very different. So we study how these epigenetic changes are brought about, how these landscapes differ, the changes which are acquired during metastasis, or how drugs which are targeted for cancer actually subdue these epigenetic modifications. Epigenetic changes happen not just in cancer cells, but also during viral infections like HBV or hepatitis B virus-mediated infections, which ultimately has a phenotypic outcome of liver cancer. The architectural changes, metabolic changes are further collaborate with signaling changes. So of late, in the last fortnight, you might have heard about the T2T consortium, or the telomere to telomere consortium, which has managed to now sequence the entire genome. The last 8% was posing to be a problem. Why was it posing to be a problem? Because it has a lot of junk DNA, as well as it has many repeats. So what are these junk DNA? The central dogma states that DNA makes RNA, RNA makes protein. But there is there are many anomalies to it also. DNA does make RNA, but not all RNAs make proteins. So the junk DNA that makes RNA, many types of such RNA. One of them are these long coding, the long non-coding RNAs. Non-coding because they don't translate to proteins. Now, what we have seen in the past is that many cancers have some signature long non-coding RNAs, but our colleague now has shown that with the help of systems biology as well as experimental validation, that many of these oncogenic non-coding RNAs also have signatures in Alzheimer's and Huntington's disease. So what are Alzheimer's and Huntington's disease? Like Dr. Gupta a short while ago said that our life expectancy has increased and the burden of many older age-related diseases like cancer have increased. Well, age-related diseases, one of the most important are the neurodegenerative diseases. These neurodegenerative diseases are kind of a taboo. We don't talk about them as much. But these are also slowly coming up in a way they would take the form of an epidemic pretty soon, like cancer. So understanding these long non-coding RNAs which have been established in cancer are now found to be quite important in these neurodegenerative diseases also. So epigenetic changes happen. Talked about epigenetics. I've talked about the junk DNA. Now let's take a look at how we look at the DNA. The DNA, as you know, is two strands are twisted around each other, rather plated around each other. But the DNA has to actually unfurl when when RNA is made, or it has to unfurl when new DNA strand has to be made. And that is done by many proteins. So many proteins crowd together around the DNA. And to unfurl the DNA, a bubble is made. That bubble can breathe. It can expand. It can contract. To understand what the mechanism of this expansion and contraction is, we use single molecule spectroscopy techniques to see how the bubble breathes, how the replication fork is made, and also how DNA repair mechanism happens, because the lack of DNA mechanism or faulty DNA mechanism, repair mechanism, is one of the hallmarks of cancer. Now, we use nanomaterials. We develop in-house nanomaterials and use them to actually see how the surface of cancer cells is different from normal cells. Not just that, we also use nanomaterials to specifically identify various serotypes of dengue virus. So if in patient samples, whether it is infected with dengue virus 1, 2, 3, 4, 5, we can use actually nanomaterials which can specifically identify these serotypes. The nanomaterials are also used in doing another smart thing. What is seen is that during neurodegeneration, lot of junk accumulates in cells. What are these junks? These are protein aggregates. So we can now design and make nanomaterial which actually prevents protein aggregation or breaks them. So it is one step towards a therapy. The next come the membrane proteins. Why should membrane proteins be important? So all of you know that we have had a legacy of X-ray crystallography in the Shah Institute of Nuclear Physics. But X-ray crystallography is primarily for soluble proteins. The membrane proteins are quite a different category of proteins. Think about it. They are proteins which pass from a hydrophilic environment into a hydrophobic environment, again into a hydrophilic environment, loop back into the hydrophobic environment, come out into the hydrophilic environment. And they do so multiple times, maybe 7 or 8 times at a bow. So they are quite complex, and to just get them into a soluble form would destroy their structure and their function. So to be able to actually purify these extremely complex proteins becomes economically challenging. We have devised ways where we can bring down the cost of purification 500 to 2000 folds. We have also devised ways to very smartly tag them with fluorophores in a way that the qualitative and quantitative fluorescence that comes out from these membrane proteins actually helps us identify their orientation and thereby understand their structure. The membrane proteins, now why should membrane proteins be important? Membrane proteins are the first line of proteins that any virus attacks, any bacteria attacks, any drug is targeted to. Now, in this COVID-19 situation, even a 10 standard kid would be able to rattle off that the spike protein of the SARS-CoV-2 binds to ACE2 receptor of the human cell. So ACE2 receptor is an example of a membrane protein. Many such proteins are drug targets, and many such proteins go haywire in cancers as well as neurodegenerative diseases. Now, just below the membrane proteins are a specific class of proteins called the receptor tyrosine kinases. These are the molecules that can pass on information from the membrane proteins into the deepest recesses of the cells, like like passing on the baton from one molecule to the other till it reaches the nucleus. So the receptor tyrosine kinases are well-established targets in cancer. They go wrong in many cancers, but now our group has shown that many of these oncogenic signatures that go wrong in cancers are also reciprocated in neurodegenerative diseases. So I go back to the theme that I have been harping on. Cancer and neurodegeneration are just two sides of the same coin. Now, going back to the structural characterization, it would be a shame if I do not tell you about the X-ray crystallography facility that is utilized by our group. So what do we do with that? We have shown that we have shown that one of the proteins of Vibrio cholerae, which is very important in the biofilm formation, we have characterized it structurally. Formation be important because if biofilms are formed, be it for viruses, be it for other infections like bacterial infections, then targeting with drugs becomes a challenge. So understanding the structure of such proteins becomes very important. We also use NMR to understand the structure of complex molecules. What do I mean by complex molecules? And why should these complex molecules be important? We know that insulin is one of the ways, artificially made insulin is injected into individuals who have diabetes, right? And now, during the course of the last 2 days, you have heard that one of the latest ways to address many cancers is monoclonal antibodies. The monoclonal antibodies versus the size of insulin is thousands of folds size difference. So if we were to analyze the structure of more immunoglobulins or monoclonal antibodies, we would need, it is not possible as of now with X-ray crystallography. So we need NMR to do that. We also use this facility to understand how to generate biobetters and biosimilar products. So biosimilar products and biobetters are better drugs which can be commercially made in a more economic manner, as well as in. Not just that, we also use computational approaches and quantum mechanics and quantum mechanics to understand how enzymes, complex enzymatic reactions happen. Because over the decades, we know that's the pathway in which an enzyme works, but the exact mechanism of its activity is quite unknown for multiple such multiple such enzymes. So why should that be important? We can then design artificial enzymes which can work better, which can mimic situations better. So that is what the crux of our group is so far. Now, What has been our output? Just one little output. Our work is well acclaimed across the world. It is very highly cited. Between 2020 and 2022, when experimental biology was massively affected during the pandemic, we managed to produce more than 156 papers, of which they are in very high impact factor journals. They are very well cited. Our expertise is sought after by multiple institutes, by many colleagues around the world. I hope I have been able to give you an overview of how we work at the Biophysical Sciences Group in the Saha Institute of Nuclear Physics. I will be happy to take your questions, and we will be very happy to have collaborations from our colleagues across the various institutes under the HBNI. Thank you very much. Thank you for your attention.
Hello, can you hear me?
Yes.
That was a nice talk, and I like your analogy between neurodegenerative diseases and cancer. But in neurodegenerative diseases, you can associate the disease to one or two problems with the genes. And in cancer, multiple proteins and multiple genes are involved. So at what level do you see the synergy, and where do you think, I would like to see at what level you see the synergy?
Okay, thanks Prasanna for the question. So the synergy is at the level where the regulatory molecules are. Like I talked about the long non-coding RNAs, we like the receptor tyrosine kinases, like many of, even at the organelle level, when you see that there is mitochondrial fission in neurodegeneration, you see similar mitochondrial fission during the gliomagenesis. So there are signatures which are at the molecular level, which are at the organellar level also, which are similar. I don't say that they are absolutely the same. Yes, there has to be differences because one would lead to extensive proliferation, the other would lead to extensive degeneration. But I think all of us are actually working on a very fine balance between the two, and either a slight increase or a slight decrease in any of these balances is going to wreak havoc. And just one clarification, Prasanna, neurodegenerative diseases are not always single genetics. I mean, they do not originate from single genes always. They are also from multiple things that go wrong in a cell. Even our belief that only one gene may be associated with one disease, a neurodegenerative disease, has to get reformed, and that should happen. So that is the problem. These are very less studied diseases, even though there are multiple laboratories across the world doing it, but these are not as much studied as is cancer. So our understanding still lacks there.
Okay, thank you, Oishee.
Hi, Oishee, this is Saurabh.
Yes,
Just a quick
hi
question.
Saurabh.
Hi, just a quick question on the mechanobiology thing. Are you
Yeah.
guys only looking at cell surface changes, or are you also looking at how cytoskeletal elements alter?
Okay. Yeah. So Saurabh, first of all, not cell surface changes. The mechanobiology, the picture that I showed is actually of the nucleus. It is the lamines which are stained over there. So it has to do with the cytoskeletal proteins, the architectural proteins. Yes.
So if there are no question, please join me in thanking the speaker.
Thank you very much.
So our next speaker is Dr. Aradhana Srivastava from BARC.
Good afternoon. Firstly, I thank HBNI for organizing this meeting, and we are really enjoying the scintillating talks and discussions since yesterday. And in the present talk, I am going to highlight some of the recent advances in nuclear and astrophysics research being done in BARC, and I will also give an overview of the facilities used. So both nuclear and astrophysics actually try to unravel the mysteries of universe. Nuclear physics focuses on what is the nature of strongly interacting matter in the universe and how they are created. High energy astrophysics, on the other hand, studies the universe at extreme. So nuclear physics, nuclear matter actually makes up of 99.9% of mass of the visible world. And if we want to study the nuclear matter at different stages, we know if we want to study a object, then depending on the size, the resolution, our probe size wavelength should be of that order. So if we want to study the coagulant matter, then the probe size should be the, when you say the wavelength, that means the energy. The energy should be a relativistic heavy ion collisions. And for the studying the neutron, which is made up of quark and gluon, to study this complex object, the electron scattering is the best probe. And when one is studying the formation of light ions to light nuclei to heavy nuclei, the accelerated beams of medium energies are used. And when one goes to study the reactions happening in stars, the observatories are the ones which one used to study the things. Now, coming to the nuclear physics, we all know that nucleus was discovered by the alpha scattering, which was from a radioactive source. But now when we study the nucleus, we need different nuclear property. We should take a projectile beam from an accelerator on a target to study various aspects of the nuclear chart, why there are only 300 stable nuclei, what happens when you go to the nuclei which are actually 7,000 number predicted, how their properties change, and how can you reach the super heavy elements. For that, you need to make the combination. You have to synthesize the nuclei in the laboratory. So you need projectile and target, two different nuclei, and you have to do some nuclear reactions. So what kind of nuclear reactions one can have when the projectile bombards the target? It can be elastic scattering. The nucleus can get excited, or it can fuse, forming a compound system, or it can just exchange few neutron or protons. This is called transfer reaction. So how we do the research in nuclear physics, you just detect the reaction products, and these reaction products from the nuclear collision actually carry the information about the nature of interaction and also about the nature of the nuclear structure. So what we need, an experimental setup which can detect all the outgoing nuclear products, for example, neutron, gamma rays, X-rays, charged particles, and fission fragments, and of course you need an accelerator. So the accelerator which we have at Bombay, which is our workhorse, is a Pelletron accelerator situated at TIFR, which has been augmented by a LINAC booster. And this LINAC was indigenously developed in India. So as we know, to have a nuclear reaction, because both the nuclei are positively charged, you need an you need to have the energy to overcome this Coulomb barrier, which is formed by the repulsive Coulomb and the attractive nuclear potential. So the energies which we get from this accelerator are around this Coulomb barrier energies, and all our reactions are centered around that. So what are the different facilities available? So there are three different beam halls available at Pelletron facilities, and where one is doing different type of research. Apart from nuclear physics, there are other activities also, for example, condensed matter, atomic and radiochemical studies, etc. And there are different user community also participating in experiments. Apart from BRC, TFR, we have SINP and collaborators from VECC, also ISRO and universities and other institutions. And we will be very happy if the CIs from the different HBNI, they also collaborate and do experiments in this facility. We'll be very happy to welcome them. So this is, on this picture, there is one of the three experimental hall, which is one of the older hall. This is called Cascade Hall. This has five beam lines, which houses one irradiation setup. Then there are activities like accelerator mass spectrometry. There are detector setup for neutron and gamma measurements, and also some atomic physics activity and a chamber for doing nuclear reactions, a vacuum chamber. And after the LINAC was augmented, we had two more beam halls. Hall 1 has three beam lines, and this is actually one of the most used facility. This is the multi-purpose scattering chamber, and this is fully automated for the movement of targets. And one does nuclear reaction studies. Then you have an array of gamma rays, neutron walls, and this beam line is planned for irradiation setup. And then Hall 2 has two major facilities. One of them is Engg. This is an array of gamma detector for high resolution measurement. And then there is a charge particle ball. This is the charge particle ball. And there is also one facility which will come up at some point, which is a momentum macromet, which can be used for radioactive ion studies. Okay, so this is the kind of collage of all the detection setup which we have at Pelletron. And we use them in a combination tailored according to our experimental requirement. So this one is the vacuum chamber, multipurpose scattering chamber I described before. And inside this chamber, one can have an array of very high resolution, high efficiency strip detector telescope for measurement of charged particle. And this chamber one can also house MWPC for fission fragment measurements. And such measurements need to be done inside the vacuum. But however, gamma measurements, for example, this is an array for high energy gamma measurement. This is a very high efficient array, and also neutron wall. This is consists of a liquid scintillator detector for neutron measurement. And this is high resolution Clover detector array for doing nuclear spectroscopy for studying the structure of nuclei. And as I said, we use the combo depending on our experimental requirement, which you will see as I show some experiments. So these are the actually nuclear physics activities. Some of the activities I have listed, there are more, but some major ones I have listed. And I will be able to give only some flavor of some of the activities. And I have chosen activities, some of which HBNI PhD students were involved, which resulted in thesis of HBNI. So what we do, what kind of reactions we study, actually we try to see what is the rich interplay between nuclear structure, for example, single particle excitation or collective excitation, with reaction dynamics. And these are the major topics like fission dynamics. BRC has a very long tradition of fission physics, and we have done some pioneering contributions. Today, I'll be presenting some recent works, then fusion, nuclear level density, and so on and so forth. So now I present some results from very exciting physics. Sorry, I'm not able to see. So this was the actually first measurement of where one could measure the electromagnetic radiation from the tiniest rotor, which is 8 beryllium. I hope you can see that. It is 8 beryllium. And 8 beryllium is known to be alpha cluster. 8 beryllium made up of 2 alpha cluster. But however, and in this research study, we could see, we could very confirm what is the shape of that. And this was very challenging experiment. You had you have a helium gas, which was alpha target, and then bombarding on that was alpha beam. And the one had to measure simultaneously the 2 alpha and the high energy gamma, using a strip. This is a double-sided silicon detector and an array of high energy gamma ray. With that, one could observe the gamma lines, which actually confirm that 8 beryllium has a dumbbell-like shape, a deformed shape, and from this rotational energy, it could be confirmed that you can see the size of this rotor as compared to your hydrogen molecule or a spinning top. So this we can say is the tiniest rotor which has been detected. The next is like 8 beryllium, there are other light nuclei which have cluster structure, and these clusters are weakly bound. At Pelletron, this is one of the major activity nowadays to study the reactions with this weakly bound nuclei, which is 7 lithium, for example. It has alpha plus triton cluster. There was a long-standing problem in a reaction with 7 lithium with other targets. There is a large alpha production. So what is the origin of this? So there are 2 different modes. One could be that this when 7 lithium interacts with target, it breaks up and then triton gets absorbed, or it can be a direct transfer of triton. So we did an experiment where using the combination, a coincidence measurement using the this Clover detector array and the charge particle measurement. By using these 2 information and the correlation, kinematical correlation curve, we could first time unambiguously give a clear evidence that it is a direct triton transfer, which is the dominant mechanism for alpha production with the weakly bound nuclei. So next, I give some example of fission measurements. So this measurement was this was a part of thesis of HBNI student Shilpi. So in this work, the aim was to study the role of quasi-fission in asymmetric fission, which is recently observed in case of pre-actinides. So in this work, same compound nucleus, which is 191 gold, was formed using 2 different combination of target and projectile, this, and then the fission coming from this was studied. And the fission fragments were detected using these 2 MWPC detectors. And mass distribution was obtained using the time of flight information, velocity information, etc., and position information. So what is interesting to see here, this is the reduced mass distribution. That mass distribution coming from these 2 different combinations is different. And the mass distribution coming from fission fragment mass distribution coming from this heavier projectile is actually having a component of quasi-fission. So so in case of pre-actinide, it is assumed that this asymmetric fission is observed, and it is due to shell effect. But so from this work, it was shown that one should be very careful if to pinpoint such effect if the projectile is heavier. So the next one is this work is aimed to understand what is the force which is driving the asymmetric fission in case of both pre-actinides and actinides. So fission, as we know, is a complex phenomena, and it is governed by both macroscopic effect, which is actually liquid drop, and also microscopic effect, which is a Quantel effect. So based on liquid drop, this is the potential energy surface of the fissioning nucleus in 3 dimensions. So this is the value. If you follow the liquid drop picture, the 2 fission fragments should split into 2 symmetric fragments, because that gives you the maximum Coulomb repulsion. And when you add your shell correction to liquid drop, then there are valleys depending on the shell effect, and that gives rise to asymmetric fission. So It was the motivation was to see what is the reason for this asymmetric fission, whether it is the neutron shell or proton shell, what is dominating. So this work showed very clearly that it is the proton shell which is dominant, or which is the one which is responsible for deciding the asymmetric fission. For example, if you see in case of, this is the pre-actinide region, which is around the lead, the proton shell of the light, this is, in this one has plotted the Z values of light and heavy fragments, average Z value. So as your compound system which is fissioning, the Z is increasing, the proton shell remains stabilized and the value doesn't change. With increasing Z, only the heavier fragment Z is increasing. But after sometimes when the next higher shell is latched, then the Z of the higher, heavier fragment, that becomes stable, and lower the Z of the lighter fragments, that is the value of that is starts increasing when you go for a heavier Z. So this actually in a very combined way explain what is the reason for the asymmetric fission for pre-actinide and actinide region. And when you go for the nucleus heavier than Z equal to 100, there is something interesting happening, because then the shell effect will, both the fragments are going to have the similar Z value. And then you can have shell effect in that also. And this is the work showing that effect. So in this, the fissioning nucleus was populated near the fermium region. And it was found that there are actually 3 different kind of fission modes are possible. One is, what is special in this case is that this nucleus is where fissioning nucleus, when you reach around mass 264, it is very close to doubly magic 132. And it is then both the fragments, and this is a spherical shape, and there will be few events where this kind of this short symmetric mode is possible. And what will be the signature of this? Because the distance between the 2 fragments is shorter, their kinetic energy will be large. So this is a rare fissioning mode and can be observed only beyond fermium, and when you have a mass number heavy around 264, and signature of that was observed in case of molybdenum, which was formed in this nuclear reaction. This blue region is actually the kinetic energy that which is corresponding to this configuration. So it was observed in case of molybdenum, and it was not observed in case of this anstitinium, because it is the mass number is away from this magic number. So this is a clear signature of this mode. So next I talk about some nuclear level density, which is very important in different branches of physics. And in this, we made a very important contribution about this. This level density actually depends on various parameters, for example, shell effects, angular momentum, etc. So in this, as excitation energy of the system increases, this shell effect should decrease and should melt ultimately, and the behavior as a function of temperature was predicted long time before, but it was actually could be confirmed very recently when with the help of a large neutron detector array and charge particle array, when using a novel experimental method where you could using the property of 7-lithium, that it is a cluster of alpha and triton. This triton, when combined with this target, you are able to make this doubly magic lead, and using this high efficiency detectors, it was possible to prove whatever was predicted long time back. So now I tell about some ultra low cross-section measurement technique which has been developed. So for all we know that for any rare events, it is where the main requirement is to background reduction, increase the sensitivity, selectivity, and accuracy. Of course, one is trying to look for a needle in the haystack. So the method we develop is, first of all, you use the off-beam technique for the nucleus. Then you know the half-life. And then you have a gamma ray coming from the daughter nucleus, and if it is the method the daughter is decaying by electron capture, then you also have a K X-rays. So if you measure both the gamma and K X-ray simultaneously, and you keep your gamma detector inside the low background setup, then you are able to reduce the background by orders of magnitude. So this is inclusive measurement of gamma, and this is after performing the coincidence. So you can see that the sensitivity was greatly reduced, and the selectivity was obtained by identifying the characteristic gamma lines and following the half-life. Using this method, cross-section of very low cross-section could be measured, and this could actually give a new direction to understanding this fusion at deep subbarrier energies. And such measurements are also very important for astrophysical reaction, for measuring the astrophysical reaction rates. So one of the other very important activities which we are doing at Pelletron is also some cross-section measurements which have direct implication on energy application. The surrogate method, one of the method which we have developed is surrogate method, which have already been established for minor actinides. So in this work, this is mainly on fusion, to help in the fusion reactor, because in the fusion reactor, which is the next generation reactor, the DT reaction will be used, and it will produce a high energy neutron and alpha particle. And this neutron will actually, this neutron will actually affect the structural material, which is SS. And these are the components of neutron of the SS, and they will transmute and form other radioactive elements. So the main problem is that after the neutron reaction, you will have a lot of hydrogen and helium gas produced, which will lead to swelling and embrittlement of the structural material. Not just that, the neutrons, the protons which are produced, the radioactive transmuted nuclei which are produced, they also will absorb neutrons, and they will also give hydrogen and helium gas. So it is very important to know all these cross sections. And since radioactive targets are not possible to make, so one can use the surrogate reaction. That means you can form, if you want to study N plus 53 manganese forming this nucleus, the same compound system you can populate by using some other channel, and this target can be made easily because this is a stable nucleus. And this cross section can give you idea about, and this kind of cross sections are really needed for planning of the structural material of the fusion reactors. So other important activity is which is related to nuclear astrophysics is a study of Hoyle state. And we know that Hoyle state is one of the very important state for population of, for synthesis of carbon and nuclei beyond the carbon. So this 3 alpha states can, Hoyle state can decay to ground state. And the ones which lead to ground state carbon and not breaking into 3 alpha actually lead to carbon production. So it is very important to know what is the configuration of this Hoyle state, this 3 alpha, which way they are arranged. So there is some investigation done in that direction, and also measurements are planned using carbon to study these Hoyle states. Now I speak something on the application activities. So these are the some application using the beam available, basically proton beam available from Pelletron. This is some track edge membrane setup, and this track edge, this track with having this kind of pore sizes has various application. And also this proton, there is a high current proton and neutron activation setup in Pelletron that can be used for, you irradiate some material of industrial application and by proton, and then there will be some activity created on this material. And if this, for example, this material, if it wears off as a function of time, you are monitoring that activity will die faster, I mean, will fall faster. So that will tell you that this wearing is happening faster. And there are other activities also like towards nuclear medicine, etc. Another important activity is to irradiation. There is irradiation setup to test the devices which go to space by ISRO. These are the set of devices, and there is one more setup which is for agricultural purpose, where you use the different grains for studying the mutation breeding, and after irradiation they are studied for better yield, etc. Now from Pelletron I come to other facility which is stationed at using a Dhruva reactor. So in Dhruva reactor we have liquid scintillator. We have scintillator matrix to study the anti-neutrino, and this Smaran matrix will be used for this. Already has started taking measurement, round-the-clock measurement since October 21, and this is very important in the sense that one can monitor reactor power in a non-intrusive way by measurement of this anti-neutrino. And it can also be used to do some fundamental research, for example, to look for sterile neutrinos and to study the anomaly in antineutrino. And these are some future plans for this kind of research going to other reactors, because this antineutrino is coming from the reactor is very sensitive to the type of core, whether it is uranium or plutonium. The other facility which we have at Dhruva Research Reactor is a very array of gamma detector, and actually this has brought nuclear structure study to another level, because this is one of the unique facility where you can use thermal neutron to produce a neutron-rich fission fragment, and you do structure study of that. And this is one of the first results coming from this facility, where the high resolution spectroscopy is done by radiating thermal neutron on dysprosium. And this has already shown, okay, this has got, these are the gamma lines, and this is the level scheme. And then this result has already been communicated, where it has been shown that this nucleus assumes triaxial pierce shape, and it has shown some real low spin vibrational modes. We are also have facility, and we are also utilizing some other low energy and light ion accelerator at facilities at BRC. One of them is folded temtum accelerator at Foot. And here we have a setup for measuring prompt fission, neutron and gamma spectra measurement. And this is actually R&D towards transmutation of actinide and minor actinides using the fast neutron produced in this setup. And this fast neutron spectra has an overlap with neutron coming from fast reactors and ADS. This FOTIA also has a scattering chamber for doing nuclear reactions. And there is a facility coming up, LEHIPA, of high current proton, and at present the energy is around 6.8 MeV, and it will progressively reach to 20 MeV, and we have plans for using this facility also. And there is also upcoming facility which is being which is in the process of coming up, which is ECR ion source, and there will be different kind of research initiated in using this facility, which is some of them are listed here. For example, fusion and also atomic physics related activities. And further, coupled to this ECR ion source, there is a plan to attach RFQ and DTL, and this will be again a neutron source, and that has also a various application which is related to ADS, radioisotope production for reactor purpose or astrophysics. So before I go to astrophysics, some of the excitements from astrophysics, I'll just conclude this nucleophysics part. But just kitna, how much minute? Okay. So these are some some immediate activities, and then we are going to some in this is some major facility proposed using the already at VIII, there are two electron and proton accelerators coming up, and we want to produce RIB and high current stable ion beam. That and this will be a very major facility in the future, giving both a stable and radioactive ion beam, where there are so many excitements there. Now coming to high energy astrophysics research. Astrophysics, the main messengers are waves, which are electromagnetic and gravitational, and also the particles, which are cosmic rays and neutrons. And then electromagnetic waves, there is a wide range from radio to gamma rays. And this here you have both space and the ground observatory possible, but for gamma ray, only space observatories are possible. And the gamma ray energy range is quite high. And this once done, so this actually gamma ray spectroscopy, the physics, it addresses the physics under extreme conditions. So the this was the first observatory tactic, which was in Mount Abu, and this has already given this was commissioned in 1997, and this already has given very nice results. This was the first gamma ray flare from one active galaxy, which was observed in sorry, I cannot see the date. And this gamma flare was at the same time detected in many other ground-based telescopes situated in Europe and USA. And then this shows another activity. This shows a gamma ray flare from coming from another active galaxy. And plotted in this graph is the energy spectra coming from other observatory, which are of different wavelengths. And then this theoretical calculations one can see, and this is the data from tactic. The calculations from explain the data from other observatory and that from tactic. And these are the synchrotron and synchrotron self-Compton coming from the emission of synchrotron and synchrotron self-Compton. And this was one of the very major and important observation made actually, and whenever there is an important observation done in the field of astronomy, it is reported as a telegraph. So this flare was observed, which was some 7 times over the background, and this was reported as a telegraph. This is from TACTIS. And this again shows a very lovely results. You have a black hole and the accretion disk. This shows the spectra, and then this shows the temperature and radius evolution from the data, from the available data, how does the temperature and radius changes. And this is using observation from TACTIS and other observatory. And this is again a very good, very beautiful results. This gives an estimate of the distance from the redshift estimation. You get the distance of your source from the Earth, and these are the results from the observation made in our using tactic. And this is the observation. This is the values estimation made using other optical devices, and the results match very well. And now this is the MACE telescope, which is recently been commissioned, and this has a very wide energy range, and these are the different size and different resolution and other parameters. And this is the simulation which was done for the integrals for the sensitivity and energy resolution. And it is also compared with a similar observatory which is there in Germany. And so one expects a similar kind of the observation or the data quality which one has been getting from the MAGIC. So this is the first result which was obtained using the MACE. This is the first result. And this result was confirmed using this January 29. And this is the full energy spectrum from the Crab Nebula from 33 GeV to 400 GeV. And these are some signs ahead using the MACE. These are some of the problems which will be addressed using the MACE. For example, this understanding the radiative process and particle acceleration, study the pulsar, which are very enigmatic objects in the Milky Way galaxy. then also probing the universe deeper than the present one. And this is the long-term future plan. At the Hanley, there will be more maze kind of the telescopes put, and that will increase the resolution and the angular resolution and energy resolution and better background rejection. And here I thank you for your attention, and I'm sorry I just crossed the time. And I also thank all my colleagues from physics group who gave me their input, and also suggestions from my colleagues for this talk. And I thank the audience for their patience.
We can have maybe 1 or 2 questions.
In the antineutrino properties in the Apsara context, you understand? I mean, you mentioned about physics beyond the standard model. What exactly did you mean by that?
Actually, this is this is elastic.
Antineutrino nuclear scattering in Apsara.
Coherent,
Yeah.
elastic coherent.
So what kind of physics beyond the standard model you hope to measure from there?
Okay, you will try to understand from the scattering the interaction of neutrino with the nucleus.
No, that is what you are going to measure, antineutrino nucleus. My question is, what kind of physics beyond the standard model you expect to probe?
No,
there?
this what I had written that was for the complete thing. That was not just for that. That for the complete neutrino research I had written, because the sterile. I'm sorry. Okay,
sterile component. Okay.
Yeah. It was not just for that component. It was for the complete reactor neutrino study.
Do you hear me? Yeah. Aradhana, it was a fantastic talk. Now I have only one quick question. This maze result, the first result that you showed, 17 minutes or something. How long did it take to get that plot? Means it was only 17 minutes data taking, or it was like 1 month data taking and it filtered out 17 minutes or what? Because this is the first result. Yeah, sure.
Can I take this question? Actually, on 29th January, we observed the Crab Nebula for 2 hours. So what is plot shown here is for 2 hours observations. But in our field, the 5 sigma detection from the Crab Nebula, that coming in 17 minutes. So that is what is the importance of the 17 minutes.
Like 5 hours data, out of that 17 minutes is the signal.
This plot is shown, this is for around 2 hours of data. Okay. So if we observe just for 17 minutes, the detection is confirmed. This is the meaning. Okay.
So you are continuously taking data, or is the what is the plan like? That
it is continuously. It is continuously.
And remotely means
remotely. Then we have people at station there also, so it can operate in both the modes.
Thank you.
Yeah. Thank you.
And let's thank the speaker. Our next and last speaker is Professor A. Srinivasan from NISER, Bhubaneswar.
Is it late order? Huh? Yes. Huh? Okay. Yeah, good afternoon. And first of all, at the outset, I would like to take this opportunity to thank Professor Vasudeva Rao, Professor Dilip Maiti, and Professor P.D. Nayak for inviting us to discuss and interact with the DA units. And I also take this opportunity to thank Director NISER for giving us the opportunity to showcase about the School of Chemical Sciences progress, what is going on in NISER. And I also take this opportunity, the Chairperson, School of Chemical Sciences, and my colleagues, those who are closely monitoring the presentations through online mode, and also they have set some of the slides for the presentations today. And I also thank one more thank goes to the people, those who are not part of the things. One is there are two Sarmajis to take care of all our proceedings so nicely. One Sarmaji is sitting inside the hall, another Sarmaji is standing outside the hall, who is taking care of all the activities. Okay, on behalf of the DI units, I thank all the organizing committee members for taking care of the proceedings so smoothly. And now we will start the progress about the School of Chemical Sciences from NISER Bhubaneswar. And these are the programs at School of Chemical Sciences. We have integrated MSc program and we have PhD program. These two programs are currently going on. And the third program is integrated PhD program, which we have submitted for the recognition from HBNI unit, HBNI. So hopefully we will get the clearance from HBNI shortly. And on a lighter note, if we don't get the clearance from HBNI, we may not get the funding from the director NISER. So that is the lighter note from our side. And for the regarding integrated MSc program, we have altogether there are 180 students graduated so far, and currently there are 191 students are there doing the integrated MSc program. And from this list, I would like to say that there are for the HBNA audience, these are the people who have graduated from School of Chemical Sciences. And there are 3 students from batch 2007-2012. And there are one from 2009-14 and one from 13-18. They have cleared the BARC training school program, and they are joined as scientific officers at various units across DAE. One is Pallavi Vitti Krishna, who joined in SOD as a Trombe. The second one is Pranyan Dididas. He is currently working as SOE, Heavy Water Plant, Baroda. And the third one is Mohit Soni. He is SOD working in Kalpakam. And there are Kanagala Sandeep Rao. He is the topper in the batch, and yeah, he is supposed to go for higher studies. And there are some incidents happen at home, and finally he narrowed down his work and finally joined in BRC training school. And currently he is SOD at Rambe. And there is the last one is Amol Chandrakar. He is SOC Chakrabarti, Surat. And this is our students, those who joined as scientific officers at various units. And we would like to thank again HBNI and BRC for giving us the opportunity to appear only for the direct interview and waiving of the written examination for this program. And regarding the PhD scholars and postdoctoral fellows, we have already thoroughly mentioned by our colleagues yesterday by Dr. Harapriya Mahapatra and Professor Bedangadas Mohanty about the PhD program. But the eligibility criteria is same as that of any other unit, MSc with a 60% mark, and they should have qualified NET or GATE LS and are all selected through the interview. And as of right now, there are 80 students are doing the PhD program in NISER, and 10 of them submitted thesis, and they are in various scholarship. Out of 64 are in Institute Fellowship, 14 are in CSR Fellowship, 7 are in UGC Fellowship, and 5 are in DST Inspire Fellowship. That the DST Inspire Fellowship is now cancelled, so only the students are in the UGC and CSR or Institute Fellowship. Regarding the PhD awarded, so far 65 students awarded PhD from NISER, from particularly the School of Chemical Sciences. Regarding the postdoctoral fellowship, there are 24 are currently working as a postdoctoral at NISER. Out of them, 17 are from the Institute Fellowship because of the generous funding from the Department of Atomic Energy. And there are 17 students are currently doing as an Institute Fellow. There are 5 of them are a project that is, they are in DST or SERB or CSAR projects, and 2 of them are working as a NPDF postdoctoral fellows. And for this, for the HBNA, particularly the Outstanding Student Award, this is there are 3 students in 2019 when they have initiated this Outstanding Student Award, and 3 of the students from NISER got the Outstanding Student Award from HBNA when they have initiated such activities. Yes, when they have initiated such activities, these 3 students got the award, and they got it from the same auditorium from Vice Chancellor. And there is one from last year, they got one from SES, that is Dr. Tyagarajan. He got the Best Outstanding Student Award from HBNI through virtual mode. Now coming back to the faculties and staffs at SES, there are 21 faculties at NISER, and out of 1 as a professor, 16 associate professors, and 2 as reader F, and 2 of them are assistant professor. And there are 2 scientific officers and 6 laboratory operators and technicians, those who are taking care of the laboratory activities, and there are 2 administrative staff, they are taking care of the administrative functionalities. And these are the faculty strength at NISER. There are 6 faculties in organic chemistry, 7 in inorganic chemistry, and 8 in physical chemistry. And I would like to take you through what the work is going on across School of Chemical Sciences. And this is about the about the organic chemistry. We have the faculty strength in medicinal chemistry, organocatalysis, polymer chemistry, physical organic chemistry, and stereochemistry. And in the inorganic chemistry, we have people working in bioinorganic catalysis, organometallic and solid state chemistry, and coordination chemistry. And physical chemistry, we have laser spectroscopy, NMR, chemical kinetics and dynamics, photochemistry, and materials chemistry. And this is about I am starting with inorganic chemistry. This is my area of research, where we mainly focus on the synthesis of the porphyrinides, and it is part of the Chem unit, and here it is mainly we focus on the contracted derivatives. By simple condensation reaction, one can synthesize the contracted molecule, something like this, and one can also do the coordination chemistry with the things, and then where we can observe where we can see the nice absorption and emission spectral data, and where we can find out the cavity size of one of the zinc complex with the adjacent, opposite, alternative bond distance between the metal ions. And what we can do further with this complex, where this is further utilized for the zinc ion binding. It exclusively bind with the zinc 2+, and where it shows the enhanced emission upon binding with the zinc 2+, and shows the 1:1 binding mode in the presence of zinc 2+, and exclusively binding only zinc 2+. And also we have done the competitive recognition experiment, and it shows a selective binding only with the zinc 2+. And the binding constant from the Beden-Sigildi job plot, one can find out the binding constant, which shows the binding value of 5.47 into 10⁴, and the detection limit is 1.5 ppm. And this is about the work of Dr. Saranappa Nemmana. He is mainly focused on conjugated bis guanidine-based aluminum complexes and its application. And he has made a series of bis coordinated complexes. One is the monometallic aluminum complexes, another one is dinuclear aluminum complexes, where mainly used for the reduction of carbonyl reduction by using the hydroboration reactions, and where where he utilized the easy synthesis steps and also less number of steps to achieve this kind of the material. And also one should note that the dinuclear aluminum complexes are less known in the literature. And he also established with the aluminum complexes where the hydroboration reaction of alkane and nitride reactions, which he has done with a variety of examples, and altogether which he has done with the 49 substrated complexes to achieve this kind of the hydroboration reactions. And he has also continued to work in the case of zinc hydrate catalyzed hydrofunctionalization, where in this case which he has synthesized the zinc hydrate for the hydroboration reactions. By here he used aryl as a nitro isocyanate complex, thiocyanate isocyanate complexes, and where he has done the reduction reactions to get the two kind of examples by using the zinc hydrides, and where he has also done with the zinc where hydroboration and hydrosilylation which he has done, and further hydrolysis which he got the corresponding secondary alcohol, where the reactions involved a selective reduction, hydrodeoxygenation, and automechanically excellent yield, low catalyst loading, all those things which he has come out with from these findings. Moving on to Dr. Bidra Habak, he is a reader of, and he is mainly working on sustainable catalytic development by transition metal catalysts, and mainly involved for oxidation of vanillyl alcohol to highly important aroma molecule, converted into a vanillin, where he mainly used for a copper catalyst and a selective oxidation for this conversion. And in principle, one should use the peroxide oxidant or a pressurized oxygen cylinder for this purpose, where he has used a simple catalyst for this conversion and achieved finally an excellent isolated yield from this. He has also done the hydrogenation of carbonyl compounds or carbonyls or aldehyde derivatives, which he has come out with by using air-stable ruthenium triazole catalyst and transfer hydrogenation under aerobic conditions. And he has also where the primary alcohols, particularly the methanol and ethanol involved here as a sacrificeable hydrogen source. And finally, he achieved the excellent yield from these reactions. Moving on to Dr. B. Krishnan, he is mainly worked on the boron-based fluorescent materials, and where the first part which he has done with the triaryl pyrrozole derivative, and he linked with the boron complexes and connected with the bilinkers, which shows the remarkable nonlinear activities. And he has also demonstrated with benzonylide-based boron complexes, where he has come out with the quantum yield and normal to excellent quantum yield, which he has come out with. And he has also used the material with the selective binding of picric acid by using a 1,1-dimethylphenylanilene and a 1,1-diphenylanilene based imidazole boron complexes, which he has come out with, where the complex selectively binds with the picric acid in compared to the various aromatic nitro acid which he has tried with, and finally exclusively binds with the picric acid. What he has come out with the solution that the hydroxyl group which is there in the trinitro picric acid, which is deprotonated by the 1,1-dimethylanilene. And moving on to the materials chemist, Dr. J.N. Bera is mainly focusing on the materials chemistry area. And his main area of research, he focused mainly on boron-based complexes, boron-based graphene compounds connected with the cobalt CPP4 material in connection with the M-zine, which he has come out with the composite material, which is effectively suitable for the supercapacitor prototype exhibiting, which exhibit ultra high energy and power densities with a robust cycling durability. And he has also worked on the metal organic framework derived cobalt selenide, which are catalyzed for the hydrogen evolution reactions and the oxygen evolution reactions, which is mainly requiring for 195 millivolt and 320 millivolt over potential to reach the benchmark 10 milliampere per centimeter square current density. And he is also involved for reduced carbon graphene oxides and functionalized carbon nanotube with VS4 composite material. Along with that, he has mixed with COFE metal organic framework derived material, where it is mainly used for the oxygen evolution reaction, where the performance requires only 230 millivolt and 239 millivolt power potential to reach the state-of-the-art current density material. Moving on to physical chemistry, where we have Dr. Sudeep Burman, which he has mainly synthesized a series of one-dimensional, two-dimensional, three-dimensional nanostructured material by using various techniques such as hydrothermal, microwave, sono, photochemical, and CVD, chemical vapor deposition, salt, gel methods, which he has synthesized a series of nanostructured material. And what he has done, which he has come out with the iridium oxide and modified ruthenium oxide, carbon nitrogen doped material, which he has come out with. And this material mainly utilized for the hydrogen evolution reaction and oxygen evolution reaction, which he has mainly focused on. And for the hydrogen evolution reactions, where the potential value is far better than that of the commercially available iridium oxide and ruthenium oxide. And in the case of oxygen evolution reactions, where it is far better than platinum carbon electrode potential, as in the basic media. In the case of neutral and acidic media, that is slightly lesser than that of the platinum carbon electrode. And he has also mainly focused on heteroatom doped porous carbon materials, which has a greater potential for both capacitive energy storage and gas absorption applications. And he has also synthesized 3D assembly of cobalt aluminum oxide spinel nanosheet for energy storage purpose, which he has come out with. And moving on to Dr. Himanshu Biswal, he is mainly working in the area of laser spectroscopy and computational studies on non-covalent interactions. Here, the non-covalent interaction, what he has mainly focused for carbon bonding interactions in proteins. Particularly, there is the carbon bonding interactions which he has come out with between the carbonyl oxygen as an acceptor and the sp3 carbon as a donor, which he has explored the carbon bonding interactions in proteins. He has also explored hydrogen bonding interactions with sulfur and selenium, where functional material, he explored the hydrogen bonding interaction in functional materials and structural biological samples, which he has explored for such hydrogen bonding interactions. And he has also studied for a long-term storage of the DNA and RNA material. Storing the DNA, RNA material, it is not that easy at room temperature, which he has come out with the cytoplasm based, cobalamin based, cobalamin amino acid ionic liquid, which he has come out with. And with that, which he is able to store the material at room temperature, particularly the RNA1. RNA1, it is usually not able to store it at room temperature. It is easy to degrade at room temperature. So it is easy to degrade as compared to the DNA. And usually the people used to store it at -20 degrees centigrade. For such purpose, where he has introduced cobalamin based, cobalamin-based ionic liquid, amino acid ionic liquid, which he has come out with, that is able to store the material for even at the room temperature. Where the next, which he has also focused on the drug design, particularly of the thiouracil dissolution, kidney stone dissolution, and material for photosensitizer application, which he has come out with. that with the help of AMC he is currently carrying out such a work for the dissolution reactions. And further, he has also mainly focused on the hydrogen bonding system with a tetravalent carbon atom, where he has thoroughly analyzed out of 913 crystals, which he has come out with 1,051 interactions. Out of that, 843 crystals he has such a hydrogen bonding interaction with the tetravalent carbon atom. And this work very recently cited, well cited in chemistry world. And this is the authors where he is mainly focusing on for the experimental proof, where he is mainly focusing on laser, high resolution laser spectroscopy study, whether he can prove such a hydrogen bonding interactions. Moving on to Dr. Malai Sarkar, where his main area of research is on quantum dots, perovskite nanocrystal, metal nanocluster, deep eutectic solvents, ionic liquids. And some of the things where he has monitored through the energy transfer, electron transfer, sensing, and protein ligand interaction, solute dynamics. And particularly the area, his research group mainly focused on copper nanocluster based nanosensor material, which mainly detect the high reactive oxygen substrate and antioxidants for the easy to detect such a material in the solution. And also his group also mainly involved for the lithium ion perturbation, particularly it binds with the monoionic liquid and the diionic liquid, dicationic ionic liquid, which he has come out with. And also the photophysical and the chemical stability of the perovskite nanoclusters are increased by using the ionic liquids. And moving on to the next one, Dr. Vishnu Biswal, his group is mainly worked on metal organic framework and a covalent organic framework. He is a new faculty joined in the School of Chemical Sciences. And his work, his group is mainly focused on this kind of the metal organic and covalent organic framework. And he would like to study for the gas separation and photocatalysis, and also energy for the hydrogen production and environmental application, which he is looking forward to do such activities. This is Dr. L. Lourdraj, and he is mainly working on he is a computational theoretical chemist and mainly focusing on mechanisms and dynamics of chemical reactions, where he involved for the thermal denitrogenation of 1-pyrazolane. Usually it goes through the transition state, where what he has come out with the transition state, instead of transition state, it goes through second order saddle high energy state to achieve the further conversion things. He has also involved for quantum mechanical study of the rotational de-excitation in HEH plus and hydrogen collisions under interstellar conditions using a machine learning fitted ab initio potential energy surface or computational modeling work. And moving on to Dr. B.L. Bhargava, his group is mainly involved for the computational soft condensed matter work. And this is mainly involved for the aminolipid based beta unfolding chains, where the zinc ions, which plays the main role for the folding purpose, where he closely monitor how the folding is happening in the systems. And his group also involved for the aggregation studies, particularly adding the salt across the aggregation in multi-headed surfactant solutions, and also mainly involved for the intermolecular hydrogen bonding interaction between the tetrabutyl ammonium chloride and the deep eutectic solvents such as glycerol and ethylene glycol based material, which he has come out with and find out the deep eutectic points. And this is the work reported by Dr. Arindam Ghosh, and he is mainly working for the chest contrast reagents. In the case of chest contrast reagents, it is usually it is called chemical exchange saturation transfer. It is alternative for the MRI contrast reagent, which he is trying to come out with. And here he is mainly used for the first case where he has used for the porphyrin-based material, where there are two kind of hydrogens which is there in the porphyrin material. One is amine NH, which is there inside the porphyrin material, which shows the 1H NMR spectral study at -1 ppm, which is far away from the water molecule. So one can do the analysis with the diassessed MRI contrast agents, and where he identified with 18% with variable pH conditions, in particular with the pH at room pH at 37 degrees centigrade at 7.4 pH range, which he is able to do the things, which shows the 18% efficiency, where the other pHs where there is the slight less in efficiency as compared to the room temperature ones. And he is also involved in para-chest MRI contrasting agents, and also working on carbon quantum dots and nanomaterial based material for the chest applications. And his group also worked in the area of NMR based metabolomics. Moving on to the organic chemistry, we have Dr. Prasenjit Mal, which he is mainly working in the area of visible light photocatalysis. In the case of visible photocatalysis, which he has come out with iodine-3 complexes, iodine-3 photocatalyst, which is selectively photocatalyst, particularly the alkyl and aryl aldehyde in the presence of the photocatalyst, which he is able to come out with a dithioacetylation. And in this case, he observed EC conversion and efficient yield for this kind of the conversion. And his group also involved for the thioacetylation from the benzyl alcohol by using a photocatalyst, something like this, that is 9-mecytyl 10-methyl acronium perchlorate as a photocatalyst, where it is easy to convert from the benzyl alcohol to thioacetal and thioethers in both the cases, where the reaction is of clear conversion. And he has also involved for by using the photocatalyst, which he has come out with the synthesis the coumarin-based 3-chlorocoumarin complexes, where the N-bromosuccinamide, N-chlorosuccinamide, which he has used along with the photocatalyst by using the starting material something like this, which he has synthesized the material of 3-chlorocoumarin materials. This is Dr. Perunjaraladhan, where he has mainly involved for the synthesis of indole-fused heterocycles, and for the conversion purpose, which he has used metal as well as the metal-free material for this reaction purpose. In the case of the metal case, where he has used copper salt for the conversion purpose. In the case of metal-free case, where he has used trifluic acid for this purpose for this conversion. And his group also involved for the functionalist benzyl material for the conversion into a benzo heterocycles. And he has also involved for the new anti-angiogenic agent, where one of the material which he has benzo heterocycle, which he has come out with. It is a potential agent for the anti-angiogenic agent, where there is a 2-amino 3-cyano benzothiophene material, where one of the position is a hydroxyl derivative, which shows the IC50 value of 150 mm and without toxicity, and works finely with the anti-angiogenic activity. And he has tried almost 200 substrate, and finally he would be able to come out with one suitable material for this activity. And this is the work of Dr. C.S. Purohit, which he has mainly worked in the area of molecular capsules and encapsulations. These molecular capsules, it is mainly suitable for binding with the cations, anions, and neutral substrate. And in this case, what he has done, he is able to do the reactions inside the capsules and also encapsulate with the higher unit, something like a benzene or a anthracene or a naphthalene unit inside the capsules. And his group also able to synthesize the favipiravir aquavir drug, that is, of course, already it is available in the market. And he is trying to come out with the substrate derivative of various favipiravir, whether he can do the collaborative work with the industry, that he is trying to explore the possibilities. And his group also involved in the design of an enzyme-like system with a predefined metal organic porous material. And also he is mainly working on, currently he is mainly focused on metal organic framework based silver and copper complexes, which he has synthesized, and the further studies are currently going on in his group. And this is the last one where Dr. Nagendra Kumar Sharma is mainly working on synthesis and biochemical evolution of gene-based therapeutic drug candidate. And his group is mainly involved for dideoxynucleoside triphosphate analogs and synthesis and polymerase substrate activities of prolydinyl nucleoside triphosphates. And he is also involved for the synthesis and biochemical evolution of aminopropanyl thymine triphosphate, where it mimics the DNA duplex kind of the structure at the solution state. And his group also involved for the amino acid amide bond instability comprising of 2 aminotropone moiety, which is cleavable under mild acidic conditions. And he has also come out with the instability of amide bond with a trifluoroacetic acid and confirmed its synthesis, conformation analysis, and mechanistic insights into cleavable amide bond comprising beta-troponyl hydrogeno acid. And he is also involved in unusual pseudopeptides and synthesis and structural analysis of these derivatives, and also come out with the respective complexes for this purpose. This is some of the state-of-the-art instrument facilities which is available in NISER, and we have powder XRD, single crystal XRD, microfocus XRD, and 700 MHz TCS-PC, GCMS, ESAMS, EPR, and fluorescence spectroscopy, which we have in the department. And we have also indigenously built by Dr. Himanshu Biswal, that is building scientific instrument that is called supersonic jet spectroscopy, which is indigenously assembling at NISERS. And with these facilities, and we have able to publish the paper in various general chemistry journal and also core journals. And so far we have published 598 papers, and then out of that 150 are from the integrated MSc student, and with an average impact factor of 4.5 to 5. And this is one last slide before concluding the things. This is the new app which we have come out where Dr. Himanshu Biswal has come out with. When we wanted to measure, suppose we wanted to measure the absorption spectra for the particular sample, take potassium permanganate, KMnO4, you take a potassium permanganate, you dissolve the material, keep it in the machine and run the machine, find out the absorption spectra, and after that you find out the excellent molecular absorption, molar absorption coefficient, all those things one can do. Now, what he has come out with, he has preloaded material, everything is there in the app, and then he can record, just you give the compound name, it record immediately the KMnO4 spectra, and also able to show the absorption spectral data, and with the peak you can find out the epsilon coefficient, and also you can do further studies. This is for the students of undergraduate and the teachers, those who are not having the facility at the village side, he has come out with the app. So he is also there in online for any further question which he has answered for this kind of the thing. What he has kept the name as village, that is virtual laboratory experiments for graduates. This is not only for UV visible data, and he has also included IR, NMR, fluorescence, all those data which he has included. This is more suitable for the village people and where the sophisticated institute, we have all the facilities, we can do whatever we want. But for the village people, it is not possible to have such facilities which he has come out with such a thing. Finally, thank you very much for your kind attention.
Can have one or two quick questions. Let's thank the speaker.
Thank you.
Thank you, Professor Nanda. We are going to continue to session 8 without any break. To chair this final session, I humbly invite Shri S.V. Nake, the Director of Raja Ramana Center for Advanced Technology.
Thank you very much. Good afternoon, everybody. Due to overrunning of the previous session, we are continuing without a break. So without losing any further time, I invite next speaker who is online. It's from HRI, Anshuman Maharana. Anshuman, please greet the audience here so that we can confirm your presence and audio quality also. Yeah, please unmute, Anshuman.
Am I audible?
Yeah, but the volume is a bit low.
Hello, is it clear now?
Yeah, please.
Okay, thank you. I'll share screen.
Yeah, you have 30 minutes sharp and maybe one or two quick questions after that. So please stick to your time limit. And stage is yours now. Please continue.
Thank you. Just a second. I think I'll have to reshare because now you can see my whole screen. Is that? Just one second. I think there's some issue with the screen share.
Oh, full screen and it is quite clear. Please continue.
Is it clear now?
Yes.
Okay,
yes, it is clear.
Just one second. I think there's some small adjusting I have to do from my side because it's. Thank you. So I'd like to begin by thanking the organizers for organizing this meeting and giving me the opportunity to speak. And as the title of my talk indicates, this talk is going to give an overview of research, manpower generation, and scientific facilities at the Physical Sciences Division of HRI. In keeping with the spirit of the conference, my choice of topics is going to be guided by the following question, that is, how can we strengthen connections within the HBI family? And since the audience is broad, and I understand that the idea is to initiate discussion within the HBNI family, my discussion will be mostly on the qualitative side. So let me start with a few introductory words about HRI. HRI is a small institute, and at present the physical science division consists of 15 faculty. We can grow to around 20. And with 15 faculty, we work in 5 research areas. And the work done is purely theoretical. We have no research labs on campus. So naturally, we don't take up goals which require large scientific manpower or aim to complete the full circle in a big problem, but our goal always has to be to be a place where various scientific ideas come together. Therefore, connections lie at the heart of our philosophy. And in this, I'd like to emphasize two important aspects of our process. The first is that although our work is purely theoretical and in basic sciences, but much of our work is motivated by and aimed at applications. And an integral part of this process is generation of high quality manpower through our PhD, MSc, or postdoctoral research programs. And of course, I'll get into the details of both these aspects during my talk. So now to the main part of my talk. It will consist of three parts. First, I will describe the various areas of research of it in HRI, then talk about manpower generation, and finally describe the scientific facilities and infrastructure that we have on campus. Okay, so on to the areas of research. We have, as I said, we have 5 divisions at physical sciences in HRI, but we like to club them into 2 broad categories. The first is high energy, where there are 3 areas: high energy phenomenology, string theory, astrophysics, and cosmology. And then there are the low energy divisions, which consists of computational material science and condensed matter physics. Within condensed matter physics, there are 2 areas that are being pursued. First is many-body physics, and the second is quantum information. So now let me describe one by one each of these areas. I will start with high energy phenomenology. Here there are 3 faculty members working. I'll start with a broad overview of the field. So at present, the standard model of particle physics is very effective in describing the interactions of elementary particles that we have probed by present-day experiments. And it has provided us with a quantum description of the strong, weak, and electromagnetic forces. And the discovery of the Higgs boson at the Large Hadron Collider has completed the particle content of the theory and enhanced our confidence on the model. However, the standard model does not address many important phenomena that we observe in nature. To list a few, it fails to explain 80% of the matter density of the universe, called dark matter. It fails to explain the particle and antiparticle asymmetry in the universe, called baryon asymmetry. And finally, there are large hierarchies in the masses of the elementary particles that we observe, and there's no explanation for these hierarchies. So the HEP research program at HRI is driven by phenomenological consideration, and it aims to address such questions. And the group essentially takes a 2-pronged approach. The first is identifying new physics that addresses intriguing questions in particle physics and cosmology. And having done that, it develops strategies to confront the standard model and these physics extensions by both collider and non-accelerator experimental facilities. Those can be terrestrial or extraterrestrial via satellites. Now, let me describe some of the key areas of research that are being carried out by the group. So, as I said, the Higgs has been discovered at the LHC, and this is a new gateway. So, active study of Higgs physics, possible generalizations of the simplest scenario for Higgs are being carried out in search for beyond the standard model physics. Also, heavy standard model particles can be interesting probes of new physics. So, targeted analysis of their physics in the context of a large hadron collider or the proposed international linear collider are being carried out using advanced techniques like machine learnings. Collider signals from grand unified theory, motivated and other neutrino mass generation models are being studied. And finally, India is a very active member of the CMS experiment at CERN, and the HRI group also has regular collaborations with CMS experimentalists at CERN, and in fact, previous analysis done by the group has been used by CMS experimentalists. With that, I will move on to string theory. This has 3 faculty members. As I said, the standard model provides us with a quantum description of electromagnetic, strong and weak forces. But a quantum description of gravity is still lacking. And string theory is one approach that aims to fill this gap in. Now, the formulation of the theory is still not complete, but the understanding is that when we understand quantum gravity, then we will be addressing many of the puzzles that arise in particle physics and cosmology that I alluded to. So there are various routes that one can take to introduce the subject. I will take the route through black holes. So quantum gravity is relevant in the regime of strong gravity. Thus, black holes are a natural arena of study while trying to develop a quantum theory of gravity. Now, the study of quantum physics of black holes has been very fruitful, apart from leading to understanding of various aspects of quantum gravity. It has led to the development of interesting theoretical tools that can have broad applicability. And it is this aspect of string theory that I will focus on. So let me start by describing some basic aspects of black. In classical gravity, as we well know, nothing escapes black holes, and hence their name, black holes. This changes when we incorporate quantum mechanics. Quantum mechanically, black holes are not just absorbers, they radiate. And when one calculates this radiation is precisely of Planck's black body form with a temperature that is determined by the mass of the black hole. And this suggests that one should think of black holes as thermodynamical objects. One can carry out study of various aspects of black holes mechanics, and then one sees that this expectation is indeed confirmed, and consistency of black hole mechanics implies that we attribute an entropy to black hole. And this entropy is proportional to the horizon, which can be thought of the boundary of the black hole region. So the entropy is proportional to the area of the bounding region, the horizon of the black. This is contrary to what happens in other systems, because we know that entropy is supposed to be extensive and proportional to the volume of the system. This led to the idea of holography. So the idea of holography, which was initiated to address this puzzle that how could entropy be proportional to the bounding area, is that a gravitational system is supposed to have an alternate or a dual description in terms of a theory which lives at its boundary. So we have a gravitational system, we consider its boundary, the boundary of the region in which the theory is defined, and then we write a usual non-gravitational theory on this boundary, and for a suitable choice of this non-gravitational theory, we should be able to describe the complete dynamics in the interior. And this idea, which essentially just arose as to address a puzzle in that about entropy, has been explicitly realized in string theory. And the precise mathematical form of this dictionary between interior and boundary degrees of freedom is called the holographic dictionary. Right now, the holographic dictionary is an area of active research, but we have already learned enough about it to start making use of it in interesting areas. So the attractive feature of this dictionary is that the dictionary relates the gravitational theory in the classical regime, so Einstein's gravity, which we know and understand, to a strongly coupled theory in the boundary. So the description, the alternate description of Einstein's gravity is a strongly coupled theory in the boundary. Now, this has been used to study strongly coupled theory. So leaving aside quantum gravity, this method is something that can be used to study strongly coupled theory by exploiting the fact that the strongly coupled theory, which usually because it is strongly coupled, we don't have conventional methods, analytic methods to carry out computations in, can be studied by using classical Einstein's gravity. So holography provides a new way to study strongly coupled systems, and that is just by studying classical gravitational systems in one higher dimensions, because it's the interior of the boundary. This idea has found applications in various settings, for instance, transport properties of fluids in strongly coupled systems at finite temperature. Phases of strongly coupled condensed matter systems have been analyzed. The results are very encouraging, but it's fair to say that everything still is at the toy model level, in the sense that if somebody is asked to give the gravitational description of a particular strongly coupled system, then we don't know the answer. But progress is taking place as we understand the holographic dictionary better, and it is clear that progress will involve people from various communities working together. So now let me describe some of the current areas of research in string theory at HRI. So one of them is understanding high energy behavior of string theory. The second is string cosmology, where we try to understand the implications of string theory at very early times in the cosmological setting. And finally, the development of the holographic dictionary and applications that I talked about in detail. Now let me come to astrophysics. Here we have one faculty member, and of course it's an area where we would like to grow. The key areas of research in astrophysics are general relativistic and post-Newtonian formalism of black hole accretion and accretion of compact objects in general, quasi-periodic oscillations of black holes and neutron stars, the astrophysics of our galactic center, and stability properties of astrophysical fluids under strong gravity using both linear and nonlinear perturbation theory. In this context, chaos is also studied. Okay. Now let me move to the low energy divisions. I will start with computational materials modeling. There are two faculty members working in the area. Innovation in materials based on basic sciences plays a central role in technological progress. And motivated by this, the computational materials modeling divisions is involved in the design of various futuristic materials. So just let me describe a few that are being currently developed at HRI. The first is in the area of photocatalysis for hydrogen production from water. Typically, platinum is used as the catalyst here, which is very expensive. So design efforts are taking place for two-dimensional materials which have the right catalytic properties. The second is in the area of solar panels, where hybrid perovskites are being studied as substitutes of silicons. These materials have both organic and inorganic components, and they're easier to manufacture in a lab. The specific challenge that is being addressed at HRI is how to increase their efficiency. Finally, there's research on sodium-ion batteries, which have the promise that they can be charged very quickly and the discharge time is a lot slower. Also, the deposit of lithium on the planet is not uniform, so it is very important to get away from complete dependence on lithium-ion substances. So apart from the design of futuristic materials, another very important aspect of material modeling is the development of new methods. Much of the progress in the field in the past 2-3 decades has relied on density functional theory. But now there are novel emerging methods, and these are being actively studied and developed at HRI. So the first is quantum electrodynamical DFT. So the idea behind density functional theory is that one does a ab initio simulation of the material, and based on what we learn about the material, one infers the interaction properties of the materials. The idea behind quantum electrodynamical DFT is first principle incorporation of the light-matter interaction. So the interaction part with light is incorporated into ab initio simulations. This is expected to give very powerful results regarding the properties of the interactions and will lead to a lot of progress in designing new materials. The second is machine learning. As we all know, ab initio simulations are very expensive in terms of time. So one uses machine learning so as to arrive at interesting candidate materials. So this really narrows down the search, and after that is done, one can carry out ab initio simulations for the already interesting class of materials which one has looked for a certain purpose. The research is interdisciplinary by nature. The efforts at HRI are part of various national and international missions. These include the Center of Excellence on Carbon Capture and Utilization at JNCASR for capture of carbon dioxide, the Center of Excellence in Materials for Futuristic Mobility at IIT Madras for electronic car batteries, the International Energy Research Institute at NTU Singapore for solar cell related research, and also the National Supercomputing Mission. Now we move on to quantum many-body. There are 2 faculty members in the area. I will focus on the work on correlated electron systems at HRI. So correlated electron systems define a frontier in condensed matter physics. These materials are usually based on D or F shell elements and which involve compact electronic orbitals. And this leads to enhanced electron-electron interaction. The first consequence of this is the failure of band theory, which is usually the starting point when we study the quantum theory of solids. And in the 1930s, with the discovery of high TC superconductivity in doped La2Cu04, the field really opened up. And soon after, there were discovery of effects like giant magnetoresistance, huge thermal power, which are phenomena of great practical interest. So there's a lot of value to develop a good theoretical understanding of these kind of materials. Now, the strong interaction that generates the collective states in here also makes the theory of these materials very difficult. One strategy is to treat the original interaction in terms of the coupling of the electrons to a quote-unquote slow variable, which for instance can be the nuclei in the solids. Now, once one does that, the ratio of the slow variable velocity to the electron velocity acts as a small parameter in the problem. And at HRI, Monte Carlo tools have been developed to address electron correlation problems within this framework. This has allowed for progress on several fronts: magnetism and superconductivity, real-time thermal behavior, and finally, parts of which is still work in progress, is understanding non-equilibrium situations. Now I come to the final topic, which is quantum information and computing. Here we have 4 faculty members. Quantum information and computing exploits the fact that quantum systems have far richer dynamics compared to the classical ones. A classical system with n bits, with a classical system with n bits, we can do manipulations with integers from 0 to 2 to the power of n minus 1 with n bits. But a quantum system with n degrees of freedoms, which are called qubits, is characterized by 2 to the n minus 1 complex numbers. So on one side, we have 2 to the power of n minus 1 integers, and here we have got complex numbers. So this immense difference is what makes quantum computing attractive. Since we're dealing with quantum systems for computations, gates are unitary operations and algorithms are successive unitary operations. And what really has made quantum computing a subject of high interest is that quantum algorithms can be significantly more efficient than the classical ones. For example, let's consider the factorization of large numbers. This plays a very important role in cryptography. Now here, the quantum algorithm, which goes by the name of Shor's algorithm, is exponentially faster than the classical one. Therefore, quantum information computing, quantum algorithms, quantum hacking preventions are considered central for all high security settings. There's a growing consensus that we will be entering an era of quantum revolution in the next 2-3 decades. This is seen by the fact that internationally there's massive investment in quantum computing and theory. In response, the government of India has initiated a national mission on quantum technologies and applications. So this is a 5-year national mission that the government of India has initiated. The QIC group at HRI is very much at the center stage of this mission. Important contributions have been made by the group. To list a few, there is the entanglement witness algorithm. So an algorithm which gives a Boolean answer to the question whether two systems are entangled or not. Characterization of entanglement when multiple parties are present and whether each party is entangled with all the others. So characterization of multi-party entanglement. And the study of the effect of noise on Shor's algorithm. In the last 2-3 years, there has been very rapid progress in the field. In 2017, IBM could manipulate 27 qubits. In 2022, that number is 500. At the same time, it's fair to say that the field is young and there are a lot of developments still going on. This is seen by the fact that the world record for implementation of the Shor's algorithm, the algorithm that I talked about in the context of factorization of large number, here the world record is still for 2-digit numbers. So this is something that internationally people are trying to push up. The real challenge is reliable control of quantum dynamics. And once we have control of quantum dynamics in a particular setting, finding the algorithms which are optimal for those settings. And obviously here there is a lot of room for collaboration on the technological side, trapped ions, NMRs, superconductors. Input from mathematicians on the algorithms is very important, and we do have expertise in all of this within the HBNI family. So now I'm done with the discussion of areas of research, and I'll talk about manpower generation and the new MSc program. Generation of high quality manpower through our teaching programs, postdoctoral programs has been central to HRI's vision from the very beginning. The first PhD was awarded in the year 2000. And since then, within a short span of 20 years, over 80 HRI physics alumna are already faculty in leading institutions of the country. In fact, happily, many have come back to HBNI now as faculty. When getting feedback from alumna formally and informally, HRI came to know that one of the reasons for the success of this its programs was a rigorous coursework that gave the students the necessary foundation to evolve into independent research. So we found out that this rigorous coursework that was there as part of the PhD program was playing a very important role. And this gave us confidence around 2015. HRI felt that it was ready to provide education at the MSc level. We put a proposal forward, and both DAE and HBNI were very generous and accepted the proposal. An MSc program in physics was started in 2016. In the first few years, we saw around 10 students. But now we have a full batch of 20 students. With an MSc, the idea is not just to produce students who have expertise in our core areas of research, but have students who are essentially well-trained and all-rounders. So therefore, we now have an MSc lab on campus, although we don't have a research lab, but still we now have a lab on campus. And as this program takes off, there are some questions that we discussed repeatedly, that is how to train students who want to do a PhD in any area of physics, or how do we train students who want to join the industry after finishing our MSc. And we hope that you will contribute to these discussions. You will, and we will learn from HBNI on these issues. And hopefully, very soon, you will be having an HRI MSc as your PhD student. Now that we come to the last part, which is research facilities and infrastructure. So the first is the cluster facility. A lot of the work that we do at HRI is computationally intensive. So a high performance computing facility was established at HRI with the 10th plan. And this has been expanded since then in every plan, and we are now at 160 teraflops. The computing facility has been set up as a shared resource which is brought together by all groups. And this has worked out wonderfully, both in terms of the computing power available to each group and also economically. Also, our computing powers are ever growing, so we plan to expand on this facility and also to join various national computing initiatives. Now I come to our library. We have an excellent library. There are around 20,000 books on shelves, many of which are rare. Around 2,500 ebooks, subscription to 50 physics journals, mostly via the DAE consortium. And this balance of latest journals, ebooks, and rare volumes makes it very useful to carry out research. It's open for 360 days in a year, above 20 hours a day. So it's the ideal place for our students to study on campus. So that brings me to my conclusions. HRI has a very active physical sciences division working on various cutting-edge problems in theoretical physics. Although we work on basic sciences, we always have had and will have an eye towards applications. I think that should be evident from the presentations. Many of the problems are interdisciplinary by nature. So collaboration within the HBNI family on these is very natural. And finally, while continuing on our well-established PhD program, where we will be producing good students in our core areas of strength, we have started a new MSc program where the goal is to produce students with a wide range of expertise. So with that, I'll end and thank you.
Thank you, Professor Ashutosh Maharana. Now, if there is any question from the audience, or otherwise we'll move. There is one question online. I think it is visible to you, Dr. Ashutosh. Sorry, Anshuman.
Just a second.
What kind of properties you intend to compute quantum electrodynamics DFT, and do they include near field measurements in the sub-diffraction limit?
So, since I'm not an expert in the field, I might not be able to answer this, but I think my colleague, Dr. Sudeep, should be online and he might be able to answer this.
Okay, in that case, I think the person from IGCAR. Okay. Yes, Sudeep, please unmute and then you can answer.
Yeah, okay, perfect. So can you hear me?
Yeah, it's clear.
Yeah, okay.
Please.
Yeah. So the thing is actually the quantum electrodynamics DFT is kind of a new things that we are planning to do right now. So it's kind of whatever we are doing in development and application of DFT, which is basically the ground state property of any materials kind of to emphasize their different properties. But then if you really want to do the excitonic property of this material to actually see the optical properties, so you have to go beyond the ground state to see the excited state property. And that exciton cannot be really captured accurately in the DFT calculation. And for that, one methodology is there, which is the time-dependent DFT. But there it's kind of a more classical. In the quantum electronics DFT, it's more like a quantum approach in order to see the polariton effect there. So right now it's not included in that, but we are trying to kind of involve that. That's a really nice suggestion. So currently what our focus is actually to see the polariton effect and how the polariton is, I mean, as we are kind of doing extensive work on the hybrid perovskite material for the solar cell. So, I mean, excitonic properties kind of should be the bread and butter of that. And we are trying to tackle this problem from the excitonic dynamics there. And there the QEDFT comes there in the picture. Yeah, if that answered the question. So that one is we haven't included yet, but yeah, it's in our to-do list actually. It's a really nice question.
Thank you, Dr. Sudeep. I hope there are no more questions. Yes, Satyaram. Dr. Satyaram Mishra from Dean Academic, RRCAT.
Hello, Professor Anshuman. I just wanted to know in quantum information, this entanglement theory is considered with which kind of system? Either ions, trapped ions, or with NMR, or with trapped atoms, or with superconductors?
I think that all of these things are being used in the development of the quantum computers. And as I said, the challenge is to find which one is the best. Maybe my colleague, Dr. Debraj, he might be present. He could add more. I think he's present. So he probably shows us DR.
Yeah, Dr. Devraj, you may have to unmute yourself and then. It seems there is no response from Dr. Devraj.
I think now.
Okay, I think Dr. Mishra can contact.
Hi.
Yeah, he's
Okay.
there.
I was struggling to unmute myself. Yeah. So can you listen to me?
Yeah, you are audible.
Okay, so as Anshuman rightly said, that means there can be different kind of physical substrates on which this quantum gates can be designed, and if you look into these big companies like Google, Microsoft, what they are mostly adopting is superconducting qubits. Okay. So, but in research labs, there are certain labs who are doing in trapped ions or even ultra-cold atoms or things like that. So they are trying to broaden the horizon. And so in superconducting atoms, as Anshuman also said, that it's of the order of 100 now that we can manipulate. So we cannot really implement means like, for example, the Schwartz algorithm is limited to only 2 digits. So we really cannot go and deal with a very big calculations. So that's the directions that experimentalists are trying to broaden using different other kind of substrates beyond superconducting qubits.
Okay, thank you.
think it's clear.
Yeah.
So let us thank speaker, Dr. Anshuman Maharana, for his presentation and covering various topics in the areas of high energy physics and low energy physics, right from their theoretical applications to the practical problems like sodium batteries and other aspects in the area of astronomical research also. So thank you, Dr. Anshuman Maharana.
Thank you.
Now, there are two more presentations from next speakers, but I think before that there is announcement from organizers, because although the audience is very curious for the next talks, but there seems to be some problem with the projection system. So we'll have a short break. I think there will be
Yeah,
announcement.
we'll take a short break for 5 minutes because there's some problem with the projector due to overheating. So very quick break, and in 5 minutes we'll resume the session.
So this is a short break for projector basically, and we'll be back within 5 minutes. And sorry, the presenters from IGCAR, Dr. N. Sivaraman and NV Chandrasekhar will be taking a short break for the projector. So we'll be back within 5 minutes.
Slide no. Am I audible there? Anurag? Just.
Yes.
Am I audible?
Yes, sir, you're audible and slides are also visible.
Okay, that's great. Fine. Slides are, you are able to see the subsequent slides?
Yes, yes.
Okay, that's fine. You can make no continuous slides so that you'll save time. After me, just they will change over.
Welcome, Dr. Sivaraman. Your slide is clear and visible. I invite all the participants who are present in person to be present. The session is going to start very soon.
Sir, could I commence my presentation?
Okay, yes. Sivaraman, you can start with your presentation.
Okay,
You have
sir.
30 minutes total, and please stick to the time schedule.
Sure.
And we'll have a few quick questions after that. So,
Dear colleagues and friends,
yes.
good evening, and it's a special privilege to present the work on the research work of scholars, chemical sciences discipline of HBN and IGCAR in this session. Especially, I'm pretty happy that I shared the session alongside my batchmate and colleague, Dr. Shankar Nake. So I'm pretty happy about that. Some of the key research areas examined by the research scholars in the chemical sciences discipline are listed here. The parenthesis shows the approximate population of the students who have examined and looked into various research areas. Some of the important areas includes chemistry aspects, especially related to fuel reprocessing, fast reactor fuel reprocessing, because the major challenges involved in fuel reprocessing, especially with reference to fast reactor fuels, involves use of high plutonium, high radiation, and high fission product contents, approximately about 10 to 15%, much higher than the thermal reactor fuel, that is the PHWR fuel. So about 7 research scholars have looked into some of the R&D aspects on the synthesis on alternate molecules to tributyl phosphate, which has been well established in the nuclear industry over the past 60 years. TBP has wonderful properties. It can extract the heavy metals like uranium, plutonium. You have excellent decontamination factors from the fission product. However, when it comes to question of fast reactor fuel reprocessing, it has certain limitations, especially when it is contacted with plutonium, because it forms a third phase, which I will discuss in due course, as well as the solvent is subject to intense radiation degradation as well. So our scholars have examined this aspect, and they come out with alternate molecules. And there are 2 important molecules which I would discuss in due course of the presentation. There are scholars also contributed to some of the thermochemical and thermophysical properties of nuclear materials. The key challenge in this area is basically putting the facility in radioactive glow box environment. And the Knudsen efficient mass spectrometer facility has been incorporated in the radioactive glow box, and our scholars have measured the high temperature vapor pressure measurements on uranium plutonium alloys in this facility, one such facility. Scholars also examined alternate coolants to liquid sodium, because sodium is used as a coolant in fast reactors, and the alternate coolants are potential alternate coolants are lead and bismuth, and our scholars have examined the interaction of lead and bismuth with various structural materials. As far as oxide fuels are concerned, both in thermal as well as fast reactor fuels, as well as carbide-based fuels, Purex process is well-established process for reprocessing the nuclear materials. Purex process basically involves once a spent fuel is taken, chopped, dissolved in appropriate concentration of nitric acid, the oxidation state of plutonium will be altered accordingly. It will be contacted with TBP dodecane. Uranium, plutonium will be extracted with the organic phase, and it will be decontaminated from the fission products as well as minor actinides. However, for the proposed future metal fuels, which will be employed in the fast reactors, the best route for reprocessing is non-aqueous based process, which is called pyroprocess. Basically, in this process, the spent fuel is used as an anode, use electrorefining method in the presence of molten salts of lithium chloride, potassium chloride, and use a suitable electrode like cadmium electrode, and selectively deposit uranium plutonium from the anode basket, leaving the noble metals in the anode basket and leaving the fission products in the salt phase. The challenges mainly involved are handling corrosive salts at high temperatures. So our scholars have contributed basically to development of various electrochemical processes. Next aspect is the corrosion studies on nuclear materials. This is also an important area because we do handle chlorides and fluids at high temperatures, and scholars have contributed significantly to the corrosion studies on nuclear materials. About 10% of the scholars have worked on the use of green chemistry for actinide separations. The two important molecule includes supercritical carbon dioxide and room temperature ionic liquids for exploring these properties. The scholars have employed both these room temperature ionic liquids as well as supercritical carbon dioxide for selective extraction of actinides from various matrices. The actinide separation and development of burn-up monitors is an important area because not much work has been done for fast-reactor fuels, and our scholars have examined this critical aspect of measuring the burn-up of fast-reactor fuels. They have developed alternate burn-up monitors, especially lanthanum 139 as a monitor for fast-reactor fuel, and molybdenum as a total molybdenum for thermal reactor fuels. Traditionally, neodymium-148 is used as a burn-up monitor for thermal reactor fuels, and there are not many literature data for determining the burn-up on the fast reactor fuels, and our scholars have come out on that. So this demands fast separation of the heavy metals from the fission products, host of fission products, and purification and do by chromatography as well as mass spectrometer. The novel materials for separation that includes use of new materials, either magnetic-based separations or using metal organic frameworks. And scholars have employed this for recovery of uranium from lean streams. About 12% of the scholars have contributed to probing the intermolecular interactions using matrix isolation spectroscopy techniques, where in this technique, organelle will be used as an inert matrix. The molecule of interest will be trapped and will be examined. So hydrogen bonding, phosphorus-based bonding, nitrogen bonding, chalcogen bonding, and many interactions have been probed. And some of the important outcomes include identification of a suitable conformer, which might be responsible for third phase formation as well. In the recent past, to support our experimental data, we have computational chemistry measurements on actinide complexes, where we do the elucidation of geometry of the ligands, geometry of the metal complexes, and measuring the complexation energy. And the key interest is to corroborate our experimental distribution data with the computational aspects. And we made some progress in this aspect. Development of sensors for nuclear and chemical industry is a very key area because some of these sensors are not available to nuclear industry, where the sensors have to work in harsh environment. So our scholars have developed semiconductor oxide-based sensors for detecting hydrogen in cover gas, ammonia, NOx, etc. Waste matrices, an important research area for nuclear waste immobilization, and about 5% of scholars have contributed to that. And 2% of the scholars, two scholars have worked on the development of strontium-89 as well as phosphorus-32 as radioisotopes for societal applications. So I shall reflect on some of these important areas. Am I audible, sir?
You are quite clear.
Yeah,
please continue.
Yeah. One of the important areas which I mentioned is tributyl phosphate, which is extensively used in nuclear reprocessing industry. It has certain limitations. It forms third phase with plutonium. It forms third phase with tetravalent metal ions, especially zirconium and thorium, which basically put a constraint on the throughput in the nuclear reprocessing industry. So our scholars have synthesized various organophosphorus compounds that includes triisobutyl, tricycloamyl, tricyclohexyl, trisecondary butyl, T2MBP, trisecondary amyl, and triisoamyl, triexyl phosphates, etc. Basically, the scholars have examined the potential extractants which retains all the important properties of tributyl phosphate. However, also should overcome two important limitations of tributyl phosphate, namely the aqueous solubility and the third phase formation. Third phase formation is undesirable in the nuclear industry, especially in reprocessing, because traditionally you should have two phases: the aqueous phase containing the spent fuel in nitric acid medium, the organic phase contains TBP and dodecane. And during the course of contacts, heavy metals will go to the organic. But in certain cases, the organic will split into two phases, which is undesirable. So basically, our scholars have examined this aspect and come out with two interesting molecules, T2MBP and triisoamyl phosphate. In one such study carried out by the research scholar, we have put a radioactive glow box for handling uranium-plutonium dissolver solutions. The uranium-plutonium dissolver solutions, along with certain fission products with americium minor actinides, were separated in a radioactive glow box using triisoamyl phosphate, which is a potential alternate to tributyl phosphate. So the heavy metals were selectively separated with excellent decontamination factor on par with tributyl phosphate. Also, this molecule was examined for separation of yttrium, strontium, uranium, thorium separation. The extraction behavior of fission products like ruthenium and zirconium, which are troublesome, especially during the course of fast reactor fuel reprocessing, and radiation degradation behavior. These are the typical results. I will not go into the detail. All I would like to say is the two important molecules developed by our scholars, triisoamyl phosphate and T2MBP, the distribution coefficient for uranium plutonium are on par with TBP, whereas the extraction of troublesome fission products, they are lower than TBP. So which qualifies these molecules to be examined in nuclear fuel reprocessing plant. And our scholars have also examined this third phase formation phenomena using different methods, including scattering techniques, and shown that these two molecules qualify. The highlights are reflected on here. The physicochemical properties, especially the density, viscosity, interfacial tension, they are comparable with the well-established solvent TBP. The aqueous solubility is marginally low, which is very important. The extraction of troublesome fission products, especially zirconium and ruthenium, are lower for the molecules developed, and that chemical, radiation, and thermal degradation are on par with the established molecule tributyl phosphate. Added to that, these two molecules do not form third phase. So we have come out with these two interesting molecules which are qualified or potential alternate extractions to tributyl phosphate. I'm sure we will examine these molecules some stage in the near future. In addition to the organophosphorus compounds, another branch of compounds of interest are phosphoramide compounds. Recently, one research scholar has synthesized a series of phosphoramide-based compounds and demonstrated its application for separation of actinides. The compounds of the phosphoramides, basically propyl, butyl, amyl, xyl as a propyl, butyl, were synthesized, characterized. The physicochemical properties are measured. The actinides were extracted, especially uranium, plutonium, thorium, as well as americium. The results are shown here. The decontamination factors wise, it is pretty good, on par with TBP. Aqueous solubilities are low, and it do extract uranium and plutonium. Of course, we have to consider the economics. These are the early days for this molecule, but it's shown a tremendous potential phosphoramide-based compounds. One of the scholars demonstrated the dissolution kinetics behavior of MOX fuel, which is used in nuclear reactors, fast reactor fuels. So his study has shown the preferential dissolution of uranium over plutonium. This is very interesting. And this study provided a methodology for understanding the dissolution kinetics of the spent fuel. This is, I was talking to you about the third phase formation. This is a very crucial aspect in nuclear fuel reprocessing industry, where the aqueous and organic phase, when it is coming into contact, especially when the plutonium concentrations are very high, the organic phase split into two phases, the metal rich and diluent rich, which is not good for the plant. So hence, there are two things: you load the plutonium less or use another molecule which doesn't form third phase. So in that context, our scholars have come out with two interesting molecules, namely T2MBP and triisoamyl phosphate. Room temperature ionic liquids are very interesting molecules, gained a lot of prominence over the past maybe 15 years. Variety of room temperature ionic liquids were synthesized at IGCAR. Basically, they are comprised entirely of ions at less than 100 degrees. They have a wide electrochemical window, negligible vapor pressure. So this enables the researchers to modify the properties. Toss-specific ionic liquids, especially, they were functionalized with phosphonates, amides, and diketonates. They were employed for dissolution of uranium-based oxides. Another interesting application is from the aqueous phase, selectively some of the metal ions were extracted, including uranium and noble metals like palladium, and they were directly electrodeposited. The electrochemistry aspects of uranium lanthanides and ruthenium, rhodium, palladium were also examined from ionic liquid medium. Another interesting application is recovery of uranium from the cellulose matrix, because our laboratory operations, we do generate a lot of cellulose waste containing actinides, and the scholar has demonstrated complete recovery of uranium from the cellulose matrix by using an appropriate ionic liquid based on BMIMCl. So exploring the possibility of room temperature ionic liquids provides an interesting area for lanthanide actinide separation. The remarkable outcome of these studies are they display unusual extraction behavior. For example, the separation factors for uranium and thorium in some cases are much higher than compared to the traditional molecular liquids. And most of the occasions we have seen, they don't form third phase. So these are the two interesting aspects, the work on the ionic liquids. Our scholars, 3 scholars have examined the use of supercritical fluids in nuclear industry. Traditionally, supercritical carbon dioxide is used in chemical industries for purification of natural products. However, our scholars have fine-tuned its properties. Basically, supercritical carbon dioxide involves use of pressures and temperatures beyond the critical point. The critical temperature for carbon dioxide is 73 bar. The critical pressure is 73 bar, and critical temperature is 35 degrees. Once you apply these conditions, carbon dioxide will slip into a new state called supercritical state, where it will possess liquid-like density, gas-like viscosity, diffusivity, and surface tension. These properties enable carbon dioxide to penetrate into pores of the matrix and extract the components of interest. But basically, carbon dioxide is a neutral, non-polar molecule, so it can dissolve and interact only with non-polar molecules, basically organic compounds. However, what we do is we take carbon dioxide, we do introduce ligands like tributyl phosphate, various amides into the carbon dioxide stream and extract actinides from various matrices. So in this connection, a lot of fundamental studies were done on measurement of solubility of these compounds in carbon dioxide. And subsequently, these streams were employed for recovery of uranium, plutonium, americium from various waste matrices. So, because one of the major motivations for taking up supercritical fluid extraction base is waste minimization. Because after extraction, carbon dioxide becomes a gas, and you do minimize the waste. So we have also a facility of supercritical carbon dioxide in a glow box for making radioactive measurements as well. We have 2 systems, one for non-radioactive applications, especially the development of basic solubility, etc. And we have a radioactive facility for handling plutonium, americium, etc., using supercritical carbon dioxide. Other important solvent extraction results of trivalent lanthanides from actinides shown here. Scholars have developed new CHON-based ligands for separation of lanthanides and actinides. This is a very important area where the minor actinides have to be separated from the lanthanide fission products. And we have proposed, the important outcome is we have proposed a method for partitioning of trivalent actinides in a single cycle process, unlike the traditional 2-cycle process. So this involves synthesis of series of substituted diglycolamides, studying the properties, the interactions, the third phase formation phenomena, etc. And scholars have demonstrated that the new modified diglycolamide-based extractants are potential candidates for lanthanide actinide separations. Another scholar examined use of modified silica-based materials. What they have done is they have functionalized silica with suitable amine-based candidates. They examined the recovery of uranium from waste streams as well as lean aqua streams, including recovery of uranium from seawater. The capacities are pretty good. And in another interesting study, magnetic mesoporous silica for efficient magnetic assisted base separation was examined, where the oxide was coated with silica, functional with amine for the recovery as well. So these resins are prepared. They were used in column chromatography mode for the recovery of uranium from various dilute streams. Another interesting application is the supramolecular reverse meiosis of CHON-based ligands in organic phase. So this involves the preparation of 2 important molecules, dioctyl hydroxyacetamide as well as didodecyl dihexyl diglycolamide. These compounds are prepared and they were examined for separation of americium from neodymium in solvent extraction experiments. Basic fundamental studies were done, and this molecule, didodecyl dihexyl diglycolamide, showed a lot of promising application for separation of americium from neodymium. Metal organic frameworks have been examined by our scholars in the recent past, over the past 4 years. Basically, substituted phthalic acids, functionalized phthalic acids were reacted with appropriate metal ion like zinc, and the resultant morph was functionalized selectively for absorption of important heavy metals. So 2 important outcomes have come from this. One is absorption and recovery of uranium from aqua streams, absorption and separation of thorium from aqua streams. So these are the early days of a morph study, but shows a lot of other fundamental areas as well. Burn-up measurements on nuclear reactor fuels are a key area for fuel management, and not much data especially is available for the fast reactor fuels. So this measurement involves identification of an appropriate, suitable burn-up monitor and correlating its concentration to heavy metals, uranium, plutonium for burn-up measurements. Traditionally, reactor physics used calculation methods, and we use experimental method for accurate burn-up measurements. Basically, we use a combination of chromatography and thermal ionization mass spectrometry techniques to get the concentrations of the metal ion or the isotopic composition of the desired element. So we have basically examined potential fission monitors. Neodymium-148 is a traditional one. We have used neodymium-143. We have used neodymium-145 and 146. We have recently identified molybdenum as a fission product and lanthanum-139 because neodymium is well known, well established, but the yields of molybdenum are much higher. So we thought that use of molybdenum might potentially reduce the radiation exposure to the personnel. So in that way, molybdenum is good. And as far as to get the accurate data, neodymium-143 or 145 and 146 combination gives much better burn-up data compared to neodymium-148 because neodymium-148 as a burn-up monitor is established only for thermal reactor fuels. And we do have a fast reactor fuels, and our scholars have used the radioactive facility comprising the liquid chromatography. And the top chromatogram shows the separation of all the lanthanides. As far as my knowledge goes, this is the fastest separation reported in literature till date. One of the research scholars have demonstrated separation of all the lanthanides in about 2.77 minutes. The earlier one is about 3.6 minutes. So this is one of the important outcomes of the study. And subsequently, the system was put in the radioactive. The bottom chromatogram shows separation of the dissolved solution from the nuclear reactor. It was directly put into the liquid chromatography without much modification, just altering the acidity. You could see that all the fission products of lanthanides alongside americium, plutonium, and uranium. So what we do is we measure the concentration of uranium, measure the concentration of plutonium, estimate the concentration of neodymium or lanthanum, and once you have the data, we do get the burn-up. Another scholar recently examined the use of laser ionization mass spectrometry technique for computing the burn-up of fast reactor fuels. He has demonstrated the ratios of lanthanum to uranium remains constant over a complete range. This is a simulation experiment, and subsequently, this aspect will be examined for burn-up measurements on actual fuels. This is using laser ionization mass spectrometry technique. Recently, another scholar examined the use of laser ionization mass spectrometry technique for the determination of cesium and strontium in dissolved solution, as well as strontium. The present work involves basically how to overcome the isobaric interference, because you do get to have isobaric interference from strontium and barium. So use of LIMS technique, the scholar has successfully demonstrated the potential use of LIMS for the quantitative estimation of strontium and cesium and overcome the isobaric interference of zirconium and barium. Because optimized laser parameters will eliminate the isobaric interference by forming monooxide species of ZR and Ba, whereas strontium and cesium appear as the elemental ions. Since it's a simulated solution, you don't see that cesium-137. So we have done with natural cesium, which basically contains cesium-133, and natural strontium, which basically contains 86, 87, 88. And shown that appropriate use of technique like LIMS can lead to direct estimation of cesium and strontium in high level liquid ways without resorting to isobaric interference, because otherwise this method demands large amount of chemical work where you have to separate strontium and cesium from a host of other metal ions. So it's one of the interesting applications use of LIMS for estimating the fission products. Good amount of scholars have contributed to development of sensors for our both reactor program as well as for the chemical industry as well as for the reprocessing program. They have examined various semiconductor oxide-based materials. Our scholars have come out with use of tin oxide-based sensors for monitoring hydrogen. Especially this is useful for measuring its concentration in the argon cover gas. Ammonia in air, this is very useful for the reprocessing industry where we do use quite a bit of ammonia, as well as in chemical industry. A silver molybdate-based material was used, as well as a sensor for determining the NOx. This is very crucial, especially in the reprocessing industry. An indium oxide-based sensor was developed. The important outcomes are like this, because the detection limits are much lower compared to commercially available sensors. And most of the occasions, these sensors have to work in unique environment. So commercial sensors, most of the occasions do not meet this requirement. So hence our scholars have come out with synthesis as well as this sensor put to use. Most of them are under trial conditions now. This is an application which I was referring to earlier, thermodynamic measurements on nuclear materials. Of course, it involves over a period of about 10 years. It involves work of two scholars. A research scholar has employed this facility for measuring the vapor pressure of nuclear materials at high temperature. This is an in-house built Knudsen emission mass spectrometer located in a glow box. This is a radioactive glow box. So boxes operated using gloves kept under argon atmosphere. And the scholars measured the vapor pressure of uranium, plutonium, zirconium-based alloys, both 19 weight percent as well as 23 weight percent plutonium at high temperature. We also have another mass spectrometer, Knudsen efficient, for carrying out non-radioactive applications, where another research scholars examine the vaporization behavior of uranium, gallium, uranium, aluminum systems, ruthenium, tellurium systems. Some of them are fission products, some of them are used in reprocessing applications. One such application I'm showing here, LACL, KCl. It's basically the eutectic salt is used in pyrochemical process, and the interaction of uranium chloride with LACl, KCl, the scholar has demonstrated and measured the vapor pressure behavior at high temperature using the mass spectrometer. Ternary phase diagrams for bismuth iron oxide, bismuth chromium oxide, as well as bismuth molybdenum oxide, lead bismuth oxide, because these are the bismuth and lead are basically potential alternate coolants to liquid sodium in the fast reactor. So our scholars have examined their interaction with various structural materials. And these are the typical results. Another scholar, there are two scholars who worked on direct oxide reduction. It's a very important application where you keep the oxides of niobium, uranium, or titanium in one of the electrodes, basically in the cathode, and the platinum as anode. You do the electrolysis in a calcium chloride melt, and the electron transfer leading to reduction of uranium oxide to uranium metal, titania to titanium, and niobium to niobium metal. And the scholars have measured the course of the reaction using hydrogen sensors, and they demonstrated successfully on a small scale. About the one scholar has worked on the first application on the uranium scale, is demonstrated on about 50-gram scale on the reduction of uranium to uranium. As far as research programs on corrosion science is concerned, 3 scholars have contributed in the recent past. Pyrolytic graphite coatings by chemical vapor deposition for pyrochemical processing applications. That involves many components. That includes graphite crucibles, which should hold the molten metal at high temperature, graphene oxide-based composites, superhydrophobic based coatings, and nano inclusions. One such application known I am reflecting here, the deposit of pyrolytic graphite on CVD for pyrochemical processing applications. Another scholar has used iron oxide, manganese oxide, core shell-based nanoparticles for degradation of organic dyes. So the transition metal doped manganese oxide shell enables the efficient sulfate activation, while the magnetic core facilitates the effective recovery of the fused particles.
Yeah, Dr. Srinivasan, there is 5 minutes remaining for
Yeah, I'll be closing in another couple of minutes. Another scholar used the multi-walled carbon nanotubes. Quite a bit of scholars have contributed to probing the intermolecular interactions using matrix isolation spectroscopy. Basically, in this technique, what we do is sample of interest is diluted with a large excess of inert gas like argon. The conformational landscape of various organophosphorus compounds were examined. Basically, our interest are to explore, is there any conformer or TBP which basically leads to third phase formation. In this context, we have examined many organophosphorus compounds, model compounds like trisecondary butyl phosphate and tris-2-methyl butyl phosphate, etc. Photooxidation behavior examined, weak intermolecular interactions, hydrogen bonding, unconventional hydrogen bonding, a new type of interaction called phosphorus bonding, where POCl3 interaction with 5 base compounds were examined. A para-hydrogen facility was also set up in our laboratory to achieve some of these endeavors. A radioactive glow box facility containing IR spectrometer is also envisaged during the course of these research programs. Luminescence spectroscopy, 2 scholars have contributed to measurement of basically estimation uranium and europium in various streams in very, very low levels. One important application is estimation of uranium in primary sodium sample and detection of uranium, europium in very low levels. Basically, they use various organo compounds, aromatic carboxylic acids to achieve these targets. The computational chemistry work basically has been taken up to support our strong experimental groups to substantiate the experimental data which we do get to have on the distribution coefficient of metal ions, the geometries of ligands, metal complexes were done. The complexation energies of the resultant complex has been identified. Recently, a scholar has demonstrated the complexation energies of plutonium complex with TBP are much favorable compared to zirconium, because when you contact plutonium and zirconium with tributyl phosphate in N-dodecane, that leads to a distribution coefficient of approximately about 22 for plutonium, about 0.5 for zirconium. And the computation studies have shown that indeed these values are acceptable. A series of such molecules have been examined for the geometry and the resultant complexes. So basically our endeavors are to support the experimental data and to screen out the ligands which are appropriate for actinide complexes. As far as the waste matrices are concerned, borosilicate base and phosphate based compounds are examined in our laboratory. 3 scholars are working on this project. That includes basically zeolites, geopolymers, etc. They are mixed with appropriate quantities of borosilicate, and fission products, simulated fission products were mixed with appropriate quantity, and they do all the fundamental studies on that. Finally, strontium production. One scholar has worked on that, production of strontium by irradiating yttria in our fast reactor. Typically by NP reaction, you convert yttrium to strontium. The scholar has come out with a flow sheet for separation of strontium-89 from yttrium. This was prepared, radiochemically qualified, radiopharmaceutically qualified in collaboration with BARC as well as BRIT. Various separation methods were developed, and finally we have zeroed down on a solvent extraction based method for purification of yttrium from strontium. These are various facilities that are used in these endeavors: ion chromatograph, gas chromatographs, capillary base electrophoresis, liquid scintillation counters, etc. These are some of the facilities available for researchers at HB and IGCAR. I'm not listing all, but some important facilities I'm listing: Knudsen efficient mass spectrometry technique for vapor pressure measurements, various advanced analytical methods like LIBS, LIMS, ICP-MS, ICP-OES. Most of the occasions, scholars measure the concentrations of actinides, transition metals, etc., as well as for burn-up measurements, nuclear reactor fuels, chromatograph systems, various chromatographs, HPLC, ultra-high pressure chromatography, which uses about 1000 bar, will be used for super fast separations of fission products, capillary electrophoresis, and chromatographs, facility for synthesis and characterization, electrochemical systems, TG-DTA, DAC for phase diagram measurements. We have OCELs for handling all radioactive materials, neutron activation analysis, of course, radiometry facility, KH and calorimetry facilities, plus various research tools for supporting our corrosion research programs and coating programs. And some of the important publications, I'm happy to share the news that our research scholars have average publication of about 5.13 per thesis. Maybe this is last year data. Maybe I have to look into that, but it's close to 5. It's pretty good. And some of the important publications of our research scholars are reflected here. Good number of publications in the recent past in physical chemistry and chemical physics, Angevandi Chemie, Dalton Trans, Journal of Molecular Liquids, ACS Journal, Industrial Engineering Chemistry, etc. Thank you all for your kind attention, and thank you
very much. You're very clear in your presentation, and it was in time. And thank you very much for bringing out the important research work at IGCAR under chemical sciences, covering very challenging areas in the particularly nuclear materials, sensors, and their applications. The session is open for a few quick questions now. Any questions from audience who are present in person here? Or if there is any specific question on online, okay. Thank you, Dr. Chandra, Sivaraman, for an excellent presentation. And we missed your physical presence here. It would have been great if you could have been here. So thank you very much. And we move to the next presentation, again from IGCAR, under physical sciences by Dr. N.V. Chandrasekhar. So we welcome you, sir, for this presentation.
Thank you,
And,
sir. And is my presentation visible?
Yeah, no, it's not yet coming. I think it will come soon. Yeah, 30 minutes for your presentation. The presentation is clear. It is in full slide, and your voice is also quite clear. So please
Good
take
evening,
the stage.
everyone. And then thank you to HBNA for giving me this opportunity to present on behalf of HBNA Physical Sciences IGCAR the various facilities which are available for research scholars and the research programs, some of the research programs and some few results which showcase our work. And let me go to the next slide. Yes, the physical sciences at IGCAR is a wide spectrum of people, and most of the people, the research scholars, are situated at the material science group, which is the concentration of physicists at IGCAR, and around 18% of research scholars originate from metallurgy and materials group, and the rest of it distributed in engineering sciences, reactor design, and so on, where reactor physics also so part of it, and various other labs. And as you can see, from 2007 onwards, actually we have had around 200 research scholars, out of which 28 research scholars work is in progress at IGCAR presently. And to give you a sample of the coursework which we do, very rigorous coursework, very much appreciated by many research scholars, they are doing very well at various places after completing their PhD work. And these courseworks are actually designed so that when they come from various groups, they get orientation towards the work which they perform from those groups. Like reactor, we have a course on advanced reactor physics. We have a course on laser matter interaction and applications to advanced materials processing. We have a course on defects and radiation damage, which is an important topic in our center. We have a course on soft condensed matter physics and so on. So most of the things are covered here. And there is also a course on sensors, detectors, and laboratory automation. This forms an important course. And recently we have included atmospheric physics and dynamics, atmospheric transport and dispersion modeling as elective courses for students to pursue, because we have these students from various groups. So I will be now listing some of the important experimental facilities at Material Science Group. Material Science Group has a lot of experimental facilities, and what is shown here is a vibrating sample magnetometer for doing the magnetization measurements. And we have a microfocus X-ray diffraction facility, which is coupled to a diamond anvil cell membrane type diamond anvil cell for carrying out the study of material, structural study of materials under subjected to very high pressure as well as temperature, and so that we can scan the pressure temperature phase diagram of this material. Recently, a lot of reactor materials have been examined using this facility, and the thermal expansion coefficients as a function of pressure and it's been calculated. We also have very nice facilities on spectroscopy, Brillouin spectrometer. We have, of course, Raman spectrometer. What is shown at the bottom is the unique facility called laser heated diamond anvil cell facility, one of the unique facilities nationally also, and where the synthesis of novel materials have been tried. I will be showing some of the one or two results from these facilities. And this is one of the facilities which holds a pride place in Material Science Group, the accelerator facility. Very wide-ranging facilities we have, and for the last 4 decades or so, many research scholars have benefited from these facilities, and world over, they have been able to establish their own facilities by the experience they have gained here. Here, what is shown at the left is the dual beam ion radiation facility consisting of 1.7 MV antitron and 400 kV ion accelerator. And this is a recent facility which has been commissioned. And what is shown at the left is the defect produced during the implantation or characterized. These are characterized using positron annihilation. Actually, I'll be showing another slide where some more facility like Mars-Bar facility is also there. So we have extensively the facilities for producing the radiation damage. Not only this 1.7 MeV, 400 kV, also 150 kV ion accelerator, and
a 200 kV ion accelerator at the UGC DACSR Kalpakkam node situated very nearby. So the material science with accelerator has become an important topic, important research area to be pursued by material science, IGCAR. So let me come over to some of the important research programs. As I had told you, we are in a very special position. Slides I missed here. We are in a very special position at IGCAR, the physical sciences group, because we have a wide spectrum of activities where physicists are involved. Thanks to IGCAR, they have given us the freedom to pursue the hardcore physics experiments where we are able to pursue experiments on quantum entanglement. We have got few research scholars completed the physics thesis on quantum entanglement. We have research scholars pursuing basic research on material subjected to extreme conditions like high pressure, low temperature, high magnetic field, and so on. We have research scholars pursuing the nanoscience, and some of the good results I'll be showing here. So let me read out some of the research programs here, which I have listed here. Physical properties of novel superconductors and various materials. And one of the things is that emergent physics with heterostructures. One example I'll be giving later on. And investigations on structure of glasses. One advantage the physicists at IGCAR is having, they have access to materials, structural as well as fuel materials related to reactor. And so we have the advantage of working with those materials. So here we are able to work with borate and tellurate glasses and using the spectroscopy techniques. We are able to work on uranium intermetallic compounds and study their equation of state and structural stability at high pressure and high temperature, and various other materials also, which are relevant to basic research, magnetocaloric materials and photonic hydrogels. In this particular thing, we have recently established the extraction of uranyl ion using the photonic hydrogels, microgel hydrogel combination. We are also excelling in gas sensing and photocatalysis work using the zero-dimensional quantum dots, 1D nanowires, nanotubes, and I will be showing few images of these, and 2D transition metal oxides. And some of these work have won awards for the research scholars, which I would like to point out here. We are also having micro cantilever-based ultra-fast humidity sensing work, which recently the humidity sensing work has been published as a PhD thesis. And we are also extensively worked on vertical graphene based supercapacitor works. We have got very good results, and this work has won laurels and best thesis award also. And we are also working on microscopy using the scanning probe microscope. And of course, our plus point is the defect condensed matter physics, where we have extensive facilities for radiation damage, producing the radiation damage, and also studying the defects using various spectroscopy techniques. Because the ion beam is not only used to produce damage, but also ion beam synthesis and other modification of materials, which I will be showing one or two results. We have a specific group concentrating on the materials modeling, so which interacts very well with the ion radiation damage as well as defect condensed matter physics people, experimental group, and where people concentrate on MD simulation work, DFT work, and so on. So let me give you some representative results on all this, whatever I have listed. And the first one, I would like to talk about the pressure-induced superconductivity in this topological insulator. We have been working on this material because it is a lot of emergent physics. At like for example, at the bottom, what is shown is the proximity effect in a topological insulator, which is placed on a superconductor, niobium. And the interface, because of the proximity effect, the superconductivity is induced in the topological insulator. It's a very recent result, and it is yet to be understood by us very well. And here I have shown few of the recent results which the research scholars have got. One of them is one research scholar has been able to synthesize a new phase, the manganese carbide, using the laser-heated diamond nanometal cell, which I have shown you earlier. And in this particular case, she has been able to estimate the hardness of manganese carbide in the cubic phase and it has turned out to be 40 GPa, which is actually super hot material. So this is a very interesting work which has emerged. And another research scholar in his award-winning thesis, he has scanned the entire phase diagram of this mixed sesqui oxide, rare sesqui oxide, using high pressure structural work. And we use extensively the mega facilities, mega science facilities in India, the Indus 2 facility, as well as outside the synchrotron facilities for our work. What is shown here is very interesting. The image of the surface plasmon polariton wave in indium nanode nanostructure. This is award-winning work. And I think the question which Dr. Sandeep Dara asked is related to this work. And the test imaging of smallest silicon nanowire is shown on the left, and the temperature sensing using the micro cantilever is shown here. I don't have an image of micro cantilever here, but this is a curve which is showing the temperature sensing. And in this particular slide, I would like to share with you the Raman spectroscopy work mostly. And here we have we were fortunate to very hard to get the Raman spectrum of uranium metal. The first time it was recorded using the surface enhanced Raman spectroscopy by this group. And we have at the bottom, this was recorded in Indus 2 high pressure X-ray diffraction. And they have got the first time they have seen the new high pressure phase in the high energy material TEX, is explosive material. And here in the bottom right, what is shown is the microgel hydrogel composite, which is used to extract the uranyl ions in aqueous solution. This work we are still pursuing to establish this particular route for extracting uranyl ions. This actually comes in the colloidal soft condensed matter group. And what is shown here is, as I told you, we have several nuclear techniques we have for defect characterization, and the Mossbar spectroscopy is one of them. And we also have time-dependent perturbed angular correlation spectroscopy. We also have the positron annihilation spectroscopy. Here, what is shown here is that by this technique, we have been able to say that the appreciable defects of A2 type is there in the CO2 FeAl, and that's what is shown in this figure of X-ray diffraction as well as this magnetization versus magnetic field. And we also have very good collaboration between the computational group as well as the radiation accelerator group. And what is shown here is the channeling and DFT studies on this iron chromium. This is not disappearing, this particular panel. And chromium system, and here what is studied is that the chromium, as you can see the bulleted point, the chromium segregation to interstitial loop suppresses oxygen interaction with the interstitial loop, and oxygen is trapped at vacancy loop at iron chromium. This is a very recent result which is published by a research scholar, and she has got her PhD. See, the bottom one is more recent. The ion beam modification used for graphene oxide and how the band gap opening is studied using these techniques, and recently it is published in Carbon.
The slide is not on the next. You are on the same
yes.
slide. Yeah,
So,
now it is.
I have just now told you briefly about the facilities at Material Science Group and some of the important results which research scholars have got. Let me go over to some of the facilities in metallurgy in Materials Group. And as you can see, several facilities for material synthesis and characterization available in Metallurgy Group. One of the recent facilities holds a pride place spark plasma centering facility for making high density pellets, high angular resolution, high temperature XRD. We have EPMA electron probe microanalyzer. We have DSC differential scanning calorimetry for measurement of heat capacity, because there is a group which is working on characterizing the thermophysical properties of the structural as well as fuel materials, reactor materials. And we also have other things. And recently we have got a high resolution TEM, and I'm sure I'm having an image which shows What is shown at the top is some of the measurements for the thermophysical property of the materials like thermal expansion, heat capacity, thermal diffusivity, which is very important for measuring the very important characteristics of these materials. And what is shown at the bottom is the hard face alloy bushes fabricated for the forged reactor application, where it has been found that the hardness is higher than those fabricated through welding route. This shows one of the images recently they have got using the high resolution TEM, where the imaging of oxygen atom has been done. One of the recent results you have got. And this shows other results like the XRD of yttrium oxide, showing ball mill duration induced phase transformation from cubic to monoclinic. Just the ball mill itself induces phase transformation from cubic to monoclinic and other images. So some of the facilities which is there in the smart materials section, where they are working on mostly on soft condensed matter physics. Many facilities are listed here. I will not read out all the facilities, but you can see they have the entire plethora of experimental facilities for soft condensed matter physics. So here the research activities themselves are like the synthesis and functionalization of ferrofluids for magnetic fluid hypothermia. This is a high impact technology which they are developing, and the development of magnetic nanoemulsion, and the development of heat transfer fluids, and the development of nanocomposite for diagnostic X-ray shielding. Many of them have students associated, and you can see the several high impact publications that they have got, and they have also won awards for these students. And synthesis of nanoparticles for dye removal, water purification, and enhanced oil recovery. And few of the results shown here, I will not go through individual results, but as you can see, the lead-free polymer nanocomposite for X-ray shielding, how they have been able to publish, make it, fabricate it, and it is published in a good journal. And many of these results are recent and done by research scholars. And as you can see, in 2015, Best Thesis Award has been won by research scholar. So let me go over to now to the another group where a lot of work has been done on safety aspects, reactor safety aspects, where physics experiments are very important. Here, I'm just listing down many of the facilities and the safety facilities, like the safety of working with sodium is very important for us. Therefore, we have mini sodium fire testing facility. The important aspects of aerosol in the atmosphere is very, the distribution of aerosol, dispersion of aerosol in the atmosphere is a very important part which needs to be studied. Therefore, we have aerosol testing facility. Other spectrometers are available for online nuclear emergency response system is being developed, and we have facilities for gamma X-ray tomography. We have other gamma chambers for radiation, gamma radiation, and so on. So the research programs which are there are on sodium, study of sodium aerosol dispersion and so on, and so dosimetry, because we need to measure the radiation dose, which is a very important aspect of health physics in safety group, and development of facilities for studying severe accident study, nuclear accident studies, and simulation studies of ejection through top shield platform of PFBR. This is also a simulation study, development of whole body counter, and so on. Some examples are given here, but I will not go through this detailed examination because I lack expertise in these facilities. But as you can see, these are all where the research scholars are developing the facility to full-fledged the experimental facilities and then studying few examples. This is on TL-based extremity dose estimation. Formulation for conventional shielding materials, because it's a very important aspect where we need to formulate the shielding materials, design the shielding for various facilities in this center. here the application of gamma ray tomography system for assessment in the reprocessing waste drum. This is a recent facility which has been developed for assay of the plutonium assay in the drum. So let me come over to finally to the physicists who are research scholars who are working for really the accelerator based programs. So here RDTG is a reactor design group and RFG is reactor facilities group. So some of the very few, because the percentage of students working here are very few. So I'm just going to list down some of the important programs in which they are involved. One is the reactor design facility has many experimental facilities for testing the design of reactor components and sodium systems, where some possibilities there to do more modeling and analysis. And that's what is listed there. The computer codes, multiphysics for design and analysis of fast reactor systems. And the second one is the reactor facilities group. Already I have been told that the FBTR as well as common reactors are available for doing nice physics experiments, and therefore these facilities are also open for carrying out physics experiments. So this only shows that recently we have got we have been able to take the FBTR to 40 megawatt, and this shows the 4 configurations which is shared by my reactor physics colleague. And so this only shows that yes, the interesting facility and where interesting physics experiments could be done. Thank you very much. Yeah. Some of the shared by reactor physics person and where the students, some of the few students, very few students we have in this particular area. So some of the work done by them is shared with me. And I just want to share some of the photographs taken few years back, where it shows the vibrant research scholars community we have in Kalpakam and some of the programs they had organized. They had invited us for these programs. Thank you very much.
Thank you very much, Dr. Chandrasekhar, for bringing out the excellent facilities under various groups like RDG, RTDG, RFG, MMG, MG, and bringing out the
this is
work.
spread over the entire center. So that is why we have a variety of programs.
So the session is now open for a few questions from the audience. If there is no question from audience, is there any question online? I had one question. You have elaborated on this lead-free polymer shielding in place of lead. How is the performance? How the performance compares as far as the shielding is compared?
Well characterized. Maybe I can ask the person to contact you and share the more detailed results. This is a published thing.
Okay, no, fine. I'll contact later.
Published one, and I have listened to her, and they are quite confident.
Yeah. Okay. Thank you very much. I thank all the speakers of this session for their excellent presentation and keeping in time and in spite of certain delays from here. And I thank all the audience and distinguished personalities present in the audience here and online mode also. Thank you very much, and I hand over the session to the organizers.
Thank you.
Thank you, sir. This concludes the final session of today. On behalf of HBNI, I thank all the chairpersons and speakers once again. Next on the program is the much-awaited evening talk by Chancellor HBNI at 6:30 p.m. So please take a break now if you need, but I request you all to assemble back here by 6:30 p.m. Thank you. Welcome back. It is now time for the evening talk we have all been looking forward to. Our esteemed speaker has arrived. Welcome, sir. So without any delay, may I please request Professor Vasudeva Rao, Vice Chancellor HBNI, to give his introductory remarks.
Respected Dr. Kakodkar, Professor Grover, directors of various DA institutions who have joined us here physically and online, faculty members and ladies and gentlemen, a very good evening to all of you. First of all, I don't want to stand between you and the much awaited evening talk by Dr. Kakodkar, and neither does he require any introduction to this audience. And certainly, he doesn't require introduction to any DA member. We all know the pioneering contributions he has made in several roles. But what is important for us to emphasize that he was also the person behind the creation of HBNI. And if we are having this discussion meeting here today, it was due to his pioneering and visionary efforts that this institution was created. And we are really proud and privileged that today he is the Chancellor of HBNI. And we thought that it's a very appropriate time for us to listen from him firsthand about what he had envisaged for HBNI and what he has observed in the last 15, 17 years and what he thinks as the way forward. So it will be a great lesson for us, and I'm sure his words of guidance and wisdom will play a great role in shaping further activities of HBNI. So without much further delay, it's my great pleasure to invite Dr. Anil Kakodkar, Chancellor HBNI, to give his address.
You can operate from here. Good evening, Dr. Vasudeva Rao, Dr. Grover, and all members of HBNI fraternity, DAE fraternity, all those who are present here in this auditorium and also at their respective places. Well, first of all, thank you, Dr. Vasudeva Rao, for inviting me here. What I'm going to do in next 40-45 minutes is to share with you some random thoughts about I'm not going to talk so much about what I thought of HBNI or how I look at HBNI today, but HBNI going forward, whatever came to my mind, I thought I'll share this with you. And I want to do that in the specific context of the meeting that you're having. It's a discussion meeting in basic sciences. And DAE, it's all research centers, autonomous institutions. There is a tremendous strength in basic sciences because DAE has all along emphasized on doing research on a broad basis, on an open basis. And we have never asked this question, why you are doing this and what is the application that you see today. Of course, we are talking about the broader domain of nuclear science and allied sciences. And even there, I think the view that has been taken right since the beginning of DAE has been quite broad. So, given that context, I think this meeting is very valuable. And in fact, I was looking forward to such a meeting. I have mentioned this, of course, I mentioned this to Dr. Vasudeva Rao. But I had also mentioned this at the UGC DAE Consortium for Scientific Research. And also, Phil had mentioned this in TIFR as well. And the point that or the thought process there was that, well, we all know the power of multidisciplinary research. And you want to realize that power to maximum extent, it's important that this ecosystem must be very large as possible. And there is a lot of merit to a large ecosystem compared to a small group. You know, just like in nuclear reactors, we have a critical mass. I think doing good research, there is this critical mass, particularly when you're talking about multidisciplinary research. That is not to sort of discount the power of individuals, not to discount the great forays individual scientists have made in their respective domains. But when it comes to multidisciplinary work, and even in basic research, multidisciplinary, particularly when it comes to, for example, looking at research which is heavily based on experimental sort of content, I think these things become very important. And I'll come to this point perhaps again and again as we go along. So, what has been bothering me, and not only in the context of HBNI, but also in the context of institutions at large, that, you know, institutions are the sort of basic pillars of any society, any country. Won't be exaggeration to say that how evolved a country is, you can measure by the institutions it holds. But at the same time, you know, there are institutions and institutions. And if the institutions are not run properly with age, you know, initially when there is new resources, new enthusiasm, you don't see these things. But with aging institutions, you will see a lot of sign of decay. And we have seen this in the academic environment in the country. We have old universities, but I think it will not be very harsh to say that many of them have actually decayed. Contrast that with some of the top institutions in the world. And I have put a picture of Harvard. No, take it Harvard, take it, you know, top institutions, most of them. If you take top 10 or 15 institutions, majority of them are very old institutions and very large institutions. And I think both are extremely important. And these institutions, Oxford, Cambridge are even older. And these institutions are, in spite of the fact that they are centuries old, they are as lively as you know, as any of the other similar or similarly placed institution. And that's very important. And I think we must make sure that HBNI belongs to this category and not the category of institution that decay with time. I have put these two figures here. Harvard on one side, Institute of Science on the other side, which is perhaps the best multidisciplinary science university in India. And in between, there is some data. This one is from Academic Ranking of World Universities 2019. And these numbers vary, as you all know. But the worrisome fact is, if you take the number of universities in top 500 of global rankings, US in that particular ranking has 137, China has 58, and then of course South Korea, Singapore. Singapore is a very small, it's a city nation, but it has 2 in that rank, and India has only 1. And this has been actually bothering me for some time, and of course I'm now engaged in seeing what can be done, but that's a separate story. The point to make is the wealth of the nation is actually correlated to the number of this kind of universities that we have, and I'll talk about that. But before I get there, if you ask a question as to what is that 1, 2, 3 that the institution must achieve, an academic institution must achieve, and you can describe that in many ways. I would say there are 3 major things that we must, at least I would like to count it that way. One, where there is a hands-on learning opportunity on real life problems and a great stakeholder engagement. In fact, this is not the forum, this is atomic energy specific, but in broader discussion, when I say, I almost go on to say that a university must mimic the society in the neighborhood. So, and of course, I'm not talking about immediate neighborhood. Neighborhood can define, and some areas could be far away, but it must mimic that. If there are problems of technology, university must be attending those problems and applying that in the context of the needs of that area where those problems occur. If there are problems related to sociology, humanity, university must attend. And that is, of course, you need to have all rigor that is required in an academic activity, but there has to be that hands-on content. If you are talking about solving a society's problem, no use sitting in your office room or even classroom or laboratory and say that I have solved a problem. That is hardly the solution which is of value. The knowledge is important, what you know, what you develop your understanding, all that is right. But when it comes to actual delivery of solution, you must capacity build people who have learned those skills, abilities through actual hands-on experience. And that requires stakeholder engagement. You can't be building everything yourself. So you should be connected with the institutions outside. You should be connected with industry, society, so on and so forth, so that the students, or for that matter, the faculty members have those opportunities. That's attribute number 1. And I firmly want to repeat this, that unless we achieve this, it's perhaps, you really will not reach that level. I don't know, some of you might have seen, there, for example, many universities in United States, and the Indian students are working there. And they all have to do internship, but not necessarily in the final year, even in every year they keep doing some internship. And many of you might have come to you. Many of those students might have come to you because they say, okay, you are going to India to be with your parents or families or something, but connect with these institutions or connect with these people and think about following questions and come up with a paper or come up with some such engagement. And this is, I'm telling you, this is even for first year students. When they go to their graduate degree or they, and the research students, of course, the engagement is much, much deeper. So this is number one attribute, which I think is very important. Second is the universities, according to me, should be the mentors for the society and the country. You must have seen, at least those who have been following history, all revolutions, universities, have been the place where there were seeds sown or the roots of revolution, thinking process. You may call it, those are the places of student unrest. But if there are issues, of course, but in terms of identifying, in terms of defining what is the current situation, in terms of defining what is likely to happen in next 6 months, next 1 year, next 5 years, and in terms of creating an advice for powers that be, I think it is the universities of standing. Those are very important. And we know that all big universities have been playing that role, and some of them have been playing that role even in the international context. So that's the second important feature. And now we are in atomic energy, and HBNI, it's, I would say, it's what I defined as neighborhood or what I defined as address the problems. For us, it is the programs of atomic energy. And so I think HBNI, we should be able to play that role. And these roles are not assigned by way of a formal assignment or any such thing. These roles, they come about because of the value of the advice that you can create, because of the capability that has been built through research and various discourses that you have within the institution. And I think, as I said, I'm not going to look at HBNI has done wonders compared to the vision when it was started. And I don't have to recount that to you. You're all aware of that. But I'm talking about the next step. And I think we should take HBNI to be the think tank where the opinion of HBNI counts in overall decision-making and policy-making role, not because that role is assigned, but because you have that credibility. And that, I think, is, we should look at this in HBNI context. And I'm very happy that in this meeting, in addition to HBNI, you have our other similarly placed organizations. For example, the DAE UGC's Consortium for Scientific Research, as well as the CEBS and I don't know whether TIFR there is somebody, but now this is important because, that actually enlarges the ecosystem. Through consortium, we are connected with the rest of the university system, which is taking interest in atomic energy related activities, because there is an organic link between us. Same thing is true with the Bombay University, because we had long-standing relations. And in fact, that got modified because of HBNI coming into existence, but CEBS is there. And I think CABS is run primarily by several colleagues from here, Atomic Energy, including TIFR, IIT, and other institutions in Mumbai. And it has, if you go to Bombay University, you will figure out what is the value they have for CEBS. Not that there are no tensions. All good things you do will create tensions, take it from me. But when they got such high rating as a part of their NAC certification, I'm sure some of you are aware how happy with it. And the Vice Chancellor in the same evening, he called me expressing happiness. So that's the importance of this kind of engagement. And I think we should leverage that, because even for atomic energy program, I believe that is very important. So I want to, begin, now this question why HBNI is irrelevant, but still want to recount that. And one is, of course, just now who said, one of you said, yeah, that, there was this experience. Dr. Bhabha created TIFR and BARC. He was director of both the institutions. Both the institutions are in Mumbai or Bombay at that time. But their organization structure are different. But at that time, he did create conditions where there is a lot of synergy between the two. So I call them complementary twins. Now the question is, maybe today the atomic energy system is much larger, and there is a possibility of finding several complementary twins where a lot of things can happen. As I was coming here, I was trying to figure out what is the best example I can share. Because at that time it began because I had seen a failure in terms of ability to connect the strength in basic research and translating that in technology, essentially in the context of thermal sensors based on quantum well principles. Now, at that time, it was a failure. Today, for example, if you look at the hydrogen recombiners, which is an important safety system for our nuclear reactors, I think it has arisen out of the basic strengths, particularly in the area of catalysis. But then it has been proven, and I'm told that these systems have been installed in all PHWR power stations. And let me tell you at this time that had that not happened, in fact, continuing reactor operation would have been a great question mark. And I think it's a great example of the importance of the connect between basic sciences and the actual application or the programs of atomic energy. Today, we're talking about climate change threat. Today, we're talking about the serious issue of carbon dioxide and then the need for sequestration or at least capture and use. And And it is very clear to me that on the basis of technologies that are known today, this problem is not going to be solved. The quantities of CO2 that one has to deal with and the usage of CO2 that we currently envisage, there is a huge gap in the sense the quantities are far too large. And so I think one needs some more fundamental solutions, and that can come only on the basis of basic sciences. And it's not my intention to talk about any particular issue in some depth, but I think it is important to create such complementary twins. And that is the message that I want to leave here. So basic research and technology, we must create, and this was one of the objectives of HBNI, that we specially emphasize research on the interface of basic research and its kind of conversion into a technology product. And of course, we had also said at that time that we will create the fellowship for such students should be somewhat higher, because we want to create that preference. I don't know, but I would still consider that to be a very important objective, because I think it's important that we must be able to build new cutting-edge technologies, first time ever, and that can arise only on the basis of progress in basic research. Otherwise, it will go on the way we have been going on in the past. Somebody has developed some technology elsewhere. We also work hard and repeat that development, which is also important. I'm not belittling that effort. But that doesn't take you to the #1 position in global competition. If you want to be there, you have to be able to do such things ahead of others. And that's where this linkage is very important. And then, of course, something which I have already said, to produce results, one needs large multidisciplinary research environment, a critical mass. And I have put this famous figure, the pasture quadrant, where I think it should be our effort to, wherever we are, I hope we are not in the third quadrant, which is research nowhere. This is for other institutions. DAE were not that bad. But even the other two, where we are very strong in basic research, we should see whether we can look at applications, and wherever we are essentially extremely strong in applications, even there we should really look at the fundamental science behind it. So everything should go to pasture quadrant, and that should remain our focus. Now, I mentioned that it is institutions of this kind that determine the wealth of the nation. I'll find it very hard to give an example from India. The only example is atomic energy itself, or for that matter, programs like space and things like that, where I think the whole technology and whole commercial enterprise, and I think there atomic energy is a much stronger example, because we are operating as a commercial enterprise, but it has come about on the basis of the R&D done within the department. But other than that, I find it very difficult to find an example. So I have picked up Stanford example, because there's some data available to the contribution coming from Stanford. Stanford University has over 2,100 award-winning faculty members, including 19 Nobel laureates, 2 field medalists. I'm sure all of you are at least aware of these things, and not only Stanford, many other universities. Companies such as Google, Cisco, Yahoo, HP, Charles Schwab, eBay, Instagram, VMware, and Tesla have Stanford roots. According to a 2012 study, since 1930s, Stanford entrepreneurs, faculty and alumni, have started 39,900 companies, which in turn have created 5.4 million jobs. And they are generating US $2.7 trillion in revenue annually. And notice this number is comparable with India's GDP. So that is the power of a high-ranking academic institution. And I think at least I, for one, would like to dream HBNI, if not going there, nearing such a thing. So for me, my vision of HBNI, and this is arising out of the TIF or BARC experience, is to sustain a peer-driven, open research culture in the backdrop of pressures of implementation of a mission mode program. With all of you, you may be faculty here in HBNI, but you have your own respective pressure. You know, this plan project, you have to deliver, you have to spend so much of money, you have to place this order. And these are all important things. You cannot belittle them. But that is not the right atmosphere for doing cutting-edge research. Cutting-edge research, you must leave people free to think. Dr. Banawali is here, and I remember when Tata Memorial Center, the new block was constructed, Dr. Dinshaw was the director. She was very particular that we reserve a place where the so-called researcher doctors, because they have to do both, they have to attend patients, but they're also doing research. They created a good launch. I have not seen it, by the way, Dr. Banawali, but I think there is a very nice lounge there for people to relax, and it's important. In between two operations or in between two other activities. It is important. You shouldn't treat this as a luxury. You need to create an atmosphere of this kind. So, and then similarly, so one is to come away from pressures of your so-called quote-unquote mission mode programs, which are, by the way, important. DAE has emerged because it has implemented mission mode programs successfully. But you want to do something which is, let us say, world-class and something which is emerging for the first time. And time has come now that we're talking about, of course, right now, we're talking about a little mid-course correction, but three-stage program is still the mainstay. And I don't think any other country will take to thoriums in the same time frame as India would have to take to thorium. So it will be something different than the rest of the world. And so I think you need to create peer-driven, open research culture. That's the key, according to. Second, we should be able to leverage strengths across DAE institution, what I mentioned, the complementary twins, to remain in the forefront of emerging technologies likely to be important to DAE programs. And this can come about in many ways. One of the thing I remember, I don't know what is the progress on that, was this question of looking at reprocessing plants, and they require sensors. And you're talking about radioactive plants handling radioactive substances and all. But at the same time, people are talking about materials which can be, in fact, suspended in that medium and then pick up signals, and you pick signals out and then process it to find out what is the pH of solution, what is the concentration, what is the thing. Now, such a thing is possible in principle, but converting that into reality is a lot of work. Now, there may be a few people here and there doing this. I think we should capture some of these things because they're extremely important for our program. And then, of course, at that time and even today, we have the new BARC campus coming up at VIII. And I think that campus, the work should be organized differently to be a part of new philosophy of doing science and technology, and particularly at the new campus at VIII. Now, I don't want to go in further detail. I don't even know whether it's happening that way or not. But according to me, all the basic sciences or basic topics, whether it's in physics, chemistry, biology, or even material science, metallurgy, or even, say, more research-oriented activities in engineering domains, they should be done in a university-like manner. While running of large facilities, the reactors, the reprocessing plants, and the like. And along with that, there is a technology development that goes on. That could be the national lab structure. And so I see no reason why nuclear physics division, or for that matter, chemistry division, should not be under the umbrella of HBNI rather than being a part of that. And you can connect that as a part of same institution, but I'll leave it at that, but I think it's a very important thing from my perspective. Now I want to take this a little further, and one question which I often ask myself, and that is, why is it that we have only, very few institutions within that first 500 and practically none in first 100? And should India not have an ambition of having at least a few universities which are within, say, first 20, or if that's not possible, within first 50? And whether HBNI will be able to reach there or not, I don't know, because HBNI is relatively small on that scale. But I think for a country like India, we do need that. So our higher education and research institutions need to be both knowledge creators as well as value creators. I think, looking at this in a blinkered way is actually, we are being unjust to ourselves. So wherever there is a possibility, so I think we should look at both. And that seen in HBNI context, I would imagine that to facilitate atomic energy program in India to be future ready. And I say this now because I think it's absolutely important that the future, I imagine future to be atomic energy, not just occupying a much larger share in the global energy scene, but it would also change complexion in terms of technology. And it will change this complexion in a very big way, thanks to the ingenuity of human mind. And the question is, we have been so far followers. We did our own development. We did self-reliant development, but we basically did what others have done. And in fact, we still continue to be highly risk averse. Now the question is, can we take atomic energy in India to be future ready? For example, people are talking about hydrogen. I'm just telling you. One knows that we can use high temperature nuclear reactors for splitting water just by getting heat. But we also know, some of colleagues who have worked in our research reactors, we know that a slight change in pH and you have very fast dissociation of water, and it becomes a crisis to contain radiolysis of water. So there, of course, the job is to prevent radiolysis, which we do successfully. But here is a way of promoting radiolysis. And what is radiolysis? Radiolysis is production of hydrogen. Now, with this so much of talk about hydrogen, why is it that one is not exploring that? And with these reactors, I think there should be a good way of production of hydrogen. I'm not saying that maybe thermochemical splitting is still the larger way of producing, but you can produce it at very little cost because the radiation is anyway there. The question is, it's very risky. Obviously, it's very risky because that's what causes the explosion risk. But if we know how to control radiolysis, you can use it to suppress radiolysis. You can use it to accelerate radiolysis in a way that you can produce hydrogen in a safe way. I'm just giving an example. I have not gone into detail. Maybe more often than that, the established will say this is a stupid idea. But the researchers don't get distracted by that. They would want to understand if it is stupid, why it is stupid. But so I'm just saying that we must make our place future ready in terms of human capability, in terms of addressing emerging needs, in terms of the global technology trend. If some new technologies are going on elsewhere, we should be there on the front line. And in terms of stakeholder engagement. Because we still have this problem that people, particularly in our country, people are still hesitant about talking about atomic energy. I haven't seen many people saying today, now that we have made a commitment for net zero, to say that without atomic energy, you cannot achieve net zero. I don't know why people are scared of talking about it. I was very happy yesterday, Times of India wrote an editorial, and they cited this. But we have that, it's such a simple, obvious fact. But even in atomic energy, we are scared of talking about it. So why blame others? So there are these perceptional issues on part of stakeholders. And who is to blame? I don't think we can blame them. We have to blame ourselves. Because stakeholder engagement is an equally important part. And I'm not saying stakeholder engagement is a public awareness program and all that is important. I think there are much deeper things that one needs to understand. And these are, I think, topics of fairly detailed research. And I think HBNI should not shy away from looking at that. Second, R&D intensive high technology. And I'm now talking about the emerging technologies which are making waves. Now that constitutes the main engine of economic growth in today's world. We are all talking about AI, machine learning, big data. Now that has already come in the technology application in a big way. But there are also other areas which are still in the research domain: genetics, quantum physics, cognitive and brain sciences, and so on. And these will become technologies of tomorrow. And there is a huge amount of kind of effort to build technologies on these. And at least some of the groups in which I'm engaged, it looks to me that the gap between India and the most advanced countries in the world is actually widening. Now, at least HBNI cannot allow that to happen. So I think we should open up our horizons. When I say future ready, that is what I mean. because, and this requires a different kind of ecosystem, the so-called triple helix ecosystem. It requires, of course, the university or the academic environment to do the research at its best, but it also requires industry to be a part. This is how we miss the semiconductor revolution. India perhaps is the best country. It was at that time. Even today, it is the best country in terms of capability in material science. But the industry participation, particularly in the context of the fabs and the related infrastructure, it didn't come about there. So also the government policy making. Now, the triple helix ecosystem or architecture requires the R&D setups or R&D part, but also the industry and also the government, both in terms of investments as well as in policies. And it's very difficult for the so-called non-enlightened decision makers to make this decision. That's what happened. You would suddenly say you have to invest $1 billion, and people will hesitate. You need credible advice. You also need bold policymakers, and only then it happens. And all these things are in that category. Now recognize that atomic energy had that ecosystem. Thanks to Dr. Bhabha, it did create that. It could support open-ended research. It could muster investments, and it could kind of influence the government in the right policy making. And that is how we are here. Now, what about the future? And that is what I think we should be looking at. So DAE was way ahead of time. HBNI should take it to the forefront once again. And that's another objective, in my view, for HBNI. A comprehensive and large ecosystem is the key, as I mentioned, and we have it. DAE laboratories, autonomous research institutions, and I mentioned the Consortium for Scientific Research and CEBS. So leveraging our common roots, we should start operating as a large science-based multidisciplinary research environment. And that is the sole purpose with which I am standing here today. And that is why I requested the Consortium for Scientific Research as well as CEBS to be a part of this gathering. Because it is through this that we can create a new high-impact knowledge as well as technology. Now, I'm not saying that the individual groups will be able to do everything, far from it. But I think we can create an environment where people can network between themselves to do this. So in that context, at least you have to make beginning somewhere. So what is it that we can do immediately? What I said earlier were much bigger objectives, and we'll have to prepare a lot. But I think, first of all, we need an advisory mechanism between HBNI and DAE to coordinate research agenda. It's not as if you do research whatever you want to do, because research also should have focus. While we talk about open-ended research, we should allow maximum choice both to students and faculty. It should not contain that, well, I'm telling you, you do research on this problem. That's terrible. But at the same time, there should be a direction. There should be a focus. And so there has to be some discussion between DAE, and we should think of creating a mechanism for doing so to coordinate these programs, look at the gap areas, and identify research topics for each domain so that there is sufficient choice for students. And this was done, I remember Dr. Baldevraj has done this in the context of reprocessing program. And a basket of problems was created. I think we should do that in practically all domains. And that can be done only after an understanding of what do we want to do and what are the gap areas. And it is on the basis of such detailed assessment that we can create so that students have still wide enough choice, but we remain focused on what we want to do. And it so happened that talking to Dr. Vasudev Rao, I did get some more ideas. So, for example, each constituent institution, as you define it here in HBNI, it should publish a list of research topics that students could choose. Let it be in open domain. What are the topics you do, because otherwise what will happen is if you just leave it to students, it may drift. The focus will be lost. At the same time, we want to give the choice. So you publish that list and allow students to choose. Each constituent institution to publish a course calendar, because you have you have several courses going on online. Now, it should be important that the students from all constituent institutions should be able to benefit that. And it's no use you publish that 5 days or 2 days before the lecture, because they cannot plan like that. But if this is done and planned well and published in advance, then the institutions can coordinate their schedules. The individual students can coordinate their or work out their schedules. And so there is a wider choice available for students that, well, I want to audit this course from here and that course from there. And I think the system within HBNI should actually allow. You need to work out equivalence and all, and working out equivalence is not very easy. But that's the trend. Even in the new education policy, people are talking like that. So within HBNI, I think we should be able to do that and allow students to kind of get credits out of auditing courses delivered in some other institution of HBNI. Joint guidance is another important area by guides from different CIs, more particularly that, something that brings in the complementary strengths needed to address multidisciplinary research problems at hand. And we talked about that. Now, this is the academics part. But when you're talking about a fairly large number of students, I think we are responsible for their career, their personality, and their future. So I think just teaching them and granting degree, we cannot be restricting HBNI vision to that, because we are talking about life of young budding people. So I think we should look at it in a comprehensive way. So diverse student activities, which allows them to gain life skills, personality development, fulfill their aspirations or aptitudes in arts, culture, sports, continuing student projects. This is also very important. There are many places, in fact, IIT is a classic example, where they run projects where the projects run for 7, 8, 10 years. See, IIT students, they made almost a toy aircraft, but to a specification to fulfill particular objective. And this was, I think, some 8 or 10 years ago. And it was a student project. But then it's like a relay race. A batch today, it hands over to the batch that comes next and all, because these things take time. Right now, there is a project going on in IIT on Hyperloop. Again, a similar student project. So the point I'm making is, and I'm sure I have mentioned earlier, that the high temperature nuclear reactor was developed in Tsinghua University. So I think we could think of such student projects, of course, in coordination with constituent institutions, but it can be great in terms of new development, but more importantly, it would be great in terms of upbringing of students. The same way there should be, I think we should take industry linkages seriously. So industry linkages, startups for development of technologies and system level development. You know, most of our universities are emphasizing startups, which is a good thing, but just by startups, you cannot build big systems. You cannot build an aircraft. You cannot build a nuclear reactor just by startup culture. You need people to work at system level, people to work on platforms, and then fill in the, several gaps by way of the products coming from startup. So we need both these and create entrepreneurship around that, entrepreneurship development around that. And I think HBNI today is now matured enough to start thinking of that in the context of atomic energy. And I'm sure, see, one of the thing which at least I'm asked outside is that why is it that there is no expertise outside atomic energy? Now, you may say that's an unfair question to ask, but it's not so unfair from point of view of people. They say, why is it that we have to be dependent only on you? So think about this, and I think we must open up somewhat and expand our sphere of activities. Now, I did talk about VIII campus and VIII campus planning and development. I hope we will do differently. Otherwise, it will be a repeat of what we have been doing in past and won't be capable enough to handle the future. I'll leave it at that. Career opportunities for graduating students. This is very important. And many students have expressed their concerns and anguish on these issues. And I think something should be done. Of course, we had this K.S. Krishnan postdoc arrangement, but the question is in research within DAE or for that matter outside in the country, because otherwise all of them will go abroad. And of course, I don't think that is necessarily very bad, but it is somewhat bad, surely. And also jobs in industry. And I think we should start worrying about placement of our students and that kind of an activities. So it's a policy activity as well as a physical activity that we need to do. Then connection between students and DAE, particularly the large DAE facilities and programs. I was told that there are many both autonomous institutions, faculty as well as students. Many of them, they have very little information about what atomic energy is. And that's not a very healthy sign. I think we must make, when you're talking about stakeholder connections, these connections are important and a stronger links between these institutions, which I already said. And then I have listed here a large number of topics for want of time, and I think this is not the place to discuss this. But there are very many areas, and they are not restricted just to science and technology, but these need to be addressed. And in my view, they also include the things like energy studies and power system studies, power finance, and so on, but also other areas of management, which is the best way of running an organization forward and running an organization with futuristic objectives. I see no reason why there should not be a sort of, I'm not talking about a management school, but at least a management group which engages in these areas because the program is large. Now, I talked about synergy between DAE and other DAE connected systems, CSR and CEBS and TIFR. So I'll just run through this. I think it's important that we create a common mailing list. How to create that? Just some thoughts. Create a mailing list for lectures and courses which are delivered online. And that in itself, well, I think I don't know whether such a thing exists. If it exists, it's very good. But if it is not, then I think this is just an information sharing. Similarly, share list of problems being handled and facilitate broadening of discussion and network around that. I may be working on my particular thesis topic, but can there be a network where other people can participate and they say, I can also contribute there, or my idea is this. And essentially an environment where more networks can emerge. So a little bit of bottom-up approach rather than top-down approach. Create opportunities for internships for students in laboratories with shared interest. So the internship is an important part of learning, and some of it is done in some other lab, will also help from the broader aspect of learning. Similarly, a greater synergy in sharing of experimental resources and instrument building effort. And I think some of these larger projects where DA is participating for way of making in-kind contribution, I think it has gone on extremely well. Several universities have done some very good work by way of producing such hardware. But within HBNI, can we think of such a possibility and explore networking of projects related to common theme and eventually kind of lead to so-called coordinated research projects, so that if each project may be an individual entity, which it has to be, but if you're talking about a theme, a larger problem, if that is subdivided into 10 or 12 or 15, whatever that number it could be, projects, and each project does kind of adds value, then the overall theme, you create much larger impact, and the program of DAE becomes that much bigger. And I think, again, maybe it is happening, I don't know, but if it is not happening, I suggest we pick it up. And that brings me to the end of my talk. And I thought I'll end up with this cartoon, which is very relevant to, I think, in many places, but also academic environment. Learning, teaching has to go hand in hand by evaluation. Now, and that evaluation, of course, we are not rigid about evaluation, but a flexible evaluation with choice left to the teacher is an important thing. But even so, we should recognize that no two students are alike. So here is a classroom of animal kingdom, and you can see the diversity. And I think that diversity is extremely important. If you want to perform as a group, that diversity must be leveraged. But if I'm an old-fashioned teacher and say, no, I must have a fair selection. So for fair selection, everybody has to take same exam, and I will evaluate them and put you in merit order. So the exam here is climb the tree. The rest of it I'll not comment, I leave it to yourself. But I think this sketch has a tremendous lesson in academics, and academics across the board in the country suffers from this, and we should do so. According to me, we keep on talking about diversity, we talk about natural diversity, particularly in modern context. Every activist will keep on talking about diversity. But why can't we respect diversity within ourselves? And in fact, diversity is the essence of excellence. And we talk about diversity in nature, but we forget about diversity amongst ourselves. And we tend to regiment everything. And that is fundamentally against principle of good education. That's my frank opinion. So I will stop here. Thank you very much. Yes, yes.
Friends, you will all agree with me that it was a very, very stimulating lecture, and it's such large number of points for thinking about that it will take some time even to absorb and debate. We are glad that a forum like this has brought together CIs from all over the country, and it is possible that through such forums we can further take some actions towards the points mentioned by Dr. Kakodkar. So we are immensely grateful to him for this very inspiring lecture. He is willing to respond to any questions from the audience, either physically present or online. If any of you would like to make any observation or put some queries.
First of all, thank you, sir, for this illuminating talk. See, recently I was attending one DST meeting. Yeah, recently I was attending one DST meeting, and there I learned that DST is also going to go similar way as HBNI. All DST organizations, they will be coming together and they will go a common university system where the academic degrees will be awarded like HBNI. So this is one way good, what you had started that they are going to copy. But in that context, if HBNI has to retain its uniqueness, so which way you foresee the future HBNI?
Yeah, I'm aware of that because I chair a couple of DST institutions. So they're all scratching their heads. There is a committee chaired by Dr. Balram, which is what is happening is good. But the driver for what is happening is not so good. The driver there is apparently the Ministry of Finance said that DST has too many institutions. I think it had come to atomic energy also. Too many institutions, you should combine them. And then they struggled. So there are some institutions which are research oriented. So they are becoming a university. There are some other universities of different kinds. So they are combining in. So DST is trying to handle this issue. And that the basis for the driver is bothering me. So actually, I was asked, so there was also an attempt to combine academies because they are also DST institutions. So I was asked this question, and combining academy is not so easy as combining institutions, because institutions you can order them around, academies you cannot. So I was asked that why don't I play that role in bringing them together? So I flatly refused. And I was asked, why do you refuse? So I said, do you know, we have classical music gharanas in India. So I said, yes. So, for example, if Gwalior Gharana and Kirana Gharana and Agra Gharana, that's the same Hindustani music. So why can't you order all of them to become one Gharana? So at least the person says, yes, I have understood, I will not talk. But the problem has not stopped. Problem is still going. So I have problem with the driver for that. But otherwise, it's a good thing which is happening. Okay, sir. Thank you.
So this NIAS has a good role of a think tank and giving advices and management. NIAS, National Institute of Advanced Studies at Bangalore.
Too much of I have become an old man, right?
NIAS, Bangalore is playing a good role in scientific think tank and giving management trainings to the senior persons from various government organizations.
Yeah.
But its role is not that way. It's a static institute in a way, I feel, apart from radar. But why there can't be more such institutes, or it is not expanding? What is your view on this?
See, a country like India, which is fast changing, I said that, even universities should play the role of mentor for the society or even the government for that matter. And now, so you need such think tanks. There should be plenty. And so I'm happy about the fact that there are many more think tanks today than what they were some time back. So far, so good. But you have to be also, you have to have think tank which are capable of independent thinking. And that is where there is a problem. And let me again cite an anecdote. When I was in the department, and we always face this problem of people wanting to comment all kinds of things. And at that time, we were talking about international cooperation and all. So I went to powers that be, I'll not name whom, and said that, look, we must involve our think tanks so that, we. Said, but where is that? Who are those think tanks? So I cited some examples. Do you have confidence in them? I said, no, I have not explored it from that perspective. But so I was told, if you want, go ahead. But if something goes wrong, it's at your peril. I said, okay, will pursue this. And then the think tank started doing some bilateral discussion. India versus US. Okay. So you have one meeting and you have some team from India, some team from United States. And then you discuss, you produce a report, maybe 7-day meeting, you produce a report. Then they decide, okay, next meeting we'll have in United States. And then I noticed that the main attraction for many of our think tank people was that opportunity to go to United States. All right. Now in that composition would not remain same. Who is talking what would be watched. And the composition for the next meeting would be selected appropriately. And now it's no brainer that you can do little statistics. You do that 3 or 4 times, you can get any think tank to say exactly what you want to say. It is, and this is a game which is going on and on and on. So now, having said that, I still say think tanks are important. And we need think tanks which are really independent. And see, India is, after all, 75 years is not too long. We are still bachas in this game. The other countries are very, very mature in this. So we are in the right direction, I suppose. But, and I leave it at that. Okay?
Sir, my question is related to your point on internship and entrepreneurship, industry, academia linkage. So the question is like this, that with the advent of technology, the information passing has become easy. Means people can email or send through cloud, etc. That has opened the doors as regards means passing the security hurdles which we faced for sharing the documentation and information. Now it remains to the scientist or the mentor that how much he wants to pass, that he can actually control without much of the hurdles. But access to laboratory, that has still remained a big challenge for the interns and for the entrepreneurs. So could you guide that there is some way which can open these things also in the same manner as these days we are doing to the information or communication. I hope my question is clear, sir.
Yeah,
It
yeah,
is-
question is very clear. And again, I'll start with an anecdote. See, we have a system that any paper published, I'm not talking about HBNI, I'm talking about, let's say, BARC or IGCAR or RRCAT or things like that. So any paper published by anybody has to be approved. I think it's still there, right? Huh?
It has.
Well, by division
it has
head,
been
group director,
decentralized,
Trombay
yeah.
council, whatever, but it has to be approved. Now, and nothing wrong with that. That's the right thing to do. I know at my time it was happening, and maybe it is happening even now. So the paper won't get approved unless the boss's name is on the paper. Is it happening now? Put your
No, situation
hand
is
on the heart and say yes or no.
situation is much better, sir. It is much better. It is not like
Okay, much better. Okay. Now the question is, why does a paper needs approval? And I had said this at that time itself. See, paper needs an approval when we are talking about the program. Invariably, many people, will describe in the introduction, we'll write about atomic energy program, 3-stage and all that treatise, which has nothing to do with that paper, but it's written. Now, such narration must be checked because you are talking about the program. But if you are talking about a scientific topic, for example, I talked about catalysis. You are talking about, let us say, you are using catalysis for recombination of hydrogen. It has, strictly speaking, according to me, nothing to do with the program. It still needs to be checked. Even in industry, paper has to be approved because there is an IP issue. If there is a new intellectual property, then you've got to be careful about whether you want to divulge it now or later. You want to file a patent first. All those issues are there. But I don't think that weighs very much here. Okay. Now, wherever there is a judgment or judgmental description or coverage on the program, I think it has to be cleared. It has to be approved. But it has nothing to do with the program, and there is a pure scientific research. According to me, there is no need for anybody's approval. So all you need to do is to make sure that there is some certification that I am not divulging or creating any value statement on the program. That's it. Or of course, in addition, you can say I'm not divulging any secret information. Now, so I think this problem can be very simply solved. On the other hand, it is important that see, for example, you have an HBNI student and one of your guides who are also working inside. Whether you sit in Anushakti Nagar or you sit inside and do work, which way it makes difference to the confidentiality or secrecy. It's the same. So similarly, if this person is working with somebody inside for purpose of internship, as long as these principles are clear, why there should be a problem?
Sir, I think my question is little different, sir. Let me clarify this. Suppose some intern or some entrepreneur wants to work on a lathe which is owned by Central Workshop in VARC.
Sorry, I think there's
no,
getting a
sir,
lot of echo.
somebody wants to use a world-class instrument or a world-class machine which organizations like BARC are having.
Yeah.
But he is not a part of the system. He is in the industry. How should we open it to him?
Yeah, but what is the problem?
So,
see, the problem is the instrument is, again, the issue is I buy an instrument, it's a costly instrument, somebody has to be responsible for its maintenance, proper use, and also somebody is asked that, well, you are responsible. Now, that doesn't make that individual owner of that instrument. Now, certainly that person has made efforts, so his or her research should be priority, no questions asked. But don't tell me that instrument is busy 24/7. And I know institutions where expensive instruments, multi-crore instruments, are actually run 24/7 and are used in a time-sharing manner. In fact, here, right in IIT, some of you go to IIT regularly. They are very expensive. Even students are going to use it. So you have to go through this process of training them, skilling them in making use of that. And all those people who get qualified, they are free to use. They are actually, they are IIT, I know even the nano fabrication and those instruments, they are being handled by students. So don't tell me that other people will spoil my instrument. Not correct. You have to go through that training. But this is, in fact, as I said, one of the purpose of bringing HBNI into existence was to eliminate this hierarchy-related problem. There were too many hierarchy-related problems where in fact, see, I have become old. So I would take liberties with my words. So at my time, a young training school chap complained to me that my head of the division doesn't give me work. So I then sat with that person. I spent 2 days understanding what is the work that was given here. So he was given some work, he has completed. Some trivial work was given. The fellow was good enough. He finished it in 1 day, went back. So he gave another work. He finished that 2 days, he went back. Third day went. So the head of the division tells the student, "Arey, ek din kaam nahi karoge to mar nahi jao." Now, is that the way? So maybe this is an extreme example of hierarchy-driven things. But I think we need to change that. And HBNI is one of the many things it should achieve is also to achieve. There's too much of this hierarchy thing. And hierarchy will never allow good research to flourish. Take it from me. So, so there are issues of this kind. And I think internship is something very important, fundamental. But I think there are people from other places coming and doing internship here. And they're very happy. I get feedbacks of all kinds. You must be managing those internships, right? So they are extremely happy. So why not HBNI? What is the problem with HBNI? So this is actually the mindset issue. And I think all of you, because you are collectively, you are a large thinking force. And only you people can correct this system. You're all at a very senior level. Why can't you correct this? Okay. So pardon me for being blunt, but sometimes message goes across when you're blunt.
1 or 2 more questions because it's already quite late. Dr. Durija?
Sir,
So you can now imagine the freedom that a retired person gets. No, I'll not fall. Yeah.
Thank you for your illuminating lecture, sir. Sir, nowadays with average age rising, I think 60 is very younger age for somebody, for the department to retire him with so much of knowledge and experience. Do you think HBNI should have a mechanism to have some 5 years tenure or 10 years tenure for the retiring faculty members?
Well, if you ask me as an individual, my opinion is a researcher should be allowed to be active as long as he's physically fit. Period. Don't ask the age. Now, the rest of it is Babugiri. I also do Babugiri at times, but I think there are many places where the age is not so wrong. You go to many of these universities, there are Nobel laureates there, and some of them are nearing 90. They are active. So now at the same time, it's also true that this is not a right. In the sense, you can't cite that so-and-so was given extension, so I should be also given extension. And if you get into that, then the whole thing gets kind of undone. And that is what you are suffering. Otherwise, some attempt was made at some stage. But you are suffering exactly this. That sab ghode 12% doesn't work. And you try to do that, we are where we are. Because excellence has, you have to have discrimination on the basis of excellence. And there must be some transparent yardsticks and all. Everybody should feel that whatever is happening is fair. If there is a feeling that things are not happening in a fair way, then it's a different matter. But as long as that is done, so you have to be, for example, in fact, in government rules allow that. Armed forces, if you, let's say you are at a particular level and at a given age, if you don't cross some level, then you are out. That's why we find many retired colonels and retired brigadiers, retired major generals, because either you make to the next level or out. Or in government, there was this 55 years and 58 years earlier. It was also with the same thought. But in the government, the whole thing has got diluted. So everybody goes on to whatever is the retirement age. So you make 60 to 62, everybody goes there. 62 to higher, everybody goes there. It doesn't work like that.
For excellent people, I think there should be age limit 65, 70, 75, some advancement.
No, I'm telling you why there is an age limit. As long as people are performing, allow them to perform.
I think we will, Dr. Samal, only one per question, please. And I think your task on this because there are 50 people online.
So, sir, thank you very much for illuminating talk. So, I am worried sometime because that's what I feel. Because you mentioned that we require a critical mass, and that is what I think a critical mass, or when you want to do excellence in research, I think there must be a critical mass of scientists to address a problem or to do a thematic research. But in this context, I want to know how HBNI will play a role, because there are many CIs. So let's say they are recruiting some faculty members, whoever. So how HBNI will play a role? Because for whatever my experience, I think that critical mass is really necessary to do good research. Otherwise, it is impossible.
Well, I think this is not a very difficult thing, provided you liberate yourself. And I'll tell you what I mean by that. See, in HBNI, whatever your program committees or board of studies or whatever, now, one is you have your regular role cut out, but at least once in a year, once in 6 months, if you decide that, well, whichever subject you are handling, where it is going. And on one side, as I said earlier, look at gap areas. And on the other side, look at its importance in the context of atomic energy program. All right? And based on that, you define a set of problems that have remained to be addressed. Now, supposing you identified some 10 such broader topics, further break down into individual PhD problems. They may be there 100 or 200. Now, as far as the individual student, individual thesis supervisor, individual thesis topic, it will remain the same as it is now. but bring in a coordination between these projects. For example, you obviously must be having seminar where student talks about it. So you bring in all these students, other students who are doing this related areas, because seminars are supposed to be open anyway. Or the faculty members can talk about. Or for that matter, many of you must have done IAEA coordinated research problem, which is not the best example to cite, but at least that concept is very good. So if there is that kind of a coordination, occasionally a discussion meeting. So today you are having discussion meeting on basic sciences, which is very broad. But let's say you have a discussion meeting only related to all topics connected with that major theme, in which there may be 10 PhD students or 20 PhD students or whatever. And look at all aspects of this. You will automatically form a critical group. Now, when you see, again, as I said, on one side, whether that group has become a strong group to earn recognition from peers in the country and outside, that, okay, if this area, this is the group of HBNI, which is a very big, we have notions. A certain topic, we know that that group is the best in this area. So you earn that recognition on one side. On the other side, look at what's happening in DAE and where we want to go and mobilize that activity. So more people will join. So that is how this critical group will come. I think it's a simple matter to do. It's your own regular meetings and all, as long as you do some little nudging, this will happen. I think this is not at all difficult thing to do.
Okay, thank you.
I think you must give chance to that lady. She had the hand and you had refused only.
Thank you so much, sir. Sir, my just a little thing I want. You mentioned about grooming the younger generation through HBNI. But in the organizations as large as BARC or DAE, as the people rise up, the middle level also tends to become, a large fraction of it tends to become dormant. So your 2 cents on the need to groom the middle level.
I'm sorry, I have not understood this question clearly.
Sir, through HBNI, through various programs, through various suggestions that you discussed and talked today, you talked about grooming the younger blood, the younger generation. But in organizations as large as BARC, as we have seen a large fraction of people, as they rise up, they become dormant. So your thought, your 2 cents on grooming the middle level.
Yeah, okay, I got it. Well, let me, today you are much better off because of HBNI. Before HBNI, there were, of course, there used to be students coming in for their PhD. For example, Bombay University scheme had, I think, 4 in each discipline, physics, chemistry, biology, right? So 12 and 12 into the PhD time, 4 years or whatever. So some 50 odd students were of that kind. Then there was a DBT scheme and a lot of students used to be. But compared to size of BARC, that number was very limited. And then, of course, there were other who will come from training school. And of course, now everybody in training school in science, they're at least an MSc. There was time when they were also BSc. So they would do MSc, they would do PhD. So that was also a student community. But for example, if you now, when that was the larger student community compared to what was the other students, whom I call floating population. Bad word, but just to understand the concept. Now, if you don't have floating population, then your academics will invariably suffer. And that is because of the problem you mentioned. And that is that, in a hierarchy, if you notionally say that you have 30-year residence time in the organization, So which would mean that roughly 3% or something new people will come and that many people will go. And then you will have an age profile in the organization. So now how many students a researcher will get to guide? And as you said, in a group, if there are 5 people, and you may get maybe 1 or 2 students. So who will corner that student? The senior most one. And then the middle level people will say, no, I don't have any student to guide. Then okay, you also become a co-guide. So it was, but the ratio of student to guide was actually completely wrong in those days. And one of the things which has happened because of HBNI is because now you have number of students who join as a student and after the degree they leave the organization. So that ratio must have been, I have not seen the numbers, but must have been significantly corrected. And so now probably not so old or relatively younger people would also get their students, at least in comparison to what the situation was earlier. So in terms of maintaining culture of research, I think existence of HBNI must have done a lot of good to the research culture, apart from the other issues which I mentioned. Now, whether that will solve all the problems which you are mentioned, or see, the other problems are related to the mindsets. And there is a distinct mindset difference between a, at my time, we used to call a PWD mindset. And no ill feeling about those who have been working in PhD, in PWD. But PWD says, I have a project, I have to deliver, this is the rule I have to follow, I don't care about anything else. Whereas here you want a mindset which is inquisitive. Can I do it differently? Can I, is there something new? And that's a complete. So, as I said earlier, once the mindset opens up, this problem of senior junior also will vanish, which you perceive. And actually, this is an indicator. According to me, this is an indicator. As long as there is a problem of senior junior, from a research perspective, be sure there is a problem in the organization. A good research organization, if you have 20 people, in a cluster, and then you ask somebody from outside, watching from outside, find out who is the senior most person, and assuming that the person nobody has gray hair or something like that, you cannot identify who is the senior most. On the other hand, if it's a hierarchy controlled organization, within minute you can find it out that he is the man, because all faces will be pointing towards that person. And that's a big difference between the organization. And this is a very serious matter. And we need to correct that culture internally. And I hope that HBNI would have made some difference. I'm quite sure it would have made some difference. Maybe we have miles to go, but that's. So that was the long answer to your question.
Thank you, sir. Thank you so much.
Thank you, sir. Let me quickly conclude by inviting everyone to dinner. Everyone, please assemble for a photograph.